Okay, good morning, everybody. So we are ready to start the final day of the conference. So it's my pleasure to introduce the first plenary speaker of this session. She's Professor Griniewicz from Steklov Mathematical Institute, and he will be talking about approximate finite gap formulas for the specially double periodic Davy-Stewartson two-rock waves.
First of all, I would like to thank the organizers for the invitation to visit this nice place. Now, I would like to present our very recent results obtained in collaboration with my colleague from Rome University, Paolo Maria Santini. Because if I understood there are also lectures for students, I'll start from some more popular introduction. First of all, very fashionable topic now is the theory of rock waves. First of all, there are some photos, maybe are not directly related to the talk, but nevertheless, rock waves in the ocean. What does mean rock waves? I think there were some other talks here, and what's important, the rock waves are waves which are much higher, maybe 2, 3 or more times higher than surrounded waves. And what is the difference with tsunami? If you talk with tsunami, the origin is very clear. There is some earthquake, and then it generates. The origin of rock wave is not completely clear now. There is a big number of researchers in this area, but I'm not ready to say that everything is clear. But nevertheless, this is a hot topic. Another beautiful picture, the photo from the Bay in Biscay, there are photos from internet, pyramidal wave near Japan. But one of the reasons, of course, these huge waves can be very dangerous. They can destroy the ships, therefore. And for sufficiently long period, there were some reports about rock waves, but they were treated maybe more or less as sailor stories. I'm joking that they were like mermaids. Sailors saw mermaids, but nobody believed him. The same was with the rock waves, but the first confirmed observation was the New Year wave on Dropner oil platform, 1995. You see this wave. But what's interesting, the rock waves are observed not only in the ocean. I prefer to call them not rock waves, but anomalous waves. Because in the ocean, the waves are very destructive. Of course, in optics, they kill nobody, but nevertheless, they may be important. And the rock waves were experimentally observed in the ocean, in the water tank, in photorefractive crystals, in optical fibers, in Bose-Einstein condensate, in plasma physics, and the list, of course, is not complete. But it's more or less clear that these anomalous waves are rather typical for nonlinear systems. And also, I saw some articles arguing with this point of view, but maybe the standard point of view now is that the rock waves is a nonlinear phenomenon and is associated with modulation instability. So, first of all, rock waves are essentially nonlinear waves. And the second, maybe they're associated with some modulation instability, and therefore you have to study nonlinear models. And well, of course, very natural question. We have some completely integral models. And of course, it's a very natural idea to try to use these completely integral models in the theory of rock waves. Because they can be studied analytically. And moreover, I would like to ask it was yesterday a very nice talk. They explained that also nonlinear Schrödinger equation seems to fit very good in real ocean experiments. But first of all, I would like to mention 3 very, very old and classical papers. Bespalov, Talanov, Benjamin Fair, and Zakharov. They studied modulation instability. This paper was dedicated to study of modulation instability in nonlinear liquids, in nonlinear optics. The other 2 waves, the other 2 papers were dedicated to the study of modulation stability in ocean waves. And I would like to stress that in the papers number 1 and 3, it was shown that to describe modulation instability, one can use nonlinear Schrödinger equation. In fact, there are two real forms of nonlinear Schrödinger equation, with plus and with minus. If you have nonlinear Schrödinger equation with a sign minus, there is no modulation stability. It also has some dark solitons, but nevertheless, it corresponds to stable medias. If you have plus, this equation describes unstable media. And therefore, if you would like to study modulation stability, you have to study self-focusing nonlinear Schrödinger equation. You have to assume that the sign is plus. Algebraically, of course, these equations are equivalent, but if you study the analytic properties of solution, of course, there is a big difference. In some sense, equation with plus is more complicated, but has much richer structures. Let me recall, because I am interested about self-focusing analysis, that it is completely integral because it can be written as compatibility condition for a pair of linear operators. Here I recall the formulas. We have two linear equations for psi x and psi t, where psi is two-component vector. And these equations are compatible if and only if nonlinear Schrödinger equation is fulfilled. It's a very old result by Zakharov and Shabbat. And it admits to integral. But in fact, our interest in the problem was motivated because our collaboration with experimentalists. What they wanted to study? They wanted to study recurrence of anomalous waves in photorefractive crystals. So there is experiment. Experiment is the following. We have a crystal, potassium, lithium, tantalate, neobat. This crystal has the following properties. If you have electric field generated by light, the refractive coefficient increases, and the area with high intensity of light works as focusing lenses. Therefore, if you have some original distribution of light intensity, the areas with high intensity, they work as focusing lenses, and they collect energy from neighborhood areas. Therefore, instabilities increases. And you can see some coherent structure. You see. Also, in optics, nonlinear Schrödinger equation is a good approximation. So what is the figure? There is some central laser beam. There is a green laser with vertical polarization. There are two side beams. The two side beams are obtained from the same laser by semi-transparent mirrors. Therefore, the picture is completely coherent, and two side beams generate small modulation of intensity of the central beam. And also there is another red laser. The reason of using the red laser, they make the system close to integral, because, of course, nonlinear Schrödinger equation is an approximate equation. But using the red laser, they tune the parameters of the media, so it became a good approximation. Now, the nonlinear Schrödinger equation, in fact, instead of times, we have z direction. It describes the special evolution of the intensity. And theoretically, you should cut the crystal and measure at different distances. In fact, in experiment, it's slightly different, but okay. And what they obtained? What they obtained is the following experimental figure. First anomalous wave, second anomalous wave, third anomalous wave. So they observed the recurrence of anomalous waves. But the question was, they wanted not only to observe, but to have some theory. And we were invited to participate as theorists, to suggest some theoretical model. So we came, and there is comparison. First, there is comparison of the measurement with the Akhmediev breather, very good agreement. And there is comparison with this first appearance and the second appearance. The curve is theoretical prediction. The points, dots are the measurement. So at least we obtained a good approximation. And now we demonstrate what happens if they change the intensity of red laser. Here we have this almost integrable situation. We have 3 recurrences. Here they decrease the intensity of red laser. The system became non-integrable. The corrections nonlinear Schrödinger equation became high, and you see that there is no more recurrence. The picture changes. So the transition between here is non-integrable, here is integrable. This is experimental data. Moreover, you see that the structures are partially periodic. Therefore, it's very natural to study spatial periodic problem for nonlinear Schrödinger equation. So we came to the following problem. First of all, we have nonlinear Schrödinger equation with periodic boundary condition, and we have to study the recurrence of rock waves. First of all, what we know, what we knew before. How to solve Soliton equations with periodic boundary conditions, especially periodic boundary conditions. The method was invented by Sergey Novikov and developed by Dubrovin, Matveyev, Itz, Laks, Matkin, Murbik, Krichiver. Sorry, I don't want to, the list is big, but. And what's the idea? Let me try to explain what does it mean, finite gap. Assume that you would like to integrate the Korteweg-de Vries equation. The Korteweg-de Vries equation is integrated using the spectral transform from one-dimensional Schrödinger operator. I would like to maybe to tell the students that we have time t, but the time t is nothing to do with time in quantum problems. There are absolutely different types. From the point of view of the quantum problem, t is a parameter. But we have a one-dimensional stationary Schrödinger operator. And we have to study the spectrum of the Schrödinger operator. What was well known? Why the problem was well studied quantum mechanics? Because periodic potential is a motion of electron inside the metal, inside the crystal. Of course, we can consider 3-dimensional crystals, but okay, one-dimensional models can be also considered. Assume that we have some crystal, one-dimensional crystal, quantum crystal, and we have some potential. Potential created by nuclei and by other electrons. And we have a quantum particle in a periodic field. What we know about the spectrum of the quantum particle? First of all, we have some critical energy. Below this critical energy, this crystal is not transparent. The particles could not move. It's some like wall. So we have an infinite gap. Then we have some spectral point. Sorry, maybe I choose not very good colors, but this purple colors. So, but if you have classical problem, then if energy is below this, they could not move. Above, particle could move. But we have quantum, so the situation changes. We have infinite, but for some energies, we have resonant reflection. Due to resonant reflection, the particle could not pass through the crystal. So we have some extra spectral gaps. So we have the following spectrum. Some spectrum and some gaps. What is known? Okay. And also, how, if you consider solid state physics, how people write eigenfunctions. They assume that eigenfunctions are quasi-periodic. Potential is periodic. But the eigenfunctions are quasi-periodic. If you shift to the period, they multiply it to some constant factor. They are Bloch eigenfunctions. In fact, physicists usually consider for real energies the Bloch eigenfunctions. But also there were a paper by Kohn who considered complex continuation. And also how to select the spectrum of gaps. We simply solve ordinary differential equations, find some these solutions. It's problem of ordinary differential equations. If absolute value of kappa is equal to 1, the solutions are bounded, we are inside the spectrum. If kappa is not 1, in fact we have 2 kappas, but kappa 1 is kappa 2 minus 1, we are in a gap. But in fact, what Novikov starting point, that in fact, the Bloch eigenfunctions are well defined also for complex energies, not only for real one. And they are defined on a Riemann surface. The following Riemann surface. We have spectrum, and we have the ends of the spectrum, the ends of the gaps. We have a two-sheeted covering of the spectral plane, and the branch points are exactly the ends of gaps. It's rather easy to show. Therefore, if we have periodic problem, we have a Riemann surface. Because the Bloch eigenfunctions, they can be extended to complex domain, and they are meromorphic on a Riemann surface, which are two-sheeted covering of the complex plane. Two-sheeted because we have second-order equation. And now the idea was the following. First of all, assume that we have a generic smooth periodic potential. What we know? We have typically we have infinitely many of gaps. But if you consider gaps with large numbers, they are very narrow. They tend to zero very fast. And Novikov told, okay, let us consider a special class. Assume that all gaps in some finite number has zero length, so roughly speaking, disappear. Assume that we have only finite number of gaps. It turned out that potentials with finite number of gaps can be considered as an analog of finite Fourier series in the linear theory. Of course, we have linear Fourier series. We could not consider infinite. In the linear theory, we couldn't consider infinite Fourier series in the real calculation. We truncate, we consider Fourier polynomials. These finite gap potentials are analogs of Fourier polynomials. And it turned out, if you consider Riemann surfaces with finite number of branch points, there is a big machinery developed at the beginning of the previous century or end of the 19th century, Riemann set of functions and so on. And it turned out that these solutions can be explicitly written in terms of theta functions. It's good news. What is bad? Because if you'd like to apply the formulas, we see that all parameters are some transcendental expressions. How to work with them? It's a problem. How to use the formulas? And also Novikov always tells that before using the formulas, we need some effectivization of them. But what we were lucky? Okay, we consider the self-Fox and Schrödinger equation. But we don't want to construct, of course, there was some papers, I think it's Kotlerov, Cherednik, many others, Previatov, many people, I don't want. They started periodic problem on linear Schrödinger equation. Also, I would like to mention Ercolani, McLaughlin, Schober, they also consider this problem. But if you would like to study recurrence of rock waves, you don't have to study generic periodic solutions. You have to study special periodic solutions. And what is special in this periodic solution? The special is that we start from a constant background plus small periodic perturbation. So we would like to study modulation stability. Therefore, we have unstable background, we have small perturbation. We study evolution of perturbation. But I would like to stress, we have small parameter, but the problem is fully nonlinear because perturbation reaches level of 1, so it's a fully nonlinear problem. It's not linearized. But due to the fact that we have such special data, we have very special Riemann surfaces. Not generic, but very special. They are close to rational one. And due to the fact that they are close to rational one, you have a small parameter in the problem. And due to the fact that we have a small parameter of the problem, we can construct approximation. And okay, so first of all, we can forget about unstable modes. We keep only unstable modes. Then finite gap solutions can be approximated by n Soliton solutions. Everything is explicit. And keep only session solitons. Okay, I will talk what happens in 2D, so I don't want to explain this in detail, but let me show some. No, because we have theta function is a Fourier series. First of all, we can sum not infinite sums, but we sum over hypercube. And essential solitons, we don't sum over full hypercube, but we sum only over some faces. So we do the two-step reductions. First step, instead of infinite sum, we choose which hypercube is the leading order hypercube. In the second, in this hypercube, you don't have to sum over full hypercube. It's enough to sum over some lower dimensional faces. I'm sorry, okay, maybe I don't want to go to details, but nevertheless. And also, you see, this is some numerics. Moreover, we took n equal to 6. It works which number of unstable modes is not too high, but we choose at least 6, not 1. The second figure is approximate solution. So you see. And next we subtract the two solutions multiplied by 1000. Moreover, it's some numerical artifact. I'm sorry, because the numeric was very long. It's very tricky to make reliable numerics for this problem. It's very unstable. So this, I took 8 hours, and maybe I required 24 40 hours to remove this artifact. But you see that very good agreement. So we have some approximate formulas, but they are really good. Of course, we have small parameter, 10 minus 6. If you make perturbation bigger, the formula is not very good, but nevertheless they remain reasonable. And these formulas instead were used for comparison with experiment. So our aim was to take these finite gap formulas, but instead of something transcendental expression, write some asymptotic series, which result in good numerical agreement. You have some asymptotical approximation, but numerical agreement is good, what was a little surprising for us. Moreover, we don't tune the phases, we simply compare two solutions, we simply subtract two solutions, we don't correct phases. Understand? Okay. But now, the problem is the following. It's so far so good, but sometimes you need 2 dimensions. Fortunately, it's more mathematical problem. It's not clear how relevant is for physics this 2, but nevertheless, let's do some mathematics now. Let's now come to the new results. The idea was the following. Okay, you would like to do something in 2 dimensions. There are 2 problems. First of all, the list of integral equations in 2 plus 1 is much shorter. I think about interesting. The second question. In dimension 1, we have, okay, Riemann surfaces with branch points. We have very good parameters, branch points. In dimension 2, we have generic Riemann surfaces. There is some technique you can book by, of course, Babenko, Nolsky, Matveev. There are some techniques, but nevertheless, it's more complicated. So there are extra technical problems and shorter list. But nevertheless, we decided the following system. We decided to make calculations for Davis-Stewartson 2 equation. Why? First of all, it's completely integrable 2 plus 1 system. Second, okay, maybe there is not very good because it has really different real forms. At least some of the real reductions are were derived in real physical systems. Unfortunately, the reduction we working with, we have to find out if there are, but we believe it should be some physical applications. Because other real reductions are physically applicable. This one, we hope that they're physically applicable, but okay. Nevertheless, so it's equation which has 2 properties. It's relevant, at least it's relevant in some real physics, and also it is good. It's integrable. Now, we write this Davis-Stewartson equation. It's this equation, and there are 2 parameters, it and nu. It is plus minus 1, and nu square is plus minus 1. It's non-local, you see. The potential Q is expressed in terms of U using those non-local relations. This equation is completely integral in the following sense. It admits the following zero curvature representation. Now, here I wrote nonlinear Schrödinger equation. Here I wrote Davis-Stewartson. You see that if U doesn't depend on Y, Davis-Stewartson becomes nonlinear Schrödinger. Because if you don't have Y dependence, you see that Q is absolute square of absolute value of U. So we have nonlinear Schrödinger. And we have three reductions. First one, nu is equal to y. The spectral problem is hyperbolic. And we have nu is equal to 1. Then we have two options. It is minus 1 and it is 1. The difference is that this corresponds to is defocusing Davis-Stewartson equation. This is self-focusing Davis-Stewartson. And you want to study Rog waves, therefore we have to consider focusing Davis-Stewartson equation. So we decided to study the Rog wave Cauchy problem, periodic, doubly periodic, for the focusing Davis-Stewartson 2 equation. Also, let me make some remark. We wrote the relation between Q and U in the Fourier space. If nu square is 1, this operator is well-defined and bounded. If nu is minus 1, we have an unbounded operator. And I think how to define doubly periodic problem for Davis-Stewartson 1, at least this problem requires very serious investigation. We may have some small denominators and so on. But if we consider Davis-Stewartson 2, U is well-defined bounded operator. The only thing is that if kx and ky is 0, we have only one integration constant. So if we have doubly periodic problem and Davis-Stewartson 2, Q well-defined in terms of U up to integration constant. Okay. You may say that maybe, but fortunately, this Davis-Stewartson has this, it has this gauge transformation. You simply can shift the phase. We can tune the phase, and we have big freedom. You see that we have freedom with simply multiply phase by arbitrary function time. And it corresponds to the arbitrary choice of integration constant. Therefore, we have this non-locality, but fortunately, there is nothing dramatic, because if we have non-local equation, we have to be careful how to find this operator, and we have to be, but fortunately, here is non-dramatic, because this non-locality only implies this gauge freedom. And this gauge freedom is physically irrelevant. Also, you may assume that 0. Now, also, I would like to make extra remark, because Davis-Stewartson equation has application in geometry of surfaces in R2. And this topic was studied by Iskander Taymanov. And also, he did a lot in the theory of the doubly periodic Davis-Stewartson 2. In particular, he proved, there were two papers, there were Taymanov and Krichiver. Taymanov proved the existence of spectral curve using some results of some functional analysis technique of Keldysh. Krichiver did some more explicit. We, in fact, have followed Krichiver approach. But I would like to mention that were two important papers. What is the difference? In the one-dimensional case, we have the proof to prove that there exists a Riemann surface is exercise for second year. Here, to construct the spectral curve, to prove the existence, it's some serious result, serious scientific result. But, and also another thing which we did not study, sorry, I have 20 minutes. Okay. Another interesting question is that we did not study the problem, we plan to study it. Because what is the difference? In contrast, nonlinear Schrödinger, Davis-Stewartson admits singular solutions. And Taymanov showed how could you interpret singular solutions. Because this theory is connected with conformal properties. Assume that you have surface in R4, which is bounded. We can make inversion, and then after inversion, we can obtain an unbounded surface. No, the surface will evolve in time, and it will be unbounded only at some moment t. Is simply, if original surface passes through 0, we make inversion, passes through infinity. Therefore, this conformal map is Mutard transformation of the original solution. It maps regular to solution with blow up. So Stewartson admits blow up. It may be physically relevant. Sorry, I'm talking about different, but I remember it was talked half a year ago by Pavel Lushnikov, who is a real physicist, and he studied collapse in Stewartson 1. So at least collapse in Stewartson has some real physical applications, some real physical problem. We have also collapse. We didn't study it, but nevertheless, it's important problem, and a good tool for studying this collapse was suggested by Iskander Naimanov. I want to mention. Okay. So what we would like to do? First of all, we would like to develop the direct spectral. So first of all, there is some inverse problem. You can construct complex operator and then select. Complex means that U and V are two independent complex Solid functions. That you have to select reductions. Sorry, I decided not to go into details because it's not finite gap audience. So maybe, but nevertheless. And there are this set of functional formulas. Okay, first of all, what does mean set of functions? It's called Riemann period matrix. So zeta functions are the following Fourier series. So we have some expression. What is not very good? To use this expression, we should know Cz, Cz bar, Ct are three constants, vectors a at infinity 2, a at infinity 1, Wz, Wz bar, Wt, a of t, k. We have many letters, and we have to use the formula, we have to know all the letters, you agree. And usually, it's not a trivial problem to calculate all the letters. But what is our result? Assume that we consider the, assume that we consider anomalous wave Cauchy problem. So we have Davis-Stewartson equation is a doubly periodic setting, and we consider the following Cauchy data. A constant and unstable background plus a doubly periodic perturbation. We may assume that the mean value is 0, also we may assume A is 1, we can rescale it. Okay, for simplicity, but it's technical. So we consider the following Cauchy, we call it anomalous wave Cauchy problem. We have stable background, and we have doubly periodic perturbation, stable background. How these perturbations will evolve. And now, okay, so let's introduce notations. First of all, we assume A is equal to 1. We add this extra constraint. This is completely non-restrictive. We also assume that some generality. First of all, what's natural to do? Consider the Fourier expansion of the original perturbation. Then, if you consider monochromatic perturbation, then we can calculate the growth rates. And we see that if kx plus k1 is smaller than 4a squared, these perturbations are unstable, and they are seeds of rock waves. All the other perturbations are stable. Okay, we would like to work with finite gap. As I told, typically, Riemann surfaces are infinite gap. But what we have, roughly speaking, we will have some handles associated with Fourier harmonics. And we can forget about stable Fourier harmonics. Consider only unstable Fourier harmonics. We have finite number of unstable Fourier harmonics. And consider only unstable ones with this constraint. You see, kx and k1 are integers times this expression, Lx and y are the periods. So we have only finite number of nx and ny such that this inequality is fulfilled. And we restrict ourselves only to unstable modes. We forgot about stable, because stable modes remain bounded, remain small.
So the sum is finite.
No, yes, we can forget. We take fine, or we make some approximation, because in some sense, each handle corresponds to some Fourier harmonics. And we forgot about everything, so roughly speaking, finite sum, yes. Because all in other terms remain small. Okay, of course, if n is very large, it's not completely true, but okay, formally, we can have small epsilon. The only question is, for which epsilon works reasonably? If n is to be million, I don't know, maybe epsilon to the e to the million, or maybe something bad, but okay. But if epsilon is not, but if you have small number of unstable modes, which is maybe one of the approximation, then stable modes can be neglected. Now, we have, remember that the spectral problem is the Dirac operator. And we have to consider, we have to calculate and describe this Fermi curve for this Dirac operator. We have Dirac operator in class of double periodic function. We multiply it by sigma 3, but it's not essential. We have this equation, and we have to describe the Fermi curve for this operator. First of all, assume that epsilon is equal to 0. We have this equation, 0 size equal to 0. Then we have this. We can easily solve this equation, L0 size equal to 0. This equation can be easily solved. And the solution can be parameterized in the following way. This is a parameterization solution of this elementary exercise. Now, what happens? Let's find concept of resonant pairs. Here we follow in Krichever. What does that mean, resonant pair? You have two, tau 1 and tau 2, such that P2 minus P1 is Kx, Q2 minus Qn is Ky. Then we tell that tau 1, tau 2 is a resonant pair. If we have this relation, equivalently this relation. And in fact, each resonant pair corresponds to some harmonics. We assume that we have generic situation, so we have only pairs. In fact, we can have more high multiplicity. It's a very interesting question, but okay. Let's do the generic case, and then let's study the exceptions later. So, now we simply calculate all the resonant pairs. You see there are two types of resonant pairs. If you have unstable mode, that we have two, tau 1 and tau 2. Tau 1 and tau 2 are on the unit circle. So, if you have unstable modes, the resonant pairs are located on the unit circle. If you have stable modes, you can again calculate the corresponding resonant pairs. But they have the following property. One is outside the unit circle, another is on the unit circle. Here is the real sum model. We took the following Lx, Ly. Calculate the resonant pairs. For example, here is two resonant pairs for stable modes. And the resonant pairs for the unstable modes are here. For stable modes, I draw only two pairs, otherwise it's too much on the figure. But you see that, for example, this is, for example, this is 2-1 harmonics. This is 1-2. But for example, this is 1-1. 1-0, 0-1, 1-1. So you have two types of resonant pairs. Resonant pairs on the unit circle and resonant pairs of this type. Our ideology, we say, okay, we forgot about stable modes. It means that we forgot about all these points inside and outside, and we have resonant pairs only at the unit circle. So, okay, you see the figure. The resonant pairs corresponding to the unit circle, on the unit circle. Now, and let me formulate the answer. Okay, formula. Okay, maybe the same formula. Also, a little better that C's are equal to 0, but what is good, you see? Yeah, okay, we have beta jk, but okay, let's see J and C minus J are Fourier harmonics of the perturbation. We enumerated all harmonics, all resonant pairs by J. So you see. You interpret AJ, BJ. We have a resonant pair, we have tau J minus 1, tau J. So alpha J and beta J are simply some very simple linear combinations of Fourier harmonics. Now you have the following approximate formula for the diagonal terms of Riemann matrix. You see that we have logarithm of epsilon square. So it's big negative number. And due to the fact that it's big negative number, of course I lead in order formulas. You don't have to sum all. You have to choose only the right hypercube and sum over one hypercube. All points outside except this main hypercube result in small corrections. Therefore, it's not a series anymore, it's a finite sum in the leading order. I don't want to discuss how to select the hypercube because it's technical detail, but it's okay, it's maybe first or second year mathematics. It's something very elementary. You see, absolutely clear formula. Also we need other guys. Let's have other guys. Okay, AFD. So you see, all the ingredients are written absolutely explicitly. Sorry.
No possibility. You
No, it's leading order approximation. It's direct problem. Yes, it's of course it's leading term formula. Moreover, in contrast, one-dimensional case, we plan to, in the nearest future, we plan to compare with numerics.
But this formula follows from your assumptions about the poles.
Yes.
Uniquely.
Yes.
So it's fixed.
No, we did the following. We posed this assumption, and we did leading order calculation. Some direct, fair leading order calculation. No extra assumptions, yes. It's some direct calculation. Or some direct perturbation theory, nothing more. Yeah, so we obtained this formula. No, we simply did the following. We calculate all the objects. Of course, maybe we have to check. In one-dimensional case, their formula is a very good approximation. Here we have to check, but at least I hope that. Okay, let me describe a little the Riemann surface. Okay, this is unperturbed Riemann surface. If you have to introduce the cycles, you see, but you have a resonant point. A cycles goes this, and B cycle goes this. And what happens if we make perturbation? It was a double point. For example, this and this, it was a resonant pair. We have a cut here, we have a cut here. If you go here, if you pass through cut, you come from this to this. And the statement is that we have in the leading approximation the position of the cuts. So we simply fairly calculate the analytical properties of the solution, perturbation, and calculate the cuts. You have monochromatic perturbation, resonant pair, we have this approximate formula. So we know. Next step. Okay, it's like we found similar formulas in book by Fay, but okay. But we did calculation for this example, and Fay it was how to do that. Maybe I tell that in Fay explained how to calculate. So we have the following formulas for basic differentials, you see. So we have such, okay, with such very fine basic differentials. So, and we know the cycles of which we have to calculate over the cycles, integrals, you see. And if you have, you see, we have such omega. So if you calculate the integral of the cycle, you simply take the values of the guy on the ends of the cut. Okay, it's elementary, more or less standard calculus. And we obtain this formula. Also, maybe I think maybe also it was question I remember when I presented first time. It was Mikhailov's question. Sorry, but could you calculate the vector of Riemann constants? Very, very clever question. And to calculate the Riemann constants, first of all, you have to select the following collection of cycles. Okay, I almost finished. I draw this for this example. It's not very difficult. And then we calculate the periods, and okay, we can do we know these cycles, and we, in the leading order, we calculate and we obtain So, no, maybe I decided not to. Maybe I would more or less to stop because I'm afraid I don't want to go into details of calculation. It's not reasonable. But the statement is the following. We develop perturbation theory, but let me make some remark. You may say that it looks very similar, but this Riemann surface is not hyperelliptic. You don't know very good representation, but moreover, yes, of course it's possible to use some type of Schottky type parameterization, okay, some Schottky series. There is some technique how to work. But what is good, you see that you have this leading order formulas and the problem how to calculate. But I would like to stress that this surface is not very simple. It looks simple, you agree. But in fact, from the point of view, if you treat it as a real Riemann surface, it's not hyperelliptic, and I don't know how to obtain a good description far before the asymptotical. The asymptotical description is very simple. Also, you have good approximate formula for basic differentials, you see. For example, okay, maybe something, you have this formula. And if you go about the cycle, you see that we have logarithm. If you go about the cycle, you get 2 pi I. It's clear. And so forth. But if you would like to go above further, it will be maybe not so easy. But nevertheless, the idea is to, if you stop at this level, this figure seems good. And I would like to remark that as well as I know, nobody did it for two-dimensional system, because for one-dimensional system is much easier. No, there were some numerics, of course. Al Osborne, I think Babenko's group, they did a lot of. But I think it was done for generic, like KP solutions. And our approach was, don't consider generic solutions, consider only solutions corresponding to anomalous waves. And in this case, we have good approximation. So maybe it's time to stop now.
Thank you.
Ну, скажем так, нет естественной структуры. Понимаешь, в отдельных случаях это может оказаться, но это не естественно. В том дело, что это не есть естественное открытие, это какая-то более-менее общая поверхность. Удивительно, что тут все как-то получилось просто. Это, собственно, конечно, Кричер обнаружил, что поверхность, история с Talking Russian потоки.
No, that's fine.
Нет, собственно, было открытие Кричера, что в теории КП возникают все поверхности. Здесь то же самое, все поверхности возникают в общем.
А картинки всякие, численные
ближайшие планы. Извините, просто я прошу прощения, как говорится, ну, это мы планируем сделать, но я могу сказать, что препринт вышел в понедельник. Это совсем свежая вещь, как бы, то есть действительно численный счет, это, как говорится, ближайший план, но мы хотим, ну как-то мы решили, скажем так, первый шаг выписать формулу. Я могу сказать, мы сделали один чек, вот какой. Sorry, maybe some remark, I make some remark, that we did the following test. We simply took Fourier series, and then we substituted into the formula. You understand? Very primitive test. We have the set of function formula. We substitute and we reproduce. So at least the test was passed. But, okay, about numerics, it's an nearest plans, but...
Okay, there's one more question.
Петр Георгиевич,
Да.
Я с английским, конечно, не сильно дружу, не очень понял, какое отношение в дефокусирующем случае вот эти сингулярные решения имеют к проблеме этих вот роковых волн, да, волн убийц.
Нет, я говорю, это как бы другое замечание, просто я говорю, был доклад физика, который говорил про сингулярность. То есть я хотел сказать, что реальные физики изучают сингулярности Дэвида Стюартсона, скорее так. То есть сингулярности Дэвида Стюартсона, да, другой редукции, но тем не менее утверждение, что как бы это, скажем так, утверждение всего лишь, что это я видел реальные физические работы, причем реальных квалифицированных физиков, которые это изучают. KOZLOV с Дэвидом Стюартсоном — это реально физическая задача.
Это не намек на то, что эти роковые бывают
меньше Integrable нет, а это неверно. Это не связано. Но как просто говорю, просто проблема в том, что я, говорится, немножко извиняюсь, что пока не вполне ясно именно вот эта вещественная редукция, в какой физике она возникает. Но я как-то верю, что было бы удивительно, если бы остальные возникали, это нет. Скажем так. Но это пока вопрос.
Actually, I have a comment on this about applications, because indeed, if you deal with water waves, you can derive Davis-Stewartson 1 for capillary waves, which are very short, or for some particular cases. For example, now it is interesting that you can obtain this equation for water waves on the surface covered by ice sheet. And for example, it was even derived by Victor Scherer with a Korfer in 1984, Davis-Stewartson 1. But if you speak about Davis-Stewartson 2, indeed you can obtain this equation, this system of equations for water waves on the surface of any depth, water of any depth. But then when you derive it from privative equations, you will have coefficients. And the system is integrable only for a particular combination of coefficients. And it occurs only in really shallow water, KH smaller than 0.5, when the system is completely modulationally stable. Therefore, if you speak about water waves, it will be Davis-Stewartson 2 defocusing.
Yes,
so,
it's exactly what I told. You don't know where you have in physics Davis-Stewartson 2 focus.
So, but not in hydrodynamics.
Yes, you are completely right, but I think maybe I told that it's an open question where we remember we discussed and we were a little upset that it's defocusing.
Actually, this idea to use Davis-Stewartson 2 integrable, it was actually we discussed this already 20 years ago, and it was a particular attempt by Victor Scherer also in 2008. He hoped that your system would be applicable to water waves, but unfortunately,
but maybe I hope maybe sooner or
maybe in some other.
At least we decided to do mathematical part.
Okay, yeah, thank you. But it is very interesting what you presented. Thank you.
But in fact, the question was, can we do at least something into the or because I was afraid about, because if we have not hyperelliptic generic Riemann surfaces, what are the parameters? It's a problem maybe. Fortunately, here it works.
Okay, any more questions or remarks? Have you used the same approach for KP conduction? That's just really
I don't know about, no, maybe, but I don't know about rock waves of KP.
Yeah, I mean about rock waves.
No, we are interested, no, as well as I don't remember, I think KP2 doesn't have rock waves.
I see.
Yes.
I see.
If I remember, KP doesn't have. It's the reason why we're interested in Davis-Stewartson 2, not KP, because at least there is a model with rock waves.
Okay.
But thank you for your question. Yeah, it was maybe, okay. Thank you. Of course, you are right that unfortunately, in what way we have defocusing. But maybe I told, we hope that we will find something. Because if it will be focusing, we will tell, okay, we have. Maybe I would be glad if somebody, one of the reasons I hope maybe somebody will find something.
Okay, thank you very much. Let's thank the speaker again. Thank you. So, we're ready to move to the next talk. Will be online. I have to apologize because I messed up Stefano's talk title, so he is going to be talking about a different topic, which I will read right now. So, hi, Stefano.
Hi, can you hear me?
Yeah, I can hear you very well, and now I'm pressing, I think now you are even able to share your screen.
Okay, so let me try. I will try to share, right?
Yeah, just enabled, so I think you should be able now to share.
Should share my desktop.
Okay, yeah, that we can see your screen now.
Can you see the presentation?
Yeah, I can see the presentation and now I can see it in full screen. So I'll tell you how it works. So we see you on this big screen, so I'm going to go to the other side so that you don't think that you are talking to, to an empty chair. So we see you and listen to hear you, so yeah. Okay, thanks very much. So the next plenary, yes, I should move it to the big screen, just 1 second. Okay, the next plenary speaker for today is Stefano Wapnitz from Sapienza University of Rome in Italy, and he will be talking about statistical mechanics of beam thermalization in multimode optical fibers. So, Stefano, you can start whenever you're ready.
Okay, thank you. So, Tiris, first of all, for inviting me to this meeting. And then I would like to thank my co-workers. As you can see, this what I'm going to present today. It's a result of a collaboration between my group in Sapienza University in Rome and the group of the Novosibirsk State University. So we have been collaborating in the frame of a mega grant over the past 5 years, so that has finished with the end of last year. And the last activity that we have done, in fact, involves both the theory and experiments of the analysis of the dynamics of multimode beams in optical fibers. And so again, I would like to thank the main people, in particular Mario Ferraro and Fabio Mangini, who have developed both the theoretical aspects, and in particular I've done most of the experimental results that I will present today. And then Mikhail Gervasiev is a PhD student in Novosibirsk, together with Denis Karenko. They have put in place this mode decomposition, experimental mode decomposition approach, which has enabled us to compare theory with experiments. So we have transferred, thanks to mutual visits that happened last year, which unfortunately now would be more difficult to continue given the situation, travel disruptions. So thanks to their visits, we have implemented their method also in Rome, and so that enabled us to carry out the experiments that I'm going to describe using our own laser sources. So I will start by this is just outline of what I want to cover today, by giving some background information and introduction into the topic, and also motivation why this work is interesting both for applications and for fundamental science. And so the main effect that I will describe in the next slides is a particular effect, which is a nonlinear effect that occurs in multimode fibers, which have a particular index profile that is graded parabolically across the transverse cross-section of the core. And the effect is called the beam self-cleaning. So it involves cleanup of the beam that comes out from multimode fibers, which typically is dirty. So in the absence of nonlinearity, you get the speckles, you get a noisy, spatially noisy signal, transverse intensity pattern, and nonlinearity magically improves and changes dramatically the beam profile. And so it's interesting for many applications of multimode fibers. And what had been missing until now, and it was quite controversial, the theoretical description of this effect, which is a result of a complex interaction between many modes. And in fact, there were two sort of alternative interpretations that I will discuss. That is, can we describe it as a sort of Bose-Einstein type of condensation of the beam into the fundamental mode, or does it represent a thermalization to thermal equilibrium of the population of the modes? So I will discuss this. And then I will move, in fact, to experimental results, which do confirm the wave thermalization picture. And the way how we could compare theory and experiments is based on what I already introduced, some new holographic method that permits, through a particular setup, to determine, to make a so-called mode decomposition. So we are able, when you see the beam at the output of the fiber, you see just a spot on the camera intensity profile. Well, what we want to do is to recover actually the population of modes. So in some sense, we want to be able to recover only phase information, not only intensity information. So you need to do some interference experiment. That's why we call it holographic. Interference with, in order to do the projection of the image into the basis composed by the modes of the fiber, and to recover the population of each mode, essentially, and see, in fact, if the mode distribute the population of the modes that you get at very high power, does it correspond with the thermal equilibrium condition? And we have not only done that, but we have also verified that there are some conservation laws that must be satisfied by the wave propagation, in analogy with the conservations or laws that occur in thermodynamics. And in particular, one of the conservations that beams in fibers must satisfy is the conservation of the orbital angular momentum. So the last more advanced set of experiments have also confirmed this conservation, and not only that, also this additional condition on the conservation of the orbital angular momentum will also change the final population of the modes, and we have confirmed this statement, and then I will conclude. So, what is spatial beam cleaning? Well, I will just add my pointer here. So it consists of, as I mentioned, a change of the multimode beam from speckles into a bell shape. So this is what the original observation, what is shown here, and the first papers that were published about 6 years ago on PRL and Nature Photonics. As you can see, at low powers you get a dirty image composed by the phase dependence or the interference of the mode population, because you excite many modes. So in the transverse cross section you get a noisy pattern, and then as the nonlinearity grows larger, you get a central spot, very clean, surrounded by a background. So this, and then keeping increasing the power, so this can be cleaner and cleaner, so the background reduces. And the central spot is pretty close to the size of the fundamental mode. So there is a clear redistribution of energy among the modes, among the population of modes, in favor of the fundamental mode. But as you can see, there is not just the fundamental mode, there is, in fact, also some population in the higher order mode. So it's really convergence, and I would say not into the fundamental mode only, but into a new distribution of population among the modes. So it was demonstrated in this special graded index multimode fibers, and there is a peak power threshold. So this happens as a certain peak power is overcome. And so what is the effect that is there, the nonlinear effect that is responsible for this effect, for this surprising observation, is the Kerr effect, that is the fact that the refractive index of the fiber has a contribution which is proportional to the intensity or local power in the fiber. And that when you consider that and then you expand the field into many modes, then this leads to modal four-way mixing. So essentially to the transfer of energy between different modes, which is the mechanism for this redistribution. Now, it seems it's easy to say in words, but it's very complex because you may have thousands of this modal four-way mixing. This fiber supports up to 200 modes. And then this means if you take all the the cross products between the modes, you develop to the cube the field, you see that you have many thousands of interaction terms. So it's clearly a complex effect, results from complexity of the nonlinear interactions in the modes. And so it is interesting for applications. Why? Well, because you have a multi-mode fiber, which has many advantages. Essentially, it's much bigger than a single mode fiber, so it has a higher damage threshold. You can couple much more power, much more energy, but still the beam, you see, has a high beam quality, so maintains the nice property of single mode fiber. So sort of, in this way, you can combine the best of both worlds, so the nice beam quality of single mode fibers with a high damage threshold of multi-mode fibers. So that's why there is an applicative interest in this effect. And it has been observed in different propagation regimes, both in the normal or anomalous dispersion, and with pulses ranging from nanoseconds to femtoseconds, and also in different types of fibers, ranging from active fibers with gain, tapered, that is changing in shape along the distance, and also in few mode step index fibers. So there is this is just a summary of many papers where by different groups after our first observation in collaboration with the University of Limoges, well, many groups in the US, in Russia, and in Europe have observed this effect. And about the applications, for example, you can use it for multi-mode fiber lasers. That is, this is a scheme of an experiment carried out in Lausanne at EPFL. And based on this effect, basically you can obtain a nice clean pulse at the output of a multi-mode fiber laser. Again, is a self-cleaning in the special cleaning occurring in a graded index multi-mode fiber in the laser that gives rise, transforms the dirty beam into a clean one. And this effect has also applications for biomedical imaging, because high resolution biomedical imaging based on nonlinear fluorescence excited by two-photon absorption in two-photon absorption microscopes. So there is really a large set of applications. Now, in terms of contrasting theoretical descriptions of this effect, well, as you can see, there are many papers coming up, and the interpretation of this effect goes from parallels with hydrodynamic two-dimensional turbulence that leads to inverse and direct cascades of the mode populations towards both higher order modes and the fundamental mode, and also a condensation of light waves in analogy with, because in fact the governing equation is the Gross-Pitayevsky equation, which rules Bose-Einstein condensation. So there is a parallel with that. And then thermalization. So there is a paper coming out from Creole, from Christodoulidis and co-workers a few years ago, that has also developed a thermodynamic theory of a highly multimodal nonlinear optical systems. So it applies not only to optical fibers, but to coupled arrays of waveguides and so on, which may essentially, the end result is that you can make a parallel between thermodynamics of conventional thermodynamics of particles, of a large number of particles interacting through collisions, with highly multimode wave systems where the interaction occurs through the nonlinearity, which exchanges energy between the modes in analogy with collisions which exchange energy between particles. And then there has been a recent paper by this group, which is also similar to what we have done, has performed with a different method, a direct observation of this thermalization. The final thermal distribution is a Rayleigh-Jeans distribution. So just a simple diagram to outline the two views, contrasting views, thermalizations versus condensation. So you can just say, well, the sort of a simple way to see the effect in a 2D phase diagram plane. And what are the coordinates in the phase diagram? So one is on the vertical dimensions, you have the number of particles, which is proportional to the number, the total laser power. So that is the number of total number of photons in the system. And then there is another variable which is on the horizontal, which is the initial energy, or Hamiltonian, the energy of the system, which is related to the initial coupling conditions into the fiber. So there are two, and essentially there are two ways to obtain a clean beam. So this region here corresponds to when you have a low number of particles or low energy, or actually high energy, because the energy starts from 0 here. So when you are in this region, you have dirty beams, and then you can make a clean beam in two ways. So either keeping the laser power constant or number of particles constant, so you go on the horizontal and you change the energy. So you change the coupling conditions. That is essentially changes the temperature of your system. We didn't introduce temperature yet. But what happens is the so-called condensation, which means that the population is essentially only in the fundamental mode, and then there is almost uniform equipartition of energy among all the higher order modes. So that happens when you cross this solid line. You can do typically the experiment is done in a different way. So that corresponds to one experiment that was actually done in France, in Dijon. But then the typical way, as that I described before in practice, is actually to keep the coupling, the energy constant. So the coupling conditions are fixed, but you just increase the number of particles or power. And if you do that, you go on the vertical and you get a thermalization that is a clean beam, which actually corresponds not to just the fundamental mode, as in this case, but to a full distribution. You see that there is also higher order modes have an important contribution here. So there is a background of higher order modes. So you see also that the beam is slightly larger here. So there are two ways essentially to get a clean beam, depending on your experimental setup, essentially conditions, depending on the route you follow to achieve it. And I will describe here in this talk the classic, the practical approach, which is in fact the thermalization approach, it can be described in terms of traditional statistical mechanics, and you can see here that essentially, you can represent the fiber as a container as a box which contains many modes, and of course, if you want to calculate, there are many ways you can have, for example, in a particular two photons in mode in the fundamental mode, which are the black dots here. So for the particular state of the system, which has two photons in the fundamental mode, there are many ways to achieve it, and you can compute all the number of ways you can achieve this particular condition of two photons in the fundamental modes. There are many microscopic states that give the same result. You can compute the Boltzmann entropy and then maximize it, taking into account again the conservation laws, which are the conservation of number of particles, which is the conservation of power, because the fiber is lossless, and then a conservation of the Hamiltonian or internal energy. And so if you just apply, let's say, without knowing how to do it, let's say in a way, you just empirically, you impose the equation of state, which holds among these macroscopic quantities from thermodynamics, well, you get a Rayleigh-Gibbs distribution, where Ni is the population of mode I, Gi is the degeneracy of this mode, and alpha and beta are two constants to be determined by fitting, essentially, but we can derive them from first principles. And epsilon I is just essentially the phase shift, the propagation constant of that mode. So as you see that there is a distribution which is very simple that corresponds to the thermal equilibrium condition. So now coming to the case of graded index fibers. So let's see what these modes actually, how do they look like? So for a fiber with a parabolic index profile, so that is you see the index profile follows a parabola, and then you can expand the field in the linear case into Laguerre-Gauss mode base, where you have two indices. In fact, so one is the quantum number, and the other the azimuthal index, which can be, so the quantum number is related to L and M. L is the radial index and M is the azimuthal index. So that's how the two indices that describe the Laguerre-Gauss base. And so Q is related to L and M by this relation. So this picture, you see how for different Qs and different M, how the modes look like. So the fundamental mode is just is just one. So the degeneracy is one, and it's just the Gaussian as a Gaussian shape. And then you have different orientations depending on the azimuthal index for the higher order modes and different degeneracies. So that is how the intensity pattern, how it looks like. So now when we want to apply wave thermalization to this system, again, you conserve the Hamiltonian and the number of particles, and you can apply, based on the Gibbs theorem of the ensemble equivalence, you can apply the grand canonical ensemble approach, which is much simpler than a microcanonical. It's very would be very complicated to actually describe it. And so we, in the frame of this approach, we can use the well-known partition function Z, which enable, what is the advantage of this function? You see, it's just defined by n, by the conserved quantities, the total number of particles, and the Hamiltonian, the conserved quantities here. And n, the small n, is the population of mode with index L and M, the particular mode in the basis. So we can obtain, by using a standard approach, the average number of particles in mode L and M by using the partition functions, so by averaging n Lm here. And if you do this, well, you obtain directly the Rayleigh-Jeans distribution, okay, which is here outlined in this box, where K, L, and M is again is what I called epsilon before, is related to the momentum, so the propagation constants, the phase velocity of the different modes of the mode L and M, and then there is a parameter T which plays the role of temperature. And beta is also can be defined as 1 over the Boltzmann constant times T, the temperature T. So this standard statistical mechanics approach again permits to derive the Rayleigh-Jeans distribution. And in fact, how these propagation constants, this P, are distributed, you see they are equally spaced. So that is, this picture shows for different quantum numbers, the values of K. You see they are there is a group of modes with a certain degeneracy, and all these modes have the same propagation constant K. So as Q grows larger, for the same quantum number, you have many of these modes with the same propagation constant. This leads, it's interesting as a side comment, that leads to the so-called spatial self-imaging effect, because again, you superimpose modes which are whose frequencies are equally spaced, so you get clearly in frequency space, so spatial frequencies, I mean, which means that you get a periodic evolution of the beam in space. And in fact, this can be revealed from fluorescence that is generated at points where the intensity is very high, because the beam compresses periodically. So when it's compressed spatially, the intensity becomes high, and that we can demonstrate that this leads to some fluorescence. So it's just a way to visualize the periodic evolution of the beam. And if you have a step index fiber that is not then you don't have, so where the index profile is like a staircase, you don't have this periodic spacing of the modes, and so you don't have this periodic evolution. You just have fluorescence when you have a sort of self-focusing initially, and that's it. Then the beam spreads out, so there's not enough power intensity to generate fluorescence. So how this Rayleigh Jeans distribution looks like? So it is a symmetric with respect to m equals 0, to the azimuthal number. So that is, you see that in fact, for this particular set of conserved quantities, clearly the population of the fundamental mode is dominating. And then you have all this smaller number of photons on average in the higher order modes, first of all in the mode with quantum number 1, and then decreasing and in a symmetric way around the fundamental with respect to the m equals 0, so the azimuthal number m equals 0. And now it is comes the point of comparing experiments with theory. And so this has been achieved by this holographic mode decomposition method developed in Novosibirsk, and again that we transferred, we implemented in Rome. And so I will. So these are some references, some papers that describe. So initially it was published in Laser Physics Letters about more than a year ago. That is a full description of how this method works. But essentially it involves, as you can see here, interfering the beam from the fiber with a spatial light modulator, a phase-only spatial light modulator, and then which produces, impress in this spatial light modulator the pattern of each mode. So it's a method that is a serial method. So you have to essentially write by some computer driving, write a special phase pattern on this spatial light modulator corresponding to each mode, and then you interfere it with the beam, and then you do this free propagation on the camera where you measure the intensity of this interference. And by this, if you optimize the method well, then one after one, you retrieve the occupation of each mode. So it's a serial method. So you have to scan all the modes on the, essentially, to write a particular pattern on the SLM for each mode, and mode after mode, you get the mode occupations. So that's how it works, this mode decomposition algorithm. You have the transverse beam profile, which is a superposition, that is a field. So complex field is given by the superposition of all the modes with particular coefficients. So how can we retrieve these coefficients of the LG modes? Well, magically, what you have here on the camera, the intensity is the intensity produced by the field that comes out from the fiber multiplied by a certain transmission function. And the transmission function is imposed by free propagation over this distance combined with SLM phase encoding, a particular phase pattern that you encode on the SLM. And what you want to retrieve are the Fourier coefficients, that is the projection of the beam on each of the modes. Okay, and then this leads to mode occupancy. Well, you can do that if you are smart enough that the resulting transmission of your SLM plus free propagation is exactly equal to the conjugate of the mode pattern, right? So if you do that, if you substitute to T psi conjugate in this expression, then you are and then you set and you measure this at the center of the image. So because Kx and Ky represent free space propagation, the spatial frequencies. So at the center of the image, so for 0 spatial frequency, this term is equal to 1, and then you get exactly what you want. You get you get the mode occupancy. Okay, so the value of the image at the center of the beam magically measures directly the mode occupancy. So you just take the intensity of that pixel, and for each mode you measure its occupation. And so that is the experimental result that shows, in fact, that there is a power flow. By using this method, we verified that there is a power flow towards the fundamental mode as the input power grows larger. So you see here the power is increased of the beam, and that is how the occupation of the different modes goes with power. So for the different, you see that at low powers you have a low population on the fundamental mode and quite chaotic distribution of energy among the modes. But as the power increases, you see that the more energy in the fundamental keeps increasing, And then there is the only, essentially there is a population in the first higher order mode, and then that decreases substantially. So there is a strong power-induced redistribution of photons among all the modes. And here in this figure, we show for different Q values, so for the fundamental mode and for higher order modes, how their population, the power fraction evolves with power. So you see essentially that there is a monotonic increase of power, so power flow into the fundamental mode, which is actually has some shoulder. So it is not fully monotonic, so for some power decreases, but eventually keeps increasing. So at the end, you see that you have at very high powers some most of the energy in the fundamental, as one would expect, but also energy in higher order modes. And it's interesting because it's a pure spatial effect. It occurs regardless of the pulse duration. Same result is obtained going from nanoseconds to femtoseconds. So it's quite interesting that the time domain essentially can be neglected. And in fact, we confirm that not only that there is a transfer of power into the fundamental mode, but actually that the Rayleigh-Jeans distribution that is predicted by the thermalization theory, by statistical mechanics, is actually approached. So here we show as a function of power the error, the root mean square error with respect to the final distribution. You see that it decreases, and this is actually the experimental result that shows that. So that is the different histograms for the mode population for the different quantum numbers as a function of power. So going from very low power, 0.11 kilowatts, so in the low power regime. And what we show here is to the left is the image. You see speckles. And then to the right is the reconstructed image. So the image that is obtained after computing the mode population from this algorithm and then superimposing all the modes that have been found, because the method enables not only to retrieve the intensity of the mode coefficient, but also the phase of the mode distribution. Because we have the phase, I didn't mention that before to simplify the discussion, but in fact we have also the phase information, which means that we can reconstruct the field and compare reconstruction with the actual image to that testifies that the reconstruction is high fidelity, so that the method is accurate. So that's very important. So you can see that the reconstructions and the original images are always good. And then so that is a check, important safety, sanity check. But then the second thing is that, again, we can see that the distribution, the mode distribution evolves and eventually really tends at very high powers to the Rayleigh-Jeans distribution, which is the one given by the red dashed line. So you see the Rayleigh-Jeans distribution doesn't hold at low powers, but when power is increased, you reach thermalization, and in fact, you have a very good, I mean, the mode power distribution really follows the Rayleigh-Jeans distribution, which means that the thermalization has been achieved. And in fact, in order to compute the Rayleigh-Jeans distribution, you have to compute the two values, also the temperature and the chemical potential, which can be computed by the equation of state. So there is once you know H and N, the energy and the total number of particles, then there is a way to compute the mu and T, and those remain the same irrespective of the power. So you can compute them even at low power conditions. You can compute them and then use them for deriving the Rayleigh-Jeans distribution. This is a red curve. Okay. So that is another validation, because we compute these fitting parameters, I would say, at this point, not from the final distribution, but from the initial one, and they remain the same for all powers. Now coming to, also we have, of course, not only verified the goodness of the reconstruction, but also the conservation laws, which must be satisfied. That is the number of particles and the internal energy, the Hamiltonian, and also the orbital angular momentum. So these are, for example, for different pulse durations, you can see that both in this case, there is no orbital angular momentum, so the parity should be 0. and it is conserved at all powers, but also the Hamiltonian is well conserved in all cases, irrespective of the pulse duration. So going from 10 picoseconds to 170 femtoseconds, so changed by 2 orders of magnitude, and the Hamiltonian is always conserved. So that is at all powers. So that is an important check. And also, well, there is some detail that I would say that this Rayleigh-Jeans distribution is actually, when you consider the two indices, the M and L, the radial and azimuthal index, is actually, we can say that there is, because again, the distribution you see is two-dimensional. There are two indices involved, so it is obtained as a sequence of sub-distributions. So that is, we'll say in details, so that is the distribution that is obtained for every L, every radial number, for the different azimuthal numbers. So you see that there is actually a sub-distribution, Rayleigh-Jeans distribution. So that is the general Rayleigh-Jeans distribution. And then let's say we do a check with a much finer detail. So there is a good agreement even when you change the two indices between theory and experiments. So the black bars are obtained from the experiment and the red curve from the theory. So that is even more accurate confirmation of the theory. And okay, so that is again, now what we want to do now is to extend the theory that I described before by taking into account the presence of an orbital angular momentum, which is an additional quantity that is conserved. So at the moment what was conserved, but it was equal to 0. So it's a sort of trivial conservation. Now we want to apply the same statistical theory and in particular compute based on the maximization of the entropy of the wave system by conserving the number of particles, the linear momentum, but also the angular momentum of the beam. And these three conservations, so there is an extra conservation law, which is, and all of them are taken into account by maximizing the entropy by taking into account of the constraints of the conservation laws by adding 3 Lagrange multipliers. So alpha, beta, and gamma. So alpha, beta, we had them already, and they were the 2 parameters of the Rayleigh-Jeans distribution. So the essential information here that when we introduce the angular momentum conservation, we have an additional constraint. So we have an additional parameter to be Lagrange multiplier, essentially, which means that the distribution now will be more complicated. It will be generalized Rayleigh-Jeans containing 3 parameters. And that is the final result, essentially. So that is the equilibrium distribution for the population of the modes, the number of photons in each mode, which contains 3 parameters, alpha, beta, and gamma, where P con I is as we had before, the linear momentum of corresponding to each particular quantum number, and M con I is the angular momentum of that quantum number. So you see, you have 2 additional quantities and 3 parameters that describe this distribution, which is derived under the approximation that the number of photons is very large in each mode, much larger than the degeneracy of that mode, and much larger than 1, essentially. And so, well, just going quickly through some steps by using the Laguerre, that is general, that is valid in general. So for the Laguerre-Gauss mode base for green fibers, well, we can express this distribution. So these alpha, beta, and gamma coefficients, we can derive explicit expressions for them, and which are only determined by the temperature, the chemical potential, L and M, the two indices of LG modes, and the angular momentum, which is conserved. So that is the final. This is a generic generalized Rayleigh-Jeans, and that is the one applied to graded index fibers. And what is the main physical consequence the presence of an orbital angular momentum which is not zero, well, is a symmetry breaking, as intuitively one would expect, of the distribution. That is, the distribution is not anymore symmetric with respect to the azimuthal index, but essentially it is asymmetric. So in this case, positive azimuthal index modes are more populated than the ones with the negative m. And there is also independently a theoretical paper taken by, again, the Christodoulidis group that recently appeared on PRL, where they have derived this generalized, they have also derived by different methods this generalized Rayleigh-Jeans distribution. How now in practice, then we did experiments again to confirm, and then I will conclude, confirm the thermalization of waves or beams with orbital angular momentum. And a simple way to generate an OAM beam in a fiber is by special coupling condition of the beam. So the beam must be injected with some offset from the center of the fiber and with some angle, spatial transverse offset, y0, and also some angle. And this leads to some helical trajectory, helical path for the beam along inside the core, and which again we can derive the average value of m of the angular momentum corresponding to this helical beam. And we have also done numerical simulations and to predict the mode distribution in the presence of angular momentum, and experiments. And so I will just move to the experimental confirmation. And once again, you see that by increasing the power, we get a redistribution. Now the mode groups, you see that they are now, there are for each G, there are so you see that I have two bars corresponding to negative and positive m values. So because of, just to show the asymmetry of the distribution. So I have split the red bar into two, for positive and negative m. And as you can see, you see initially, well, there is some distribution with not so much population of the fundamental mode, but then eventually the distribution tends to the theoretical one, which is given by the blue dots. So there is a good asymmetry. There is not only convergence, but also confirmation of the final asymmetry. And it's interesting to see that in this case, even though the fundamental mode is the most populated, the beam, the thermalized beam, still has some speckles, because there is some asymmetry and significant population of higher order modes. So I would say that in this case, you get these results prove that there is a thermalization, but without a clear cleaning of the beam, as it was in the symmetric case when you had no orbital angular momentum. So by just looking at these pictures, you would not be able to say, well, the beam is thermalized, but you need the mode decomposition to confirm actual thermalization. And so you see that the error progressively decreases as the power is increased, the error with respect to the generalized Rayleigh-Jeans distribution, and also both the energy and the moment, average momentum, average quantum number and average momentum are conserved. M is conserved as it should be. So we also proved conservation of the angular momentum. So I will conclude by saying that we have validated the description of spatial beam self-cleaning of this complex effect as a thermalization phenomenon. And we have highlighted the difference with respect to the condensation description that comes back to the initial plot that I have shown. And we have described this thermalization in the usual framework of the statistical mechanics. And we carried out an experimental demonstration by means of this holographic mode decomposition technique, which actually permits to validate the approach. And in particular, to confirm that the equilibrium distribution is given by Rayleigh-Jeans law. We have verified the conservation law, laws, and also this is a pure spatial effect because it's verified independently on the pulse duration. And we have generalized the approach to beams carrying orbital angular momentum. So, well, that is everything here what I described today. Of course, all of this is really just the first step, I would say, in this approach, because it permits to validate this thermodynamic description of, which is based on a few conserved quantities, like you know, it happens in describing usual thermodynamics of gases, but then everything else still has to be done because this is just a validation. But then the advantage will be to use this description in order to predict, for example, what happens when you have you know, many beams interacting. So, for example, when you put two different gases together, what is the final temperature? So there are many answers that can be given by this approach in a very simple way, based on this again, on the conservation laws and laws of thermodynamics, in the similar way that we can predict the state of a complex system based on global variables and not microscopic variables. So I think that is a very promising approach to study multi-mode systems. Well, not only in optics, but of course also in plasmas, in many other contexts. So I thank you for your kind attention, and thank our sponsors for this work. Thank you very much.
Okay, thank you very much. Are there any questions or remarks? Do you have a question?
Okay, thanks very much for the talk, Stefano. I'm interested in the statistical mechanical framework that you developed. So, but because I obviously don't work in this area, so my question is about those temperatures that you had.
Mm-hmm.
So, if I understood correctly, you started with a microcanonical ensemble. Yeah?
Yes.
And then you moved to the grand canonical, and then you had some sort of E.T. Jane style statistical mechanics with Lagrange multipliers. Mm-hmm. So, is there a way to understand these temperatures which appear? Are they some just intensive parameters that you need?
Well, yeah, the temperature can be computed from essentially from the equation of state. So there is a standard ways to compute the chemical potential and the temperature. But of course, the temperature has only a meaning. We can compute it also for, as I said, for any beam power or number of particles. But then it has only a meaning when the state has at very high powers, when thermalization has occurred. Because so in a situation when you have, because otherwise at low powers you don't have, temperature is has a meaning once you have thermalized, otherwise it's meaningless, as it occurs for a gas. Until equilibrium is not reached.
Okay, so as long as you have some equilibrium state, it makes sense, yeah? As soon as you move away from the equilibrium, mm-hmm. it starts becoming just some parameter, yeah?
Yes.
Okay, thank you.
So that's why it's interesting, because again, that's something we are working on now, is to combine different beams with different temperatures, and then predict. Let's say we combine two beams with different temperatures, T1 and T2, and in general, what is the final distribution? It's a very complex task. You need. But then you need, even numerically, it takes days to simulate thousands of modes. But then if the two beams have equal power and different temperatures, then you would expect that the final temperature at equilibrium is the average between the two. And that is something we have confirmed. So it's very powerful. You don't need to do any simulation. But you can predict the results based on a simple let's say, everyday situations. You put two liquids at different temperature, you mix them, or two gases at different temperatures, and then you let them evolve, and then what is the final temperature? Well, you can answer without, just even a boy can answer, I would say. You reach the average of the two.
Okay, so experimentally you see the laws of thermodynamics, yeah?
Yes, yes,
for
right.
this.
We are very validating the laws of
Okay,
thermodynamics.
that's brilliant. Thank you.
Any more questions or remarks? Okay, no questions from the audience, maybe from the online participants. Okay, in which case, let's thank the speaker again. Thanks very much, Stefan. So we continue at 11:20 Moscow time.
Thank you, bye-bye.
Okay, Andy, can you hear me from this microphone then?
Yeah, I can hear you fine.
Okay,
Yeah.
so it's my pleasure to introduce the next plenary speaker for today. So it's Andy Hohn from University of Kent in the UK, and he will be talking about continued fractions and hyperelliptic curves. So Andy, you can start whenever you're ready.
Okay, great. Thanks very much, Satiris. So it's a pleasure to be here and to talk to you all. Okay, so what I'm going to tell you about today is some work that I started off doing on my own a few years ago, and then recently I've sort of continued the project with John Roberts in Sydney and Paul van Hacke in Poitiers. And my original motivation was coming from some results in number theory about integer sequences, which came from some work by van der Poorten. So what he did was he constructed some SOMOS sequences or SOMOS recurrences, which are certain integer sequences from continued fractions. So SOMOS recurrences from so basically from continued fractions, I would say elliptic continued fractions. So continued fractions related to an elliptic curve. And then also there were some other results more from a kind of direction of combinatorics. So people working in combinatorics. So it was originally 3 Chinese people, Xin, and then later also Chang and Hu from Beijing, and then actually all 3 of them they ended up working together, and what they found was some Hankel determinant formulae for SOMOS 4. So let me just sort of show you what I mean to give you the motivation. So the original SOMOS 4 is this recurrence relation. Oops, let me rub that one out. Okay, so it's a 4th order quadratic recurrence relation. And it has many amazing properties. So it actually arises in cluster algebras. It has the Laurent property, but in particular, as a result of the Laurent property, that it generates Laurent polynomials in the 4 initial values. If you take the 4 initial values to be 1, then that means that you get a sequence of integers. So the integer sequence looks like this. Okay, I'll write down just a few terms and then. Okay, and then what Xin et al. Found is that this sequence of integers, you can write it as you can, okay, with some choice of initial, slightly changing the labeling of the indices. What you do is you sorry, I'm hearing myself in echo. What you do is you consider this quadratic equation for eta, so which in particular defines an elliptic curve, and then you expand, well, more or less eta, but actually eta over x minus 1, expand that as a power series, so you get x plus x squared plus 3x cubed plus 8x fourth plus 23x to the fifth, and you can work out a recursion for those numbers as well, if you like, from the quadratic equation. So you write down that power series in x, and then you read off the coefficients. So the coefficients of the power series are 1, 1, 3, 8, 23. And then what you'll find is that, so sorry, I need to start a new page now. Okay, so then what you do is you form a sequence of Hankel determinants from the coefficients of the power series. So D0 has to be 1, and then D1 also is 1, which comes from the first coefficient of the, so that's the first coefficient in the power series, and then D2 is the Hankel determinant formed from the first 3 coefficients, so that's 1, 1, 1, 3, which is equal to 2, and then D3 is equal to, so now we use more of the coefficients in the power series, so 1, 3, 3, and then 8, 8, 23, and you work out that determinant, and that's equal to 3, and so on. So you basically take that power series, form the sequence of Hankel determinants from it, and that will give you this. Okay, so maybe it's not very convincing because I've only showed you 1, 1, 1, 2, 3, but if you carry on, what Chang, Hu, and Shin managed to show is that this power series gives you precisely the terms of this quadratic recurrence relation. So they used kind of combinatorial methods and also lots of determinantal identities to prove this formula, but I was interested in 2 things. So I already had many years ago, I understood this SOMOS sequence in terms of discrete integral systems. So in particular, you can think of it as a reduction of the discrete Hirota bilinear equation, so discrete KP equation, bilinear KP equation, if you like. And so I already had an analytical formula for the initial solution of the initial value problem of the SOMOS 4, which is in terms of the Weierstrass sigma function, or you could write it in terms of Jacobi theta functions instead, if you prefer. But I was trying to understand, first of all, where does this Hankel determinant formulae come from, and then also to understand Van der Porten's work, which was based on continued fractions, as I mentioned, well, Van der Porten did only consider this example of elliptic continued fractions. He was also interested in extending SOMOS sequences to high order quadratic recurrences. So there's like SOMOS 5, 6, 7, and so on. And he had an approach to doing that using essentially hyperelliptic continued fractions. So doing a continued fraction expansion of a function on a hyperelliptic curve, but somehow the formulae in the higher genus, in genus 2 and more, became extremely messy. So he didn't really have a very coherent result at the end of the day. In some special case, he managed to obtain a SOMOS 6 recurrence of a particular form from a continued fraction expansion coming from a sextic curve in genus 2, but he didn't really have a good way to describe the higher genus case. So I kind of started studying his results a bit more closely, and I guess eventually I sort of understood that actually the right way to understand it was in terms of discrete integrable systems or integrable maps. So that's integrability in the Liouville sense, but in the discrete setting of symplectic maps. And that could actually give you very clean and sort of neat formulae for the higher genus analogues of this construction. And also it naturally led to a connection with orthogonal polynomials, and then actually that is what immediately gives you Hankel determinant formulae. So in fact, you don't really need to do a complicated combinatorial construction in the way, or complicated determinantal calculus in order to derive these Hankel formulae. It really comes from quite standard results about orthogonal polynomials. So let me explain. So I'll explain van der Porten's construction and how it goes, and then I'll sort of show you how you can understand it in terms of integrable systems, and then also how you can get Hankel determinant formulae. Okay, so so the idea is you consider a hyperelliptic curve, and I'm including elliptic curves in that. So so you take the genus is going to be G, which is going to be at least 1, and it's given by an even affine model. So y squared equals f of x, and f of x is going to be something of degree 2g plus 2, so a polynomial of degree 2g plus 2 with no repeated roots. So it defines a smooth affine model of this curve, and then okay, it's also convenient to sort of complete the square in this polynomial. So I'll write it as ax squared plus 4 times r of x, where a is going to be a monic polynomial of degree g plus 1, and r is going to be of degree g, so sorry, of degree g minus 1, so we can okay, sorry, of degree g, that's right, yeah, so some coefficient, let's say times x to the g plus dot dot dot. Okay, if we complete the square, we can always write it like this. This is not so important, but it makes some of the computations easier. And then what we consider is a particular rational function, or we could say a meromorphic function on this curve. So so we take a function y naught on, so sorry, I'll call this curve C, curly C. So this is a meromorphic function, and it's got to have a particular form. So it's going to be given by y plus a polynomial in x, which is going to be of degree g plus 1. So this is a monic of degree g plus 1. And then, sorry, I'll call that p0. And then in the denominator, there's another polynomial, which is just degree g. And it doesn't have to be monic. In general, it's not going to be monic. And then what we do, according to van der Porten's construction, is we construct the continued fraction expansion of this function as a power series in x, where you think about x being large. So think of x going to infinity. Now, if you think about this hyperelliptic curve, this model of this hyperelliptic curve has 2 points at infinity. And so what I'm going to do is expand around one of the points at infinity, which means that I'm choosing a particular branch of the square root, if you like, a particular branch when we define y. So the points at infinity are say infinity 1, where y behaves like a of x. This is why I wrote down this formula with a squared plus 4r, why I completed the square. And then the other point at infinity is y looks like minus a of x to leading order, you could say. So that's the and then there's obviously corrections. So we could just say y looks like goes like x to the g plus 1, or y goes like minus x to the g plus 1 at those points. It's the same thing. Okay, so now what we want to do is actually take the a continued well, first of all, you can think about doing a power series expansion of y around infinity, the first point at infinity. And so to leading order, it will just be, if we normalize things correctly, it will just be go like x, at this function y0 will grow like x, and then it will have a constant term, and then a tail, which is all negative powers of x. So we can expand y0 as a power series around infinity, or as x goes to infinity, but we're taking this particular branch. But then also we can use that to define a continued fraction expansion, which is actually a Jacobi continued fraction, or a J fraction. Okay, so let me again get a new slide, and hopefully you can remember what I just wrote, but I'll write it up again. So the point is, what do we want to do? We want to we say that y0 has J fraction expansion around infinity 1, and what does it look like? Well, the point is that if you think about the power series and what we're getting, then you can if you have any power series so that you can think of this as an expansion of you could think of this just in terms of formal series. So I would write this as you can think of this as a Laurent series in x to the minus 1. So what I'm saying is that what I mean is that you can have a finite number of positive powers in your expansion, and then all of the rest is negative powers of x. Okay, so the point is that if you take any function, what you do is you can get a continued fraction expansion, and it looks like exactly the standard form of a continued fraction expansion for a real number. Okay, so you know the algorithm for finding the continued fraction expansion of a real number is that you take the integer part, and then you take you have a remainder, which is if it's non-zero, your remainder is a number between 0 and 1, and then you take the reciprocal of that number, and then again you have a remainder, which is you have an integer part, and then again the remainder is a number between 0 and 1. You keep on taking the integer part and then taking the reciprocal of the remainder, and that's how you generate the continued fraction. So in this ring of power series, even just formally, you can expand any series in exactly the same way, but what you have is that so A naught here will be, let's write it as y naught greater than or equal to 0, so it's the polynomial part of y naught, and then similarly we can write a formula, a recursive formula, so yn is going to be an plus it's plus 1 over yn plus 1, so we get a sequence of functions, so y0, y1, y2, and so on, and at each stage this is the polynomial part, so this is a polynomial in x, and then the remainder is the, if you like, the tail is all the terms of order x to the minus 1, and then we take the reciprocal of that. Now the way that we're gonna, what's special about the particular fraction that we're considering, well, okay, in general, if you take any series like this, then the polynomial part could have any degree, but in this case the recursion is set up in such a way the polynomial part is linear in each case, so the degree of an equals 1 for all n greater than or equal to 0. So this is really sorry, I mean, to be more precise, I said this is a J fraction, but really this is only a J fraction in the case where you have a linear term at each stage. Okay, so each of these A1s, A2, A0, A1, A2, and so on, they are just linear polynomials in X. Okay, well, okay, there's a condition we want actually. So in the first place, to make this thing work, we require that there exists, let's say, q minus 1 of x, such that well, so we started off with this hyperelliptic curve divided by the polynomial f, and then we've picked this function y0 and of a particular form, and what we actually need is that f of x minus p naught squared is divisible by q naught. So that's an an additional condition on the function that we're considering. And then what you find then by induction is that the continued fraction expansion is, as I said, it's a J fraction, so only linear polynomials appear at each stage, and then we get the same relation for all n. So what that actually means is that we can write the function yn that appears in each line of the continued fraction in the form of, so it takes this form y plus pn over qn, where the degrees of pn and qn are the same as the degrees of the initial ones. And also we can write it alternatively in terms of qn minus 1 with the same thing on the bottom. So what you can see, if you think about this a little bit, is that the function yn for each n has poles at the zeros of the g zeros of qn, and at actually infinity 2, the second point at infinity, and also from this the second formula on the right hand side, you can see that it also has g zeros at the zeros of sorry, I said something wrong before. Sorry, the poles are at the poles are at the zeros of qn and at infinity 1. Infinity 1 is where we're expanding as it is a pole, simple pole, and then infinity 2 and the zeros of qn minus 1 are the give you g plus 1 simple zeros of the function yn. Okay, so we have a sequence of functions with the same structure, and that's kind of the point. And now the thing is that you can write a recursion for pn's and qn's, and you actually get a dynamical system for the coefficients of pn and qn, and this dynamics is integrable dynamics. So that's sort of the punchline, in a sense, in terms of the work in terms of understanding the result of van der Poorten. And let me kind of say a little bit more about that, a little bit more detail. First of all, the functions an look like 2 over un x plus vn, let's say. So as I said, they're linear functions of x, and the polynomials pn, well, they look like, you can write them as a of x, where, remember, a is the sort of leading part of the quadratic that defines the hyperelliptic curve. And then, if you like, the first sort of correction is at order g minus 1. And there's a coefficient there, un, that appears in the ans, and that has to be non-zero. Okay, if you hit a 0, then obviously that thing doesn't make sense. But you can eliminate un, and then what you get is the recursion for recursion relations for pn and qn give a difference equation of order of total order 2g for the, well, so let's take the pair dn and vn. Okay, so I don't want to try and describe this too explicitly just now, but let me give you the example of genus 1 to explain what it looks like. Okay, so in genus 1, you can take your curve. You can take the curve to be. Let's so y squared. I'm going to write the curve as y squared is, so it's a quartic curve, x squared plus f plus 4ux plus v. And then, well, exactly how you write the dynamics, there are lots of different ways to write the dynamics, but actually a convenient way is to think of this as a map. So this is in dimension 2, a 2D map, which takes you from a pair, say dn vn minus 1. So I've sort of moved the index back, but just a little bit makes the formulae a bit easier to write down in a short way. And the map is that Vn is minus Vn minus 1 plus u over dn, and dn plus 1 is minus dn minus Vn squared minus f. So there are two parameters in the curve, or sorry, three parameters. There's u, v, and f, and f is I mean, this is not a quartic curve because I'm missing a square here. Okay, so that should be x squared plus f all squared, right? So there's f and u, which appear, those parameters appear in the map, and there's another parameter we'll see in a minute. The first thing to note is that this map is symplectic with just the sort of canonical symplectic form dvn minus 1 wedge ddn is the symplectic form, and it has a conserved quantity which I can write as h equals dn times vn minus 1 squared plus dn plus f minus u vn minus 1. Oh, I'm sorry, that doesn't look good. Let me just rub that out at the bottom. Okay, so that's a polynomial, a cubic polynomial, a degree 3 polynomial in Vn minus 1 and d. You can check, so this map defines Vn in terms of Vn minus 1 and Dn, and then it defines Dn plus 1 in terms of Dn and Vn, so you can think of that overall as a map from Dn Vn minus 1 to Dn plus 1 Vn. Okay, so it's symplectic and it has one conserved quantity, so trivially that's integrable in the Liouville sense. And how does this relate to the curve? Well, basically this quantity h, which I'd call the Hamiltonian, is proportional to u times v. So you can see that the curve there has another parameter v in it. Okay. Now, what else would I like to say about this this map? Well, the idea. So how do we get the Hankel determinants from this? Well, the point is that really what we do is we think of the function. So think of the function g, which is going to be y naught minus a naught, and the continued fraction expansion of that actually looks like okay, there's an initial constant s naught. So I've subtracted off the linear term, and then this looks like, you can rewrite this actually as x plus v1, and then minus d2. So there's a initial choice of sort of normalization. So you can rewrite this fraction and expand it like this. Okay, so this formula is sort of universal. This is true in any genus, actually. It's not, there's nothing special about. Okay, so this is a sort of universal feature of these continued fraction expansions. So this is what I said is a Jacobi continued fraction, or a J fraction. And then also we have we can expand this as a power series in negative powers of x. So hold on, should just be x to the minus j. I'm sorry, I'm not doing very well here. Yeah, so this is just the power series expansion in negative powers when I've subtracted off the linear part. So and now the thing is that from this power series we form the sequence of Hankel determinants. So so this is, if you like, a moment generating function. And if you form these Hankel determinants, so delta naught is 1, delta 1 is S naught, delta 2 is S naught, S1, S1, S2, etc. So if you know what Hankel determinants look like, so delta n is S naught up to Sn minus 1, S1, S2, Sn minus 1, and so on. So there's your Hankel determinants. Then you also can form a kind of bordered Hankel determinant, which is where you take S naught, Sn minus 1, and then you take up to Sn minus 3, Sn minus 1. So you miss out a row basically. Oh, no, sorry, this will be with Sn because we want it to be the right size. So again, of something size n by n. Then you find that these expansion coefficients, so that appear in the J fraction, so the dn's and the vn's are given by a universal formula. So dn is given by this ratio of Hankel determinants, and Vn is given by, and forgive me if I make a sign error. I may have made an overall sign error, but basically something with ratios of these sort of bordered Hankel determinants. And the point is that actually this is just classical stuff, which is, you know, it is oh no, sorry, I've put this should be, I said I was making a sign error. This is minus Vn, so they should be the other way around. But this is classical stuff. This is sort of goes back to Jacobi and Stiltjes, and this is really comes from the theory of orthogonal polynomials. So if we think of that power series that defines these moments, these coefficients Sj polynomial, well, you can think of the this continued fraction that I wrote at the top gives you a sequence of approximations to G, which have the form G. So like for each stage, we can truncate the fraction and we get a ratio of polynomials of degree of, well, Pn is degree n minus 1, and Qn is monic of degree n. And these are actually orthogonal with respect to a natural product, which is just defined by the moments. So let me write down very quickly, because I've only got 5 minutes. All right, let me write down also what the thing is. So the point is that we have these orthogonal polynomials. So let's say Qm is equal to some factor times delta Nm, where, so this is orthogonality, where our inner product is defined by this power series. So what we actually do, if you think about it on the curve, you integrate the function g that we started off with times f times g. So these are all functions. Think of all of these as functions of x, or x is your local parameter at well, x to the minus 1 is your local parameter at infinity, at this point at infinity. So you integrate g times the product of the two, say, polynomials or functions around at a small loop around infinity 1, and that gives you this this inner product. So so then there's, as I said, this is sort of classical theory of orthogonal polynomials, and actually this has been developed by Aptekarev and Nuttall and other people working in approximation theory. If I have actually looked at this case of approximating hyperelliptic functions, and then in number theory also Bombieri and Cohen and Zanier and other people have, as well as Van der Poorten, have looked at this from sort of a different point of view without really maybe knowing each other's work. So there's sort of an interesting overlap actually between people in number theory and people in approximation theory, and maybe integrable systems, who don't are not aware of each other's work. So yeah, so the point is that now you have so if you like, for each genus you have an integrable system, a discrete integrable system, and you have explicit Hankel determinant formulae for the solutions. And yeah, I didn't explain, for example, where the Poisson structure comes from, or the Poisson bracket, but or the symplectic form. But there's a natural way to define a lax pair for this system. Essentially, you have a lax matrix, which is just given by this. It's basically this. For each n, you write down this lax matrix, and then the curve that you start with is the spectral curve for this lax matrix, and you can then also define a Poisson algebra on the coefficients of these lax matrices. So there's a natural way to do that for any g. And the last thing I should mention is also that this is actually connected to the Toda lattice. So if you look at the continued fraction expansion with these coefficients Vn and Dn, then you have, well, so you also have the flows generated by the Hamiltonians, the conserved quantities for this, although it's a discrete system. So if you combine the H1 flow, let's say there's a sort of natural initial Hamiltonian, and if you call the flow variable t, then I've written dot, these are all d by dt, then you get, in fact, the infinite Toda lattice. So if you'll bear with me, because I started a little bit late, I want to actually show you what the solutions of the infinite Toda lattice look like with a little animation. So so basically you simultaneously solve the map, which is a finite dimensional map, but then you iterate it. So you have an index n, and then simultaneously you have a flow, or in fact g flows, which commute with it, and so that gives you, overall, you can prove that gives you a solution of the infinite total lattice. So what I've done here in this animation is, first of all, I've just plotted one of the functions, which is d1 against t. Oh no, I'm sorry, that's not the that's the wrong video. That's not the function. Sorry, go to the bottom where there's the lattice. Yeah. Okay. Sorry. Here's the animation that I wanted. So here's one lattice site, which is d1, and all I'm doing is I'm evolving it in time for a particular solution of the elliptic case, genus 1. So you can see it just goes up and down. It goes up and down on a compact interval. Now here's the lattice points from 0 to 11. Now I've got 11 points from the lattice. So I should say that these dn and vn are actually just Flaschke variables up to a square root. So if we take 11 lattice points, I'm just plotting one of the Flaschke variables, which is dn, then you can see, so what's happening is each of these points is oscillating up and down coherently, just like we saw one point oscillating up and down, because it's a purely periodic motion in this case in genus 1. And now here I've plotted 200 lattice points, so 200 dn's, one of the two Flaschke variables, and now this is what you see for the evolution in time. So it looks rather like a traveling wave because there's a lot of points. Strictly speaking, it's not a traveling wave, but it's a sort of, because it's a discrete problem. But if you like, the continuum limit of this would be a sort of one. I mean, this is like a one-gap solution of the infinite total lattice. So if you like, the continuum limit would really be a traveling wave in t. So that's why it looks rather like a traveling wave. Okay, so I started a little bit late, but I've also gone over time, and I'll try and leave 1 minute for questions if anyone would like to ask me a question. But thanks for listening anyway.
Okay, thank you very much, Sandy, for a very interesting talk. So are there any questions or remarks? Well, from the lecture theater, no questions. Maybe from the online participants. Actually, I want to say that those who are watching on the YouTube, they can only ask a question only via Zoom, just in case. Are there any online questions? Well, okay. I have a small question. So there were quite a lot of non-commutative talks this year.
Oh yes.
So can you say? Well, you have a system that is related to the total lattice. What about the non-commutative version of it?
Yeah.
Because it is related actually to a Young-Baxter map and a tetrahedral map.
I mean, actually, that's something that I'm looking at the moment with Pavlos Kassentakis, who's just visiting me in Kent at the moment. So, I mean, the point is that, in a sense, the way that, so Pavlos is kind of looking at it from Young-Baxter maps point of view, and so he has some candidates for some of these maps, at least in genus 1 so far. We looked in detail, and then. Well, from my point of view, the continued fraction expansion can also be made. It's also possible to make sense of non-commutative continued fractions. So this was done by Differential and Kedem, sort of in the context of trying to define non-commutative cluster algebras, and they have explicit examples which correspond really to linearizable dynamics, which is sort of simpler, but yeah, I believe that it's possible to also do the continued fraction expansion construction in the non-commutative case. The thing that we found with Pavlos, with some of his work with Kalukas before as well, is that the non-commutative systems sort of have extra variables which correspond to the parameters. So sometimes when you have commutative variables,
well, yeah, in most of the cases, I think they even if you consider all your variables to be non-commutative, the parameters almost always have to be commutative.
Yeah, that's right. But what I mean is when you try to write the system, I mean the example that Pavlos has, when you try to write the system, you basically get extra variables, and then let's say some combination of those variables becomes the parameters in the commutative case.
Oh,
so it's like sort of in a sense, like sort of Casimir variables. And actually the construction we're doing with John Roberts and Paul van Hacker, which is sort of which is based on Stiltjes fractions, actually. We looked at it, you know, the way I've presented it today is sort of I had some parameters from the curve which were kind of fixed from the start, but we've been looking at it, say, in a larger phase space to begin with, where, you know, some of the parameters just become from Casimirs, but there are many Poisson structures you can choose, in fact. So I sort of imagine in the non-commutative case it will be something like that as well.
So are the Casimirs invariants?
Yeah, they are invariant.
So do you expect in the non-commutative case to remain invariants without making this Pavlos's favorite centralization assumption?
Yeah, no, that's the problem. I'm not sure, because yeah, he sort of has to make an assumption that things are central elements or something, which
in my examples, actually in the tetrahedron case, you almost always lose half of the invariants. You need to consider some at least some of the elements to be commutative. So
yeah, okay. Well, it would be interesting to look at your examples as well and see how it compares. But probably Pavlos knows it better than me. What he probably knows your.
Yeah, I was mainly referring to Pavlos's and Koulakas's last work on.
Yeah, exactly. Yeah, that's right. Yeah, great. Thanks.
Okay, thank you very much. Any other questions? Okay. In which case, okay, thank you again very much.
Yep. Thank you for the nice. It's a nice meeting. I'm sorry I couldn't join, because we've been having a meeting in Kent for the last 3 days as well. So
yeah, so we hope that next year things will, the whole situation will calm down, and we will have foreign participants as well to visit.
Yeah, I'd very much
here.
like to visit.
Before that, it was the pandemic, so it's always the last 3-4 years. It's for a few reasons we do it in a mixed format. Okay, thanks again very much.
But thanks a lot, Soteris. All right, cheers.
Thank you. Cheers, bye.
Okay. Bye. Okay, I'll stop sharing.
Yes, please. So the next talk is by Leon Takhtajan. Yeah, I can see him online. Hello, Leon, can you hear me? We cannot hear you. You need to switch on your microphone.
Yes, yeah. Can you hear me now?
We can hear you now perfectly, and we can see you all on the big screen. So it's my great pleasure to present the final plenary speaker for today. So it's Leon Takhtajan from Stony Brook University in the USA, and he will be talking about symplectic structure of integrable systems. So Leon, you can start whenever you are ready. Thank you very much.
Yes, thank you very much. Actually, Yaroslavl is a beautiful city, and I like to be there, but it turns out that I'm giving online talk, which I really don't like. And it's in Stony Brook now 5 in the morning, but I'll try my best anyway to give you some reasonable talk. So the structure is, the title of the talk is Symplectic Structure of Integrable Systems, but in fact, that was my original plan. And so actually, I can tell you a little bit about symplectic structure, the most general symplectic structure on a space of all integrable systems, even in 2-dimensional space. and one time in 2 plus 1 was introduced by Krichver and Fong. It's rather abstract. It deals variables are all Lax operators and corresponding formal Bloch functions. Then the symplectic Krichver-Fong symplectic form has this way. It's a residue in terms of quasi-momentum, and then it nicely reduces to the space of one-dimensional integrable systems and reproduces all known symplectic structures. In particular, it reproduces the well-known Gardner-Fadeev-Zakharov symplectic form for the KdV equation and many others. And so this is the general kind of introduction. And then I decided somehow that it would be interesting to talk about KdV equation, although it's so much is known about it, but still there are, let me say that in this talk, I like to discuss a very old thing, the KdV equation on the whole real line in a class of rapidly decreasing functions in a Schwarz class. And this talk turned out to be, I didn't plan it, but it's like a tribute to my co-authors, Vladimir Savelich Buslaev and Lyudmila Fadeev. So, and it will be based, I will explain in a second a motivation for it, but it turns out that it will be based on our old works. And I believe neither Buslaev, nor Fadeev, nor I ever give a talk on this, on our work, on this subject. So it's probably maybe appropriate to give at least one talk on this. So let me very briefly remind you the setup, which everybody knows. So that's the Hamiltonian, that's the Gardner-Poisson bracket introduced by Gardner. Everything is here so well known, it's like from any elementary textbook. That's the KdV equation. Then, of course, it's known that the Gardner bracket, Poisson bracket, is degenerate. The simple functional, just the average of U, is the annulator, Casimir, of the Poisson bracket. So the whole space is foliated by symplectic leaves. And these symplectic leaves these are fine spaces where the annulator is constant. So that's also well known. Then the Gardner-Fadeev-Zakharov symplectic form is given by this nice expression. It's infinite dimensional, but makes perfect sense since we are on a symplectic leaf. Then this antiderivative is well defined. You can and gives you, since variations, differentials of a field have zero average, so you can integrate from x to infinity or from minus infinity to x, you get same. So that's, but of course the Liouville initial data are not canonical variables, and it's very easy to find Darboux coordinates in terms of the field variables. These are like odd part of a potential, and then the integral of the even part, antiderivative of the even part. Then in these are Darboux coordinates for Gardner's Fadeev-Zakharov form omega, and then it has this canonical form dp dq with infinitely many variables. All this is so well known. Then of course there are action angle variables which have this form. So we consider Lax operator for the KdV, which is the one-dimensional Schrödinger operator with potential u of x. Then here 1 over a and b over a are transmission and reflection coefficients for this one-dimensional Schrödinger operator. Then kappa minus kappa square are discrete eigenvalues, and bi are normalization constants for the corresponding eigenfunctions. So these are the action angle variables, and the famous result by Fadeev and Zakharov says, 1971, says that this symplectic form omega is canonical with respect to this action angle variable. So this action variables, these are angle variables, and these are finite dimensional Soliton part, canonically conjugated momenta and coordinates. And Hamiltonian has this form, so everything is very nice. So we can say that the mapping from one set of canonical variables, field variables, px and qx, to spectrum, to scattering data, to canonical variables which correspond to scattering data, is a canonical transformation. So that's the key fact. What it means to be a canonical transformation means it preserves the symplectic form, obviously. But so that's what Fadeev and Zakharov did, and then actually it's kind of interesting. Fadeev in 1971 gave me like a carbon copy of typewritten manuscript of this paper. It was very, and so I was studying it. So unfortunately, I don't have this. This carbon copy is not preserved. Now, but in fact, being a canonical transformation means more. It means that though symplectic forms are preserved under this map, but symplectic forms are two forms, and in many cases they are exact. There are corresponding one forms called Liouville one forms in this case. And then if we write corresponding one form in field variables, like here, and corresponding one form in scattering data, canonical variables, then the difference, or the sum here, note I changed P and Q, is exact. So there exists what is called the generating function, in our case, functional S, which can be expressed in terms of either old variables or the new variables, and so this equation holds. And what's the advantage of having a generating function? It's really a remarkable thing, since if we have a canonical transformation, in symplectic geometry it's called symplectomorphism. It's a map of a manifold on itself, which preserves the symplectic form. So this map is it's n functions, say, of n variables. Or here it's a functional, it's a map, infinitely many functions are mapped to another infinitely many functions. But this map can be described by a single function, which is a generating function. And for instance, if to prove complete integrability, to prove that this map is a canonical transformation, it's enough to find a functional which depends on half of the old variables and half of the new variables, say on P only on momenta in field variables and action and angle or coordinate in new variables, such that another part, Q, is this variational derivative, action is variational derivative of the generating function with respect to phi, and soliton momenta are this just partial derivatives. So if we know that that there is a functional S with these properties, then automatically the map from action variables from field variables to action angle variables is canonical. So there is no need to check to calculate symplectic form in new variables. We need to find a generating function. And that's a very interesting question. Remarkably, it is not addressed. Recently, I was thinking about it for some time, even talked to Vladimir Zakharov like 3 years ago. Now we are working on this problem with Alexander Itz is a work in progress. So I was planning to report on it, but it's still not finished. So instead I will discuss some other things related to the KDV equation. But this, let me emphasize that finding a generating function for integrable systems is an outstanding problem, which outstanding means not solved. Although it's 51 years from the original Fadeev-Zakharov paper, and also another motivation why we are talking about generating functions. This was a powerful method for solving problems in classical mechanics. It goes back to Jacobi, it's Hamilton-Jacobi equation, and finding generating function even for the basic integrable systems like earlier top or earlier Poisson problem is non-trivial. It's non-trivial and rather involved. But if there is a nice interpretation of generating function in natural terms, either in the field variables or in terms of the scattering data variables, this would be extremely interesting. Now, of course, let's do the simple example, elementary example, which is really an exercise in Fourier transform, which makes sense. So let's do it briefly. Consider linear KDV, linear dispersive waves, given by this equation. It's immediately solved by the Fourier transform. These are coefficients, real functions pk and q. They are given by these formulas, where little p and little q are canonically conjugated variables, the same as before. Then in this case, the generating function, or rather function now, depends only on p and capital Q, and in terms of the old variables, it's just their product, p times q, integral from 0 to infinity, where these variables live, or it's by Parseval, it's this product, and you can write it using Fourier transform in a mixed form, what we want, and then it's immediate that capital P is this variational derivative and capital Q is this variational derivative. So this generating function for the KDV is just P times Q, roughly, in either for old variables or for new, or of course this formula is the key.
Yeah, I'm good, thanks. Yeah, just given an online talk. So.
Is there some question?
No, it was just a microphone switch on. So
okay,
sorry about that.
Okay. Okay, so that's kind of the outline. So that's what I was planning to discuss. And there are some interesting things related to this. And of course, so instead of talking about this problem, I will discuss some rather special and things for the KDV equation, which show that KDV symplectic extraction is kind of particular, because you see, we can define integrable systems defined on the whole real line is basically with certain boundary conditions at infinity for the field variables. Roughly, we can define them into two types. One type is when continuous spectrum of the corresponding Lux operator is bounded, say like for Schrödinger operator, it's on a positive half line, k greater or equal than 0, or for the total lattice, or continuous spectrum has a gap, like for nonlinear Schrödinger equation with constant boundary conditions at infinity in the repulsive case when we impose these boundary conditions, or like for the total lattice, or continuous spectrum may fill the whole real line, like say for nonlinear Schrödinger equation, when for attractive case, when we can impose decaying boundary conditions. So, and then in the case when continuous spectrum, absolutely continuous spectrum has a gap or doesn't fill the whole real axis, then the special features I will be describing, they hold. If continuous spectrum fills the whole real line, these features don't exist. In terms of the spectral theory, it means that in the first case, the Lux operator has a virtual level at zero energy or at the boundary of a continuous spectrum. In the other case, there is no virtual level. Say, zero energy is not a virtual level in some sense. Okay, so this kind of puts things in perspective. And so still I will be discussing. So the next part of my talk will consist of two sections. And in the first we'll discuss some very special things about annulator, and in the second I will talk about scattering theory for the KDV equation from a Hamiltonian point of view, and then we'll discuss the generating function which in this case will be the classical S matrix for the scattering of all modes in the KDV theory. So let's continue. So let's consider what is called annulator paradox. This is our old paper with Fadeev, actually. I don't think we ever talk about it. I think the paper is I think is very simple. Look at the annulator. If you compute, it commutes with all the field variables, because this immediately follows from Gardner bracket, right? So we are doing now, so I'm switching from symplectic structure to Poisson structure. So naively, this holds. However, in terms of the action angle variables of a scattering data, we have some paradox. This equation doesn't hold. Namely, we have the trivial trace identity, right? That's Fadeev-Zakharov trace identity in terms of scattering data. The average of the total average of the potential is given by this simple formula. Then, since we believe that this rho and phi are canonically conjugated, sorry, there is another half of the bracket here is missing for strange reason. Then these brackets are canonical, then we easily compute the Poisson bracket Q. Obviously Q commutes with rho and P, but its bracket with phi and Q is non-zero, it's just this. So it's obviously something is strange going on here. It sounds like, looks like a paradox. So in one set of variables, the Poisson bracket is zero. In the other set of variables, it's non-zero. And all this is elementary computation. Nothing deep is going on. So this needs to be explained, right? And at the first glance, resolution is simple. You see, we need to consider, if we say that we consider only those functions of the field variables which have the property that their variational derivatives with respect to ux decay for large x. That's only our admissible functions. Then the bracket is, then Q is not admissible in this sense, since its variational derivative is just one, and it doesn't decay. But still, we can compute bracket Q and U between Q and UX, right? But this is not a serious resolution, because obviously Gardner bracket can be extended to those functionals on the field of the field variables which have finite limits, plus minus x goes to plus minus infinity of this variational derivative. Then you define the bracket by this formula. That's just the Gardner bracket extended to the whole phase space. And then if you extend, consider this larger sorry, not a phase space, we extend the algebra of classical observables. The phase space here, where the Poisson manifold is all coordinates on the Poisson manifold are functions u of x, potentials u of x, which with rapid decay at infinity. But admissible functionals, observables, should have this property. Then this is a Poisson structure. And we'd like to see, then another feature is the following, that the functionals a and b, which we use for constructing the action angle variables, are admissible in this sense. But if you compute variational derivatives of a and b with respect to u, as Monakov and Zakharov did long time ago, then we see that functionals a and b are of this type. Their limits at plus minus infinity are non-zero, they're just values. So in order to compute, so the lesson is very simple lesson, that in order to compute brackets between these functionals a and b, we need to use extended bracket. And then the strange thing happens, that if you do this, you get the following simple formula. That's the classic paper by Zakharov and Monakov, where they reprove complete integrability of KdV and nonlinear Schrödinger equation by computing Poisson brackets. This was actually original approach of Zakharov. Fadeev told him that it's better to compute symplectic structure because it's more, like at that time was thought more mathematical, but now of course they are both at the same footing. So if we consider extended bracket, then this part is Zakharov-Monakov computation, but this is an extra term which comes from the extended Gardner bracket, from the term which include boundary values of the variational derivatives. And as a result, we obtain this simple expression, equal to sign is missing. It equals to this. And then in the limits, if this is in upper half plane, if we take this limit in the correct way, using Sahotsky-Plimel formula and so on, then for the action angle variables, we obtain the following brackets. So that's, of course, the usual delta function, but we have this contribution. Usually, if you consider functionals whose variational derivatives decay at infinity, this is zero, because x times delta x is zero, where delta is a Dirac delta function. But this product only makes sense when the functionals are singular, and our Q is precisely of this type. So if you look how Q looks, it's rho of K over K. That's how. And then if we make this correction, it's just a one dimension, because for all other functionals, this term can be neglected. But then, if you compute the bracket Q with phi using this Poisson bracket, you get zero. And same with Q, as it should be. And so this is a special feature which is manifested itself by the fact that continuous spectrum starts from K equals to zero. So K0 is contributing. So that's very simple thing. But then we'll see, then let's consider another, even more primitive argument. Now, let's discuss another, so to say, paradox, which is the scattering theory paradox. Again, this is another paper with Buslaev and Fadeev. I think we wrote it for Martin Kraskell, 60th birthday. Yeah, I think it should be 60th birthday. But it's written somewhere, or maybe 60th birthday, I guess. Yeah. So this is another very simple story. Consider the two soliton scattering. As we all know, two soliton solution splits at large times into two spatially separated solitons whose velocities are precisely p1 and p2 we discussed, and their coordinates, which q1 plus minus and q2 plus minus, are given by simple formulas. Let's compute their difference. Delta q1 is given by this, and delta q2 is given by this. And now we say that since solitons are spatially separated, then asymptotic momenta and coordinates should be also canonically conjugate variables. Say at minus infinity, we should have this, that p1, p2, q1 minus and q2 minus are canonical variables. If we assume so, then at plus infinity, due to this elementary computation, we see that that the variables, asymptotic variables at plus infinity are not canonical. So soliton scattering is not a canonical transformation, which sounds really ridiculous. And of course, this means, because we are in a scattering theory, we are assuming that there are in states, out states, and the scattering matrix exists and is unitary. So that's what it should be. But here we see that kind of, if we can define in states at time negative infinity, then the out states are no longer canonical. So how could this be? And so it looks like solitons are spatially separated. But in fact, of course, this paradox can be written also for the modes of continuous spectrum. We will discuss it in a moment. But of course, let me say that this is very naive for the following reason, because our symplectic form is not local. It involves antiderivative, or the Gardner bracket is not local. It's not delta function, it's derivative, delta prime. So both of them are so Gardner bracket is not ultra local in some sense, and symplectic form is not local. And therefore spatial separation is not enough. So what is obviously wrong in this paradox? The assumption that asymptotic variables, for instance, for in state, are canonical. Because if they are canonical, then this doesn't make any sense. But so let's discuss. And so in order to check this, we can do the following. It's very easy, and that's what I will discuss, to find true in and out canonical variables for the scattering theory. And this can be done by another computation, which uses the fact that which uses the Liouville theorem, that symplectic form is preserved by the phase flow. So on the solutions of the equations of motion, symplectic form is constant. And therefore, we can substitute into it asymptotics of the KdV equation, large time asymptotics, evaluate symplectic form asymptotically, and setting t to infinity will give us exact solution because the form is preserved under the evolution. And so we use asymptotic, large time asymptotics for the KDV. They first were obtained by Zakharov and Monakov, and then later Mark Ablovitz and Sigur considered some details for the so-called intermediate domain. Zakharov and Monakov obtained very beautiful formulas for the main domains, so to say. So this is the one main domain when sine x equals to the sine t, or more technically it's this condition. Then another domain will be with opposite inequality and negative sign. Then in this domain, solution splits into sorry, this is kind of a trivial domain when KDV solution is a sum, just a sum of solitons, because solitons and waves are separated for the KDV due to the fact that continuous spectrum is bounded. Then this is the sum of n solitons with this asymptotic coordinates. So that's not difficult. This is not difficult. The difficult part is this domain, and also, it is this domain for which Zakharov and Monakov computed asymptotics, and then there is intermediate domain between these two, where Ablovitz and Sigur made a contribution. So these are more complicated, and I'll just write, excuse me, I'll write these formulas, namely, as for large times, we have a main term, which is this 1 over square root of t, absolute value of t, and then there is the next term, which is also important for the computation of the symplectic form, and other terms. So I'm right, like it's asymptotically equal to, but we can write it equals to plus a remainder term, which can be estimated. Because now, of course, asymptotics of integrable systems is well developed by using Riemann problem, by Itz, Deift, Zhu, and many other people. But we are just, for us, at that time, this development didn't happen, and for us, even now, just Zakharov-Monakov formulas are sufficient. So we have this asymptotic. Psi is this characteristic variable equals to 4k squared. This is just from stationary phase. Then the phase phi plus minus is very simple, has this form where rho is canonical action variable from scattering data, and amplitudes are more complicated. They have, well, this is the amplitude, also is a complex amplitude, so it's more absolute values also in terms of scattering data. But then the phase is much more complicated, and the whole thing is a computation of the phase. This is Zakharov-Monakov formula, effectively, written in this form. There is a gamma function, which is kind of characteristic of the fact that the scattering is like a Coulomb potential, because it's 1 over square root of t somehow. And then we have this asymptotic formulas. And then, if you see from these formulas that we have a classical KDV scattering, now it's complete. We have canonical momenta of wave modes and solitons are conserved, and phases are changed, and this is not a canonical transformation. Again, so now let's discuss what is a canonical transformation. And then we do the following simple thing. It's a long computation using the, so we compute, we take a symplectic form, omega, Fadeev, Gardner, Zakharov, symplectic form and compute it and substitute into it Zakharov-Monakov asymptotics and evaluate it at large t. The result, when t goes to infinity, is a symplectic form omega plus, which equals to the symplectic form due to the is Liouville theorem. And after the very long computation, which was in the paper, you get the terms we expect. We expect that naively this would be the only answer. But then you get a lot of cross terms, which depend only on canonical momentum. This is continuous spectrum, this is mixed, and this is discrete spectrum. So we see obviously that asymptotic, that naive scattering theory is not canonical for the KDV because of this extra contribution. So the main computation of that old paper with Buslaev and Fadeev is this, and similar we can compute the symplectic form at t equals negative infinity. It will get this part which comes from asymptotic phases at negative infinity plus the same cross terms, but there is some difference. You see here it's integral from 0 to k, and here it's from k to infinity. They both come with a plus sign. Now these two terms are the same, but they differ by a sign. This is negative, this is plus. These expressions are same, but we are summing over I less than j. Here it's j less than I with the same sign. So this and then looking just at this symplectic forms, it's easy to modify phi plus and q plus to get a canonical variables, and in the same way it's very easy to modify phi minus and q minus to get canonical variables at negative infinity. Namely, so we have a formula for the canonical variables at plus infinity. Sorry, k is missing here. No, it's phi hat plus of k. It's the initial phase. Then we add this term. Then we add this integral, which is reminiscent of a q of the annulator. So this computation is somehow related to the elementary thing about annulator we discussed in the beginning. And then the contribution from solitons. It's pure soliton contribution. Same here again for asymptotic phases at minus infinity in time. Again, k is missing. It should be phi hat minus of k is given by the same formula, which is, and then, sorry, finally, the corresponding coordinates, Soliton coordinates, formulas for them are extremely simple. Of course, you may ask, and this is correct, one should get these formulas in much easier way instead of computing the symplectic form, since you substitute rather complicated expressions into rather complicated symplectic form. And so there should be a better way of understanding this, because all these terms have some structure related to, so it would be desirable, to returning to the main question, to find the canonical transformation from t equals 0, which is this form, to t equals plus infinity, which is this variable. And then this will come for free. Same for minus infinity. Probably one should do the same for solitons. So this, of course, this, what we can solve using these formulas is much easier thing. We can find, in the next slide or so, we can find a canonical transformation from in variables to out variables. But finding, this is easy from these formulas. Finding canonical transformation from t equals 0 to t equals plus infinity is a non-trivial thing. This will give this formula. This refers to the problem Alexander Itz and I were working on. And now, just let's say a few comments on this formula. This formula have kind of nice that, so the claim is that these are true asymptotic coordinates. What's the advantages? Of course, this is just a reminder that the in states and out states are just wave packet and non-interacting solitons, and at t equals negative infinity, solitons are at the left in space, at negative infinity in space. Wave packets are on the right in space. And then in the process of scattering, solitons go through the waves and are arranged in and come in front of the wave packet. And the formulas for modified asymptotic coordinates, they are nice in a sense that they emphasize the causality principle. So, namely, modification of soliton coordinates depends only on solitons situated on the left of a given one, because solitons are arranged on the decreasing order. So kind of only they acquire the change when they go through. Maybe I missed increasing, decreasing, but this is kind of depends only on a half. Same with the modes of a continuous spectrum, only densities, because this reflects what I said, integrals from k to infinity or from 0 to k. So that's causality. I'm not 100% certain whether this is consistent, but anyway. Now finally, let's discuss what is a classical S matrix. Then we have a canonical transfer. We have the scattering transformation from in states at t equals negative infinity, they are canonical variables, to out states at t equals plus infinity. This transformation is now canonical, and it has a generating function, which is classical S matrix. And this generating function has very nice form. It depends only on momenta, as it should be, and I guess it gets this quadratic in momenta, then non-trivial interaction between continuous spectrum and solitons, and pure soliton contribution. And then we have simple relation between in and out states, that out states are in plus this variational derivative, and coordinates are this. Of course, classical S matrix is very useful in describing classical scattering, and of course for quantizing. Semi-classically, quantum S matrix would be exponent of the classical S matrix divided by h bar. So this of course can be done for semi-classical quantization of solitons, but this is the other topic. So now I like to finish to say that these threse simple things we discussed are related. It would be very interesting to understand this scattering, these things with annulator, this scattering matrix for the periodic problem. This I don't know how to, it's much more interesting. Probably one should use Veselov-Novikov brackets and things like that. That is one interesting problem. And as I said, there is the most the problem which interests me most right now is finding the generating function for the canonical for Fadeev-Zakharov canonical transformation. So I think it's already time, although we started a little late, but it's still the last talk, so I think I'll stop here. So thank you. I'll stop.
Okay, thank you very much. So are there any questions or remarks? Okay, from the conference room, no questions. Maybe from the online participants, any questions or remarks?
Leon, hello.
Yes.
Do you hear me?
Yes, yeah, I do.
Okay. So I remember that time Zakharov and the group, tried to compute this classical scattering matrix using perturbation theory, and even use it for the kind of characterization of integrable equations. Can you comment on that? You understand what I mean?
Say it again. You mean this scattering matrix? So what do you mean by scattering matrix?
This what's classical S matrix, what you call classical S matrix.
Yes.
That people try to compute using the perturbation theory.
Yes. But this is, you see, I see what you're saying. I think it's here you need to know large time asymptotics for that, right? And if
right, no, in a sense your formulas are exact, and they had a perturbation, kind of expansion in small amplitudes, things like that.
Right. Yeah, I think this makes sense. I understand. Yeah, but.
And also, could you comment about finite gap solutions? You say that periodic solutions, because in finite gap solutions we don't have asymptotics. They are
right.
Periodic.
This I cannot comment. It's a
say?
question. I think you're absolutely right. I think it's a good question to understand what happens in the finite gap case, or even in the infinite gap case, like when you have the most general periodic potential. This would be very interesting. I only know one result by Capeller and maybe Makarov about annulator for the second bracket for periodic case but it would be very interesting. I cannot say anything meaningful about periodic case except that it's an obvious problem.
Because in periodic case we have a finite number of data.
Right, but I mean, like in this case, you have the general case when there are infinitely many gaps becoming smaller and smaller.
Yeah.
I can make a comment about the finite.
And we cannot hear you very well. I think you should.
Hi, can you hear?
Yeah, that's perfect now.
Yeah. Sorry, I can make a comment about the finite gap case. That some work that we did many years ago with Vadim Kuznetsov, and then also he did more work on the same subject with Paul van Hacker, was about you could say Darboux-Backlund transformations for stationary flows of KdV. So there you can write the you can actually explicitly calculate generating functions for the Darboux transformation as a canonical transformation, if you like, on some dynamical systems in finite dimensions which correspond to the finite gap solutions of KdV. So there are explicit expressions, and essentially you can write each flow. There are the finite number of commuting flows, and you can independent flows, and you can write each of them as a composition of these canonical transformations. So like you can interpolate basically using, if you like, Darboux transformations and so on. So actually in that case that might be a way to get maybe in a sense you can already derive the the generating function that you want in the finite gap case using these results. But,
yeah, probably. Yeah, this is very interesting. Thank you. Yes. Yeah.
yeah,
course.
I can send you some references maybe.
Yeah. Yeah. Thank you.
Okay.
Okay, thank you very much. Thank you very much again, Leon. And thanks twice for having to wake up so early because of the time difference. So, okay. So then we continue at 2 o'clock. So that, yeah, we have it. Okay, so it's one, yeah, so it's one more question from when Shiuma, maybe you can switch on your microphone. Yeah.
Hi, Professor. Anyway, I think I don't know.
You need to speak a little bit louder because you cannot hear you very well.
Can you hear me? Yeah, okay.
A little bit louder, please.
I see. Okay, good. Yeah, I think I have some questions because the KDV, we have diverse solutions, right? Not only the finite gap and Soliton, and we have now even Soliton gas. So I'm thinking, even we have some classical solution, for example, the maximum minimum solution, like the rational solutions as well. So my question is, do you think if we can have canonical transformation or symbolic structure for the Soliton gas or rational solutions? How about this kind of solution? Can we have a symbolic structure for such kind of solutions, or we have some theory?
Say it again. What kind of solutions? What kind of solutions you are saying? We consider this.
Soliton gas. I mean the limit of Soliton, and also rational solution, rational function solutions. Can we have a bunch of the rational function which are maximum minimum solution, right? So
you see here we are considering solutions in a Schwartz class, rapidly decaying. So so only this, all this like Fadeev, Zakharov, all this is rapidly decaying case.
Soliton case is
just fixed number of solitons. It's fine. It's fine.
I mean the limit of the soliton. I mean,
that's different. You are
soliton, right? Let n go to infinity.
This means what you are discussing is a compactification of the phase space. It's a very different problem because you think of this as the phase space is sliced, kind of stratified by number of solitons. It's no solitons, one soliton, two solitons. It's like this infinite dimensional manifold stratified. Then you say that if you consider the limits, it's non-compact. It's hugely non-compact. So what you are saying that you would like to see what happens at the boundary. It's very interesting, but it's kind of difficult here.
Yeah, for sure. Of course, if you have a
it's a boundary. Behavior is kind of compactification of the phase space.
That happened anyway. I think there are a lot of interesting phenomena for the
right. Yeah, but here it doesn't. Yeah, but it doesn't. Yeah.
We have very phenomena. I think very
right. Yeah, but here we are considering on this phase space only.
Right, Schwartz space. Okay, great. Yeah, that's really
only Schwartz space. Fine. Right, exactly. Okay, fine. How to compactify it? It's another interesting problem.
Good. But anyway, the KDV recently we explored for the KDV, even for the rational function solution, they are very interesting. If you use the round scale, we have the linear superposition for the
right, but that's different. You see, we are discussing
different kinds.
That's different, right. So of course there are many of other beautiful things, but that's different here. I cannot comment on this because it's different.
Thanks very much.
Okay, thank you very much. So thanks again, Leon, and see you soon. So we meet again in this conference room at 2 o'clock.
Okay. Yeah. Thank you. Thank you.
Okay, we're ready to start the second session of this day, so it's my pleasure to introduce Professor Habibulin from Institute of Mathematics of the UFA Federal Research Center in UFA, and he will be talking about integrable classification of 3D lattices. The talk will be in Russian, however the slides are in English.
Все включено. Я хочу поблагодарить организаторов за хорошую конференцию. Это удобно, комфортабельно нам. И очень вложен большой труд. Тересу большое спасибо. Так, мой доклад об интегрируемой классификации трехмерных цепочек выполнен в сотрудничестве вот моим соавтором. Ну, тут краткая, она включается. А как красный что проявляет? Рассматриваются такие цепочки. Здесь три независимые переменные. Это n, нижний индекс, g, верхний индекс, и непрерывная переменная x, по которой входит дифференцирование. Вот. Мы говорим об способе классификации вот таких уравнений при помощи дарбу интегрируемых редукций. Значит, в связи с этим мы напоминаем, что такое базис интегралов, интегрируемость по дарбу, и также алгебраические критерии интегрируемости по дарбу. И дальше некоторые ходы, как можно использовать в процессе классификации. Вот, такие системы рассматривались, вот здесь вот перечислены некоторые работы, в которых они исследованы, приведены, где-то около 10 примеров таких уравнений. Среди них есть те, которые получены при помощи преобразования Бэклунда и другими способами. Вот. Наше наблюдение состоит в том, что если цепочку, вот, которая вот в середине, можно смотреть, вот такая она у нас была цепочка, а при g равном единице мы поставили какое-то вот условие обрыва функции f1, которая отличается от основной функции f, и функция fn, конечное вот уравнение, она другая. И вот мы хотим, чтобы полученная система 2 была интегрируема в смысле дарбу. Но она получается дифференциально разностная. То есть есть сдвиг, одно характеристическое направление вдоль n, другое характеристическое направление вдоль x. Вот, она в каком-то смысле аналог обычной гиперболической системы. Вот, примеры показывают, что для любого из уравнений, из того списка, который приведен в предыдущих 3 работах, для них вот выполняется условие того, что система 2 интегрируем по дарбу. Ну, я сразу коротко скажу, что значит интегрируем по дарбу. Система состоит из n большое уравнений, поэтому она допускает n большое уравнение, максимум n большое интегралов по x направлению, n большое интегралов по n направлению. То есть в итоге вот максимально допустимо 2n интегралов. Мы
Напомните, пожалуйста, сколько нужно интегралов для интегрируемости по дарбу?
Вот раз у нас система n-ного порядка, должно быть 2n интегралов. По тому и по другому. Больше и не бывает. Остальные будут функционально выражаться. Независимых будет n в том направлении, n в другом. Так, теперь вот такой же подход мы применяли ранее в наших работах с Попцовой, она же и Кузнецова Мария, при исследовании уравнения цепочки Тоды. Вот это вот когда n одна дискретная и x, y две непрерывные. Вот здесь мы квазилинейные случаи рассматриваем и требуем, чтобы такие же условия существовали. Но здесь уже гиперболическая система обычная, дифференциальная. Вот. И с ней мы провели такую классификацию по этому уравнению, получили, что все известные уравнения туда входят, и еще одно дополнительное нашлось. Вот для первых трех уравнений классической цепочки Тоды наличие этих интегрируемых обрывов, интегрируемых по Дарбу, оно известно более 100 лет. То есть вот если мы подбираем правильно здесь условия обрыва, каждая из этих цепочек, она становится интегрируемой по Дарбу системой гиперболических уравнений. Это давно уже известно, исследовано, но оказалось, что и все остальные тоже допускают такое же свойство, вот, оно, видимо, универсальное. И поэтому мы перешли на случай вот больше дискретных, меньше непрерывных. Вот. Теперь мы поговорим немножко вот о системе вида 4. Здесь немножко она более общая, потому что там была какая-то она разряженная. Здесь вот входит у n вектор с n компонентами, вот ее сдвиг, а здесь покомпонентно производная входит. Вот такую систему. От нее требование к ней, чтобы она была разрешима в обратную сторону. То есть мы здесь по повышению номера, можно и по понижению. Мы требуем, чтобы это было выполнено. Иначе ничего у нас не получится так. И, кроме того, требуется, чтобы функции были локально-аналитическими. Ну, сейчас строгое определение того, что такое интеграл. Система 4, которая вот на той странице была, вот эта система 4. Про нее долго будем говорить, поэтому... Вот что такое интеграл? Это функция, которая может зависеть от xn и от сдвигов. Вперед и назад, вот какое-то количество сдвигов, но считается, что по крайним она однозначно, то есть как бы обязательно зависит, что производная отлична от нуля. И основное свойство, чтобы вот dx от этой функции должно быть 0 в силу системы 4. Если мы сдвинем, поменяем переменные производные в силу системы 4, тогда мы должны получить 0. Но поскольку сдвиг вот возможен по n, то можем считать, что k равно нулю. И если мы возьмем вот много таких интегралов от единицы до n, они будут образовывать полную систему интегралов, если вот определитель отличен от нуля. Так что это вполне проверяемое свойство. Дальше вот переходим к x, интегралу по другому направлению n. Вот теперь это функции уже зависящие от производных будут. От xn, как всегда, и вот у n ее производные и так далее, вплоть до порядка какого-то m. m это вот производная высокого порядка m. Теперь мы требуем, чтобы выполнялось условие dn степени r к i снова i. То есть мы хотим, чтобы для любого r было вот это вот условие dn на r i равно i. Ну, как мы понимаем это равенство? Это означает, что вот если мы применим, ну, r пусть равно единице сначала, мы применим один сдвиг, пересчитаем все, справа будет некоторая функция, зависящая от тех же переменных, что и исходная. То есть, как бы, поскольку у нас не автономные интегралы, то сам способ сопоставления функции вот этим аргументом, он вообще меняется кардинально. И поэтому мы ставим сюда r. Если требовать не автономные, то есть автономные, наоборот, если не зависящие от n, то хватает r равно единице. Вот пример, показывающий, что сюда r надо ставить. Вот у нас цепочка, пример, у которого вот функция i как бы претендует быть интегралом, потому что она зависит от unx, ее один раз сдвинули, она снова зависит от unx. Но если мы второй раз применим, то уже вот появится новая переменная un плюс 1, то есть как бы фактически это не интеграл. И пример показывает, что надо вот это все контролировать, чтобы это было выполнено при всех целых n. Ну и снова наличие, отличие от нуля определителя некоторого гарантирует, что полученный набор интегралов, какой-то вот взятый набор интегралов, у него порядки вот таких порядков, вот мы дифференцируем, строим определитель, и он отличен от нуля. Вот. И определение системы интегрирования по Дарбу, если существует полный набор интегралов по тому и по другому направлению. Теперь, чтобы пользоваться, нужен какой-то хороший критерий интегрируемости. Вот он, мы его хотим вывести. Это алгебраический какой-то критерий эффективный, чтобы интегралы не считать. Ну и не сосчитаешь, когда ничего не известно. Так, теперь мы сказали, что x-интеграл зависит только от сдвигов и x и n. Значит, если мы вычислим производную, пользуясь формулой дифференцирования сложной функции, то у нас тут получится, что фактически интеграл аннулируется таким вот дифференциальным оператором, векторным полем. И мы должны его упростить, пользуясь системой. Вот эти вот производные выражаются через несдвинутые производные. Это мы сделаем. И получим для этих векторных полей вот такие простые выражения. Ну, дальше мы пользуемся нашей системой и упрощаем. Но заметим, что оператор K0, он фактически содержит производную. Вот unx сюда входит, функции f входят и во все сдвиги. То есть получается, что уравнение, которое мы решаем, k0, примененное к g равно нулю, оно переопределенное. Почему? Потому что коэффициенты зависят от переменной unx, в то время от unx производной, в то время как само решение зависит только от сдвигов. Следовательно, к уравнению 9 нужно приписать еще n большое уравнение вида вот xk, это дифференцирование по nx с номером k. Здесь k функции, вот по каждой из них, по производной, каждой из них надо дифференцировать, и это должно быть нулем. То есть фактически мы получаем 9, уравнение 9 и 10, вот столько, вот эти операторы k и x, они должны аннулировать наш g. Но, кроме того, должны аннулировать и всякие кратные коммутаторы. И еще, как бы вот, можно взять линейные комбинации. Но поскольку вот визуально видно, что комбинации не только с константами, но можно умножать на функции, зависящие от динамических переменных. То есть мы приходим к некоторому обобщению понятия алгебры Ли, когда умножение разрешается на функции тоже. То есть как бы такая более общая алгебра. Умножать можно на функции из кольца А большие, функции аналитические функции локально, зависящие от динамических переменных. Такие алгебры называются алгебры Ли-Райнхарта. Они описаны давно. В чем отличие? Вот давайте посмотрим на уровне примера. Пусть у нас есть два дифференциальных оператора, производные по x. Здесь x квадрат, здесь x куб. Если мы возьмем коммутатор двух, то получим x четвертый уже до x. И так далее. Если мы дальше будем коммутировать, степень будет расти, и алгебра Ли над полем констант будет иметь бесконечную размерность. В то время как если мы возьмем алгебру Ли-Райнхарта, то над кольцом функции аналитичных вне точки x равно нулю, то у нас получится, вот, что алгебра одномерна вообще. То есть то бесконечномерно, то одномерно. Да? Поэтому, ну, как бы, если мы будем требовать конечномерность алгебры Ли, то мы возьмем очень узкий класс уравнений. Вот. И вот это как раз подходящий объект алгебры Ли-Рейнхарта. Ее конечномерность гарантирует существование полного набора интегралов. Тогда и только тогда. Эта теорема была доказана Кузнецовой Марией и Анатолием Васильевичем Жибером. Вот в 2021 году опубликована в Уфимском мат-журнале. Анатолия Васильевича, к сожалению, нет с нами уже. Дальше переходим к n-интегралам. Здесь ситуация сложнее. Вот возьмем, здесь вообще, если по направлению x алгебра возникало просто дифференцирование, тут же и порождало характеристическое векторное поле, здесь приходится над этим работать. Значит, мы имеем соотношение сдвиг i равно i, то есть мы имеем вот такое соотношение при r равном единице, но при всех r должно быть. При r равном единице смотрим на него, видим, что появилась слева переменная у n плюс 1. Функция f, она тоже присутствует. Здесь dx(f), она тоже присутствует, она везде присутствует, во всех как бы аргументах, но глобально она от n плюс 1 не зависит. Следовательно, производная от этой сдвинутой функции должна равняться нулю. Ну, мы с этой стороны умножим на d минус 1, и вот этот обкрученный оператор, он у нас и будет характеристическим оператором. То есть вот мы обкрутили d под у n плюс 1g оператором сдвига с двух сторон, и обозначили его уже первые, в знак того, что мы только первые степени взяли. И вот он как раз должен аннулировать наш интеграл. Но поскольку переменных у нас n большое, то все эти вот операторы аннулируют интеграл, но они и есть характеристические операторы. Но это не все характеристические операторы, потому что ну вот мы пока сначала вот запишем в более удобной форме в виде векторного поля. Все это можно раскрыть в виде векторного поля получится. И для простоты обозначим через yg0 просто эту переменную, дифференцирование по этой переменной. И тогда получаем формулу для yg1 здесь вот. Эта формула хороша тем, что она уже для любых k будет иметь такую же форму. Значит, вот мы сдвигаем дальше. Ну, мысленно, если мы скажем, что здесь k равно 2, то мы проверили, что первый сдвиг, но мы при помощи того характеристического оператора гарантируем, что первый сдвиг не повышает, не позволяет появлению новых переменных. Поэтому второй смотрим для y d2n, то надо снова дифференцировать по у n плюс 1, потому что второй-то не появится, а первый может появиться. Ну и так каждый раз мы получаем серию характеристических операторов YGK. Вот. K идет вплоть до бесконечности, мы можем его вести. И кратко мы записываем, что YGK рекуррентно вычисляется через YGK минус 1. То есть рекуррентно мы переходим к следующему векторному полю. Так, дальше вот появляются посторонние, посторонние переменные. Вот мы сдвигаем назад, и получается, что наряду с функциями u, g, n еще и обратные сдвиги будут появляться. То есть, если мы рассматриваем уравнение YG kt и равно нулю, то получается, что векторное поле содержит обратные сдвиги, а решение не содержит их. Поэтому мы должны дополнительно писать вот эти вот x-чертой операторы, которых тоже очень много. Получаем вот фактически вот эта система уравнений. Вот все, что мы можем, это вот эти должны выполняться уравнения. Теперь как здесь определить характеристическую алгебру? берем, ну, фиксируем какое-то g сейчас начну сначала. Значит, мы называем, что система 4 имеет конечномерную характеристическую алгебру по направлению n, здесь опечатка n, если выполняются два условия. Вот для любого g существует s от g, что вот этот набор переменных независим, но следующие уже через них выражаются. То есть цепочка вот этих операторов по k, она k растет не до бесконечности, где-то останавливается первое условие. Значит, каждый оператор выражается вот через эти, получается номер какой-то SG, который от каждого G зависит. И дальше мы говорим, что вот все мы их так построим, у каждого из них есть SG, и дальше мы уже строим алгебру Ли-Рейнхарта, Ln, порожденную YG-катами и XG-катами, которые меняются уже от единицы до k большого. K большой — это максимальный от SG-тых над полем, как бы над кольцом локально-аналитических функций от динамических переменных. Вот если эти два условия выполнены, то мы говорим, что система 4 допускает характеристическую алгебру, конечномерную характеристическую алгебру Ли-Рейнхарта по направлению n. Теорема утверждает, что система 4 допускает конечномерную характеристическую алгебру Ln тогда и только тогда, когда она допускает полный набор характеристических n-интегралов. Вот. И из этой теоремы следует, и из той предыдущей, что система 4 интегрируема в смысле Дарбо тогда и только тогда, когда обе алгебры имеют конечную размерность. Посмотрим вот некий пример, в котором мы немножко посчитали. Мы берем систему достаточно частного вида, потому что производная входит уже отдельно, вот она единичным коэффициентом, линейная, неизвестная функция от 4 переменных. Вот мы ее для удобства уже от минус n до n вот так вот представляем. Первая функция, вот она от 3 переменных зависит, только это, как положено, от 4, а это тоже от 3. Ну, как бы крайние переменные исчезли. Вот. Где fg — это та же самая наша искомая функция, просто она аргумент зависит от g. Оператор d, dx действует на функцию от сдвигов вот по такому правилу. Следовательно, dxh — это у нас сумма xg-тых у nx плюс некоторый хвост y. Получается, что вот хвост имеет такой вид. Это дифференцирование по dn плюс 1, n минус 1, n плюс 2, n минус 2. Дифференцирование по n плюс... Просто у n нету здесь. А иксы это было на предыдущей странице. Иксы это вот сумма таких вот производных. Ну, в силу специфики тут в силу специфики немножко задача упростилась. Иксы теперь уже немножко другие, потому что у nx оно вылетает, и получается мы пользуемся немножко другими образующими. Что мы собираемся делать? Мы предположим, что вот эта вот алгебра Lx с чертой имеет конечную размерность, и попытаемся вывести условия на функцию f. Вот важную роль здесь играет автоморфизм. Если мы векторное поле обкрутим dn, то вот мы снова получим ту же алгебру. То есть иксы вообще не меняются, а y меняются очень вот по простому правилу. Все остается на месте, алгебра остается на месте. То есть это автоморфизм алгебры. Дальше мы строим некую последовательность. Вот берем y, прокоммутировавший с x0 и x F0, прокоммутировавшись уже с предыдущим и так далее, построим последовательность операторов. Поскольку алгебра конечномерна, то получится, что часть из них вот линейно независима вот, до m, а m плюс 1 уже линейно выражается через вот эти m. И автоморфизм на y вновь построенное действует вот по такому правилу. Здесь получаем производные от xg вот, действием оператора xg катые. Вот такие вот формулы. И теперь мы автоморфизм применим ко всему равенству 11, получим еще одно такое же равенство, но уже немножко другое. Мы видим, что ym плюс 1 мы отсюда исключим, и будет равенство, в котором уже линейная комбинация линейно независимых операторов получается. И мы начинаем при них приравнивать коэффициенты. И получаем, что коэффициенты лямбда, они просто константы. Вот. И коэффициенты лямбда, которые у нас были в линейной комбинации, вот эти в линейной комбинации коэффициенты, постоянны. Значит, ym плюс 1 выражается таким простым способом, через постоянный коэффициент. Дальше, при иксах, если мы приравняем, у нас будет три равенства. Дифференциальный оператор pxg, примененный f0, g от минус 1 до единицы, он равен нулю. То есть мы получаем, что функция f является квазимногочленом по отношению к этим трем переменным, а у квазимногочлена коэффициент будет зависеть от разности вот этих двух переменных уже в самой точке g. Но дальнейшая работа уже мы должны смотреть, как между собой взаимодействуют вот эти y уже. Но это такая довольно такая тяжелая работа. Ну и это мы пока еще в начале пути, поэтому полной классификации пока речь не идет. Значит, посмотрим, каковы бывают, например, каковы бывают полиномы. То есть мы получили вот здесь вот полином, какой он бывает на уровне примеров. Вот тут приводятся известные примеры. Вот этот пример, вот для него полином второй степени. Дальше вот следующий полином вообще второй степени, и у него нули, лямбда равны нулю. Следующий пример – это преобразование Бэкленда для цепочки Тоды. Здесь полином третьей степени. Следующий вот тот же самый полином третьей степени. И, наконец, Адлер-Старцев, вот нашли пример. Тут у нас корни 2, минус 1 и 0. Вот такие полиномы. Ну, в принципе, ну, наверное, на этом я и заканчиваю.
Полином зафиксированного полинома, она проще становится?
Да, попроще становится. Ну и похоже, что очень высоко, наверное, то есть вот мы посмотрели, я не сказал, мы посмотрели вот второго порядка полином, и вроде там больше ничего нет. И вот нашли пример новый, который, похоже, является тоже интегрируемым, но это пока еще в процессе. Все.
Хорошо, благодарим. Спасибо. Есть вопросы или замечания? Один вопрос есть.
Есть вопрос? Да, есть.
Ну, ты просто не
Я
слышал
только хотел спросить представление Лакса. Для них есть?
Представление Лакса отсюда сразу не вылезает.
Ну, отдельно.
Отдельно, да, есть они. Есть. Для этого второго нету, а для остальных.
One more question. Еще один вопрос.
Еще один вопрос, если можно, я бы задал.
Сейчас там кто-то вопрос?
Булат.
Не, ну пусть Володя задаст сперва, я потом.
Не, я просто
Да
комментарий.
я обойдусь тоже, я обойдусь.
Комментарий
конечно,
хочу некий сделать. То есть я ничего совершенно по существу плохого сказать не хочу, оригинальное исследование, оригинальный подход и все такое прочее. Но все-таки я бы заметил, что вся эта история начиналась вовсе не с разностных, а с дифференциальных уравнений. И начиналась она лет 150 тому назад с Дарбутом, я не знаю, с ВСО. После этого, опять-таки, в рамках дифференциальных уравнений была работа, там, я не знаю, Лизнова, Шабата, где все это характеристическая алгебра, все такое вводилось. Но в конце концов и мы тоже с Жибером были. А это как-то при изложении все...
Да, я слишком экономил время и там не задержался, но я сказал, что вот в этом случае рассматривали вот этот случай с водами, он рассматривался еще классикой, и эти случаи, они были исследованы.
Нет, случаи-то, конечно, я имею в виду просто подход, все эти объекты, вся эта кухня, она, в общем, на обыкновенных, на уравнениях-то часто водных была.
А вообще, конечно, после этого сделано. Я не говорю, что это дословно.
Но отличие еще, можно сказать, что вот здесь вот характеристические алгебры, они были алгебрами, а дальше уже алгебры Грека. Надо определяться, чтобы...
Что наоборот, что не всегда вот эти самые алгебры Грека или кого-то там, но иногда их удается свести к алгебру. Да. А вообще говоря, не обязательно именно.
Я пропустил, да, здесь множество работ, классификацию Емелова, Шабата, я потом, значит, Леснов, Павелов, Козлов, там тоже были изучены гиперболические системы с точки зрения алгебр, и тогда они пользовались алгеброй. Дальше была классификация скалярных уравнений типа Вилля, которую выполнили Скалов и Жибер, и там получили классификацию. Ну, конечно, вот, стараясь вложиться в срок.
Окей, я понимаю, что есть еще один вопрос по Zoom. Или уже не актуально? Хорошо.
Ну, если времени нет, я просто, мне вообще интересно. В S-интегрируемом случае вот эти ваши алгебры, скажем, для двумеризованной тоды как-то лезут или нет?
Там они бесконечно мерные будут.
А медленный рост, что-нибудь, чем-нибудь выделено или нет?
Ну, рост там помедленнее, медленный рост. Это тоже как бы известный Катца, Муди алгебры там возникают. А с переменными коэффициентами эти алгебры, наверное, в S-интегрированном случае не рассматривались. То есть я не видел таких работ в S-интегрированных.
По какой-то причине очень часто они сведут вот такими вот функциями, но после замены переменных их таки можно свести к алгебре в константах. Вот этот эффект не очень понятен, но это наблюдение такое есть. Было бы желание. Ну, замена переменных, линейное образование, делить на функции, смотришь, оно уже становится постоянным коэффициентом.
Ну, это в случае, когда они... Есть только два случая, когда квадратичные или экспоненциальные. В этих случаях обходятся алгебрами. А так в основном уже сложные уравнения. Но это вряд ли.
Может быть, просто никто не пробует.
Сказать, что не сводится, это слишком сильно для работы удобно пользоваться. Для работы выйти из этой алгебры.
Хорошо, тогда, если нет других вопросов или замечаний, еще раз благодарим, спасибо большое. Да, только одно замечание хотел говорить для микрофонов, то есть мы бегаем с микрофонами, потому что мы хотим, чтобы тут было громко, только людям не слышно онлайн, ничего, без микрофона. Okay, so the next talk is online. Hi, Pavlos.
Hi, Sotiris. It seems that there is a problem with my camera, so I will not try to switch it on.
Okay,
so
that's fine.
But
okay. you can try to share your slides.
Yes, I think this is necessary, isn't it?
Yeah. Okay, that works. So
good.
I'm going to move you to the big screen. So I say this to everyone. So I'll move you to the big screen so everyone sees you in the audience from the other side, so that you don't think that you speak to an empty chair. So okay, let me move you there. Okay, can you hear me from this microphone?
Yes, I can.
Okay, great. So it's a pleasure to introduce the next speaker for today's Pavlos Xenitidis from the Liverpool Hope University, and he will be talking about symmetries of systems of quad difference equations. So Pavlos, you can start whenever you're ready.
Okay, thank you very much, Sotiris, and thank you for this nice conference. Unfortunately, I cannot be there. I cannot blame neither me nor you, but let's now focus on what I want to say today. So my talk today will be on, as the title says, on symmetries and some quad difference equations, on partial difference equations. This is some work that we've done with my student Louis Brady, and that was part of his master's thesis. And we've started last year discussing it. I think I presented that work at one of the conferences last year, again here with you, Sotiris. We started working on integrability conditions for systems of quad difference equations. And the question that Louis and I raised was, okay, can we just derive some of these equations, these integrability conditions, without using all this heavy machinery of recursion operators and all formal series, all this stuff? And we went on and to investigate what is happening, and we found some interesting results. Actually, the answer is yes, we can do that. So the plan of my talk is, first of all, to introduce the class of systems of difference equations that we are going to consider. And based on this class and its description, I'm just going to introduce some terminology of eliminable and dynamical variables. In other words, what variables I can eliminate using my system, and what remains will be what I will call dynamical variables. And then I'm just going on to give a definition of symmetries and how we can determine by just deriving determining equations and derive also construct some consequences of these determining equations. And of course, I will give you some examples just to give you a better idea of what we are talking about. All right, so before that, let me first of all fix some notation, right? So as I've said, we are going to discuss systems of partial difference equations. So we need functions of two discrete independent variables, which we will denote here with n and m. I didn't say it explicitly, but of course, I hope now it's clear that I'm talking about two-dimensional systems with two independent variables. For functions which depend on these variables n and m, like this function u, the dependence on n and m, it will be given in this way. Instead of writing every time u of n plus I, n plus j, I'm just going to use the notation with indices, so ij will denote the value of this function u at n plus I, n plus j. And it is also convenient sometimes to avoid using so many indices to use the shift operators, s and t. The s shifts n by 1 and t shifts m by 1. So if we want on a function fij, if we act with s to power k and t to power l, that means the first index will change by k. We will add the power of s in the first index and the power of l in the second index. All right, so this is the action of these two operators on functions of n and n. Because we are going to discuss systems, and so we have to deal with vectors and matrices. Vectors will be denoted by boldface letters like this one, and the components will be denoted with upper indices like this. On the other hand, matrices will be denoted with Roman uppercase letters. And in general, in some cases, for some definitions, in order to avoid writing all the arguments of a function, I'm just going to use this notation to denote that this vector function f depends on u and some shifts, but in a finite but otherwise unspecified number of shifted values of u. All right, so this is my notation, and let me first of all start with the systems that we are going to discuss. Even though here the definition is quite generic, the example that I'm going to use will involve two functions. Here the definition is about a system of k equations from k functions, ui, I here runs from 1 to k, and this system involves the values of these functions u, of this vector function in 1 u, at 4 points of the z-squared lattice, which form an elementary quadrilateral. So in other words, all the equations of the system will be of this form. It will involve only the shifts of u at these 4 points which form this elementary quadrilateral of the lattice, this here. So, and sometimes we will use components with q with the upper indices, but in most cases we will just use the vector notation. So here q is a vector which depends on all these four variables. u00 is this point, is the value of u at this point here. u10 is the value of function u at this point here. u01 is the value of function u here, and u11 is the value of the function u at this vertex here. Right. Just to make clear here that we say that this system depends on these four vectors, but it doesn't mean that all the components of these four vectors will appear in our system. All right, and that will become clear when I will discuss specific examples. But of course, this is a very generic class of systems, right? So we want to have some criteria, some conditions of what system we are going to consider. Right. First of all, we want these systems, systems to be such that these Jacobians to be different from the zero matrix. What is the Jacobian? It's just a derivatives, is a matrix with columns, the derivatives of q, of that vector q of our system, with respect to variables u1, ui, pq. Right? So what does it mean? It means at least one of the components, u1, pk, u up to uk, pk, or q, sorry, not k, will appears in the system. So in other words, this matrix cannot be zero. All right. So that means at least one component of one of these functions will appear in the system. All right. This is one requirement, and on the other, the second requirement that we have for this system is how we can rearrange this system. And So for that, let me just introduce this notation. So suppose this is an elementary quadrilateral of the z-squared lattice. So we have the 4 vertices here, and I denote them with V1, V2, V3, and V4. And the edges which connect these 2 vertices with EIJ. So E12 or E21 doesn't make any difference. These edges are unidirectional. There is no direction here. Right, so E12 is the edge which connects the vertices V1 and V2. And now what we require for every edge on this elementary quadrilateral, we can rearrange our system, this quadrilateral system, or we can solve it uniquely for L variables sitting on vertex Vi and K minus L variables lying on the other vertex Vj. All right, so let me just, I will give an example in a moment. All right, so for every vertex Eij, I will be able to rearrange my system for L variables lying on one vertex, Vi, and the remaining variables, K minus L variables, lying on the other vertex. The vertex for which I can rearrange my system for these variables, these L variables I denote here with U with indices A1 up to AL. And the variables, the K minus L variables with indices B1 to BK minus L, right? These variables I call eliminable. And all the remaining variables which will appear on the right-hand side of the system, we call dynamical variables. In other words, what does it mean? If you want, let me just try to write something here. So that means I can rearrange my system and write it in the form. So this is this variable sitting on the Vi is a function, let me call it FA1 of the variables U, and let me also call RAL on VI is a function AL of U, and in the same way B1 VJ is a function B1 of U, and so on, or for all the remaining variables here. And the functions on the right-hand side do not involve any of the values which appear on the left-hand side. So the values here, these ones here, this is what I call eliminable variables, and all the variables which appear on the right-hand side here in these functions, I call dynamical variables. All right, so this is what I'm just on this slide, and the importance of these variables stems from the fact that they play an important role in symmetries, as we will see, on functional equations and the initial value problem. And actually, I'm just going to show you an application and use of these variables for an initial value problem. So this is a system which belongs in this class. This is a discrete NLS system coming from our work with Sotiris and Sergey that we've done a few years ago. So here, instead of using U1 and U2 just to avoid all these indices, I'm just calling U1 U and U2 I denoted with V. So this is the discrete NLS system. Well, it's from the way it is written, it's obvious that I can rearrange my system and solve it for these two variables, right? Which actually in this case is the values U and V on this vertex here. Or I can do the same thing for these two, right? And these are the values of U, V at this vertex. Well, probably it's not very clear, but I can also solve this. I can rearrange my system for U 0, 0 and V 1, 0. So U is here and V is here. So on this edge, I have two choices. One is the one, this one, and the other is that one. For this edge, I can do the same thing. I can solve either for U1, 0 sitting here and V1, 1 from here, this pair here. And finally, for this edge here, right, I can solve the system I can rearrange my equation I for U00, which sits on this vertex, and V01. So that means if I have an expression which must hold on solutions of my system, I can use any of these pair of variables to eliminate them from that expression.
So you have written all the possible pairs that can be eliminated in.
Yes, and I didn't probably. I must emphasize here that I require that system can be solved uniquely with respect to
yes.
Yeah.
So that you get a rational function. Yes. Of
Yeah,
course.
yeah. Exactly. And of course, all these choices allow us to set up different initial value problems. For this particular system, we've discussed the staircase initial value problem in that paper when we derived that system, but actually there are more interesting initial value problems, which are actually, this initial value problem exploits all these different choices of eliminable variables. And this is the picture. Let me just explain what we have here. So this line here is the n-axis, so n is 0 here along this line. Right, and so on this line, at these points here, we give u and v. So the two functions are given here. Right now, this is the m-axis, n equal to 0 along this axis. Here, in the upper half plane, we give only v's. So here we have only v as initial condition, and in the lower half plane, here we have as initial condition only function u. And these initial conditions are sufficient to determine u and v everywhere on the plane. Okay, for instance, for here in this quadrilateral, using my system my original system, I can find u and v. So here, what I'm doing, I'm just using a different set of eliminable variables to determine u and v on this edge. Having now this information here for v, I can move to the next quadrilateral and use the shift of my system on the right to determine again u and v, and so on and so forth. So I can move in this direction in this way by just exploiting, using, sorry for that, hold on, that should be, something, there is a, hold on, right, this is that. Something is missing here. Yes, I can solve also, sorry, there's something is missing here. Yeah, I can solve also for U1, 0 from here and V1, 1 from here. So this is the pair which is missing from here. Sorry about that. Right, so this is what this pair is, these eliminable variables I'm using here to determine the values of u and v in these quadrilaterals, in this direction. In this part, in this direction, I'm just using the fact that the system can be solved for this vertex. So I'm just using now this pair of eliminable variables. I determine the values of these eliminable variables using the initial condition. They can do that in this direction. All right, in the same way, in a similar way, we can move below the n-axis. In this direction, what I'm using, I'm just having all these initial conditions here. They are sufficient to determine u and v here. And in this case, I'm just using this pair of eliminable variables. And in this direction, I can use another set of eliminable variables. Sorry about the going back and forth. And what I'm using this eliminable variable. So these variables play an important role in this initial value problems. Of course, as I've said, we are mainly interested in symmetry. So let's first of all give a definition on symmetries. What is the symmetry of a difference equation or a system of difference equations? Well, here in this case, we have a system of k equations with k functions. So, and we call a generalized symmetry of just symmetry, a vector function f of this system, if this relation here holds on solutions of our system. what we have here, we have matrices. These are the Jacobian matrices of the defining function, vector function of our system, right? These guys here, multiplied by these vectors, the shifts of the symmetries, right? And this must be equal to 0 on solutions of our system. Of course, here, of course, the sum is, I don't have any limits, so everything depends on the form of our system. For a quad system like ours, like this one, so this I and j just take two values, 0 and 1, and the whole condition can be written in this form. Right? So what does it mean? So if I have a function, if I have a system Q and I have a function f which satisfies this relation on solutions of my system, this is what we call a symmetry of my system. Of course, the question here is, what happens if I have Q, but I want to find f? How I can find it from here? All right, and this is the main question here. We try to see how we can, from this equation, how we can determine f. For this kind of systems, it can be shown that actually all the symmetries split in this way. We have one part which involves shifts in the first direction, and another part which involves shifts in the second direction. And in this, in what follows, I'm just going to discuss only symmetries of this form, which involves shift in the first direction, and or as we call symmetries of order 1, first order symmetries. All right, so from now on, when I'm writing this equation here, the determining equation of symmetries, f will be of this form. All right, so let's first of all see what this means. We have this equation. Now, as we've said, our system involves k equations for k unknown functions. And so in general, this equation here, the determining equation, involves 8k times variables. So it involves in principle, in general, all these variables. And of course, all these variables are related via the system. So again, it said, so we have the system Q, which relates actually, our original system involves these 4 variables. This system here, its shift to the right actually relates these 4 variables. And the system here, the backward shift, just involves these 4 variables. The interesting thing here is that now in this determining equation that we have, only 2 terms involve these 2 guys. And these 2 guys are these 2 vertices here. These 2 values of u appear only in this term and in that term. So that means if I use the eliminable variables on that edge to eliminate some values, some shifts of u which appear here, the remaining variables on that edge will be the dynamical ones. But if this is a symmetry, this must be an identity. So that means that must be independent of the remaining of the dynamical variables on this edge upon this elimination. All right, and how can I express that? That means if I differentiate my determining equation with respect to the dynamical variable sitting on that edge, then the resulting expression will involve only the derivative of these 2 guys. And the resulting expression will be this. Here, what I have a matrix, a Jacobian matrix of Q with respect to U naught naught, multiplied by the Jacobian matrix of our symmetry. This is our unknown here with respect to the backward shift of the U. And here I have the derivatives of this vector U minus 1, 0 with respect to the dynamical variables on that edge. And similarly, I have here the derivatives of u minus 1, 1 here on this vertex with respect to the dynamical variables on that edge. And of course, it means that if we have 2 or more different choices for these dynamical variables, in principle, we can use all of them. So what is the advantage of this equation? Right here, let me just go back. Here in this equation, f appears with 4 different sets of arguments. F involves only these 3. This shift of F involves these 3. This guy here involves these 3 sets of U. And the last one, this guy here involves these 3. So you see we have 4 functions, the same function actually, with 4 different arguments, a set of arguments. Whereas here we have actually just one function, the derivative, that's a Jacobian of F with respect to U minus 1, 0. With this here, this guy here has depends only on these 3 variables. And this guy here, it's shifted, right? It involves only these 3 guys. So at least now we have our unknown appears with only with 2 different sets of variables. And this is easier to solve. We can do that also not only for this side, but also for the very right side edge of these 3 quadrilaterals. Right? In this case, we just focus on this guy here and this guy here, and these 2 guys are the only ones which involve variables here, sitting on this edge. So if I do the same thing, eliminate the eliminable variables from this edge, and then differentiate with respect to the dynamical variables on the same edge, then I should get an identity, something which was called identity or solution of the system. And this is this relation here. Again, what I have here, I have one object, the derivative of F, the Jacobian of F with respect to U1, 0, and with 2 different sets of arguments. Here I have the shift, so this guy is here, and the other guy, this one, has these 3 arguments here. So these 2 different sets of equations are easier to, easier compared to the generic deterministic equations means to deal with and to solve. And for our example that I've shown you earlier, this equation, the first equation which uses the dynamical variables on that edge, here on this edge, we have 2 sets of dynamical variables. One is U minus 1, 0, V minus 1, 0, which is U and V sitting on that edge. And then the other one is U minus 1, 1 from here, and V minus 1, 0 from here. So we have now to exploit both of these choices and write this equation in terms of these dynamical variables, and this can be done. Well, I'm afraid I'm running out of time, so I probably have to skip more, a lot of details here. And actually, this equation here, when we use either of these 3 choices of dynamical variable, boils down to these 3 equations for the components F1 and F2 of the symmetry. Right? The first one is very simple. The second one, it has the form of a conservation law. I didn't say anything about conservation law, but this is what it is. And actually, these 3 equations are sufficient to solve and determine the dependence of F1 and F2 on U minus 1, 0 and V minus 1, 0. All right, this comes from one of the equations that we get. Now we have to do the same thing for the right side here. In this case, we have 2 different sets of dynamical variables. One is the U and V sitting on taking values on that vertex, and then we have U21 and V20, this pair here. Same story, both of these choices of dynamical variables lead to the same set of equations, and these are the 3 equations that we get for the components of our symmetry. These equations now involve the derivatives of F1 and F2 with respect to the forward shifts of U and V. And again, the second equation here has the form of conservation law. But all these equations that we found here actually can also be found using the integrability condition. But here we don't have to use all the machinery or as a set of formal series and all these things. And they are sufficient to determine the lowest order symmetries up to arbitrary functions of U and V, right? Which then can be determined by going back to this symmetry. Actually, at the end, what we have to do, we have just to determine in some sense, some point symmetries. And in this case, we find these two symmetries only for this system. Of course, here I didn't consider the case of considering symmetries which also act on the parameters which appear in the system. If I do that, then I will derive one more symmetry which depends explicitly on n, on the independent variable, and plays the role of a master symmetry. And actually, in this way, we can prove the integrability of our system. Another system in the same class is this one. This is a different way to write one of the discrete order systems. And right in this case, if we work in the same way, or we have these two equations that I've shown you earlier, we have actually now to exploit, to use the eliminable variables on that edge, well, backward shifted. So I have to use, this is the eliminable variables, and the corresponding dynamical variables on the left edge that I've used earlier are these two. And then on the right side, on the right edge, are the corresponding dynamical variables are these two. And then here you see we have only one choice of dynamical variable for these two edges, and both of them lead to some equations for the components of our symmetry. From the left-hand side,
can I ask about the previous equation? Is it a generalization of the discrete potential KdV equation into two fields, or it's my impression?
And, this is a discrete order system.
Discrete order.
Yeah. It's not the one which is related to discrete KdV.
Oh, okay. I see.
Yeah. Okay. Right. And as I've said, now using these dynamical variables from the left and the right edge, as I call them, we end up with these two equations only for each edge. These are involved derivatives of the symmetry with respect to the backward shifts of U and V, and these with respect to the forward shifts. Right. Of course, here these equations are not sufficient to. Again, these equations are exactly the same that we get from integrability conditions. They are not sufficient to determine the lowest order symmetry. So what we have to do, we gain some information from these two equations, then we go back to this equation and determine the symmetry. In this case, we find two symmetries. This is one symmetry is this pair here, and the other symmetry is that. For the integrability of this system, we're using symmetries. Well, in this case, we don't have a master symmetry which can generate the whole hierarchy of symmetries, but we can use, actually, now it's quite useful to use the integrability conditions and then derive a higher order symmetries for both of these symmetries. And actually, in this way, you can derive in a constructive way all these symmetries and prove the integrability of this system. Right, I think that was what I said. It was already too much for 30 minutes. So here what we've done, actually, we've tried to find a systematic method to derive additional equations for determining the symmetry of a quad system. Right, and this is without using any machinery coming from integrability conditions. Of course, both approaches give the same set of equations at the end of the day, and that should be the case, actually. And the interesting thing is that, of course, I didn't have time to go through all these details. We have developed also a nice systematic method to solve this kind of functional equations, which exploit all these variables, eliminable and dynamical variables. And the good thing is that we can easily implement them in symbolic computations, well, Mathematica or whatever this software you use for symbolic computations. Even though I didn't mention something very briefly, our approach also can use to find non-autonomous symmetries. Usually they appear when we vary for the symmetry. We assume that the symmetry acts also on the parameters appearing in the system. And of course, it's always interesting to see if this kind of approach, this kind of things can be extended to other systems. These systems which defined on different stencils. Right, so far we use this kind of methods and approaches for quad systems and quad equations, but there are sporadic examples of systems of which are not defined just on quadrilateral, but their symmetries are not known. Anyway, so it's an interesting topic. Thank you very much.
Okay, thank you very much, Paulos. Are there any questions or remarks? Again, the conference room, no questions. Maybe any from the online participants? Just in case for those who are watching on the YouTube, they can only ask a question via Zoom, if anything. Okay, then I have one question or comment somewhere in the middle. So I think not everyone in the audience is aware of the connection between these symmetries and the integrability. Maybe you can make a comment.
Right, yes. Okay. Here I've mentioned the word integrability. With this term, I mean we call a system of equations integrable if it admits hierarchies of symmetries in both lattice directions. So hierarchies of symmetries of increasing order. That means that our system, so if just let me go back, right, in this case, let's for this system here, right, we've shown that it has these two symmetries. Now this symmetry, these are not the only symmetries. Then for F, we can you can find a higher order symmetry, which is of order 2, and actually you can find then a third order symmetry, and so on and so forth. Actually, so you don't have just one symmetry, but a hierarchy of symmetry of increasing order. Every time, in every step, the order is increased, and the same is true also for these two symmetries, or this symmetry G. We start with this symmetry, which is of order 1. The next symmetry, which commutes with this one, is of order 2, and so on and so forth. And this is the notion of integrability in this case. The system admits hierarchies of symmetries, as I said, of increasing orders in both lattice directions. Well, for this system again, because the system is symmetric invariant under the interchange of directions N and M, once you have the symmetry in one direction, you have just to swap around all the indices in F and G's in these two symmetries, and you have symmetries also in the other direction. So in this case, we have symmetries in both lattice directions.
Okay, thank you. And any other questions or remarks? Actually, I have one more question, but it's not straight to you. It's a question to Professor Habibulin. Do you have a similar integrability definition for differential difference equations with the symmetries?
Yes.
I know that Pavlos developed a very nice technique for evaluation of discrete systems.
But it is for fully discrete.
Fully discrete, yes. I know it.
Yeah, but what about this differential difference?
Differential difference?
Semi-discrete that you were talking about earlier today.
Yes, we studied differential difference and difference fully, a method of evaluation of higher symmetries, but slightly different from Pavlos. With Garifullian, we have developed some technique how to evaluate.
So there is.
Yeah. I mean, even for this using formal location operators and finding integrability conditions. Yes, it's also well developed for differential difference equations. Yeah.
Okay, I'll ask you later for the reference.
But
okay.
Studies equations higher order discrete, and also for them, as I understand, for them he derived method for constructing biosymmetries.
Yeah, I also. Yeah, is it a method for constructing higher symmetries? Is the question.
Yes, if you use the method of what I call integrability conditions, right? This formal location operator, of course, the integrability conditions that you find play the role also of determining equations for the symmetry. So you can construct higher order symmetry using these formal location operators and these integrability conditions. And usually, and since I have this slide here, what I've done here to find the higher order symmetry, I've used exactly this file. I've used integrability conditions, formal integrability conditions to find the higher order symmetries in for these two symmetries here.
Okay, thank you both, actually. Okay, let's thank the speaker again. Thanks very much, Pavlos. And
okay, I will stop sharing now.
Yeah, so we need to move to the other Pavlos now.
Yes.
From Liverpool to Kent. So.
Yeah.
Okay. Hello, Sotiris.
Yeah, hi, Pavlos. Can you hear me from here?
Yes. What about?
Yeah, okay. We can hear you, we can see you, so you can try to share your slides or your screen.
Okay. What about now?
Something is going on. Yeah, now it's on. So okay, so. The next speaker for today is Pavlos Kostakis from University of Kent, and he will be talking about hierarchies of compatible maps and integrable difference systems. So, Pavlos, you can start whenever you are ready.
Okay. First of all, thanks a lot, Sotiris, and I would like to thank Sotiris and the organizers for inviting me again to give a talk in the conference. And well. And thanks a lot for that. Okay, and in this talk, I'm going to speak about some recent work that it was partly developed with Theodoras Kouloukas from Lincoln University and myself. And well, the work is on deriving and extending, let's say, integrable maps in a way that I'm going to describe what I mean in the integrable maps into, let's say, the non-abelian domain, or in the non-commuted domain, if you like to say, to call it like that. Okay, so this is the idea, the motivation of this talk, and actually the fact is that we want to do also a bit more about extending on the non-abelian domain. We want to have hierarchies of maps, of compatible maps, into the non-abelian domain. Okay, so let me start very quickly with the outline of my talk. Well, I don't know how much I'm going to say today, but I'll try to cover this, these bullet points. So first of all, I will start with an introduction of what is known in the literature on the commutative setting. And then I will say what we want to achieve, and actually want to achieve the bullet points 1 to 3. That mainly I would like to extend in the non-abelian domain the Yang-Baxter maps, and then derive hierarchies of these Yang-Baxter maps. And finally, to associate these Yang-Baxter maps with hierarchies of integrable difference systems in edge variables. So actually, I can associate these Yang-Baxter maps with partial difference integrable equations in 2 dimensions. So I mean, in 2 dimensions, I mean 2 independent variables. Okay, but first of all, I would like to present some definitions. Actually, we have to do some definitions, and after that, I will give you the results. Okay, so for some definitions, I just have here what we will call a vertex equation. So a vertex equation is a discrete equation on the Z2 graph that relates the values of the dependent variable that I denoted here as phi on a cyclic cell of this graph. So actually, an equation that relates phi, phi1, phi2, and phi1, 2 will be called the vertex equation. And here I said phi, phi1, phi1, 2. And in that setting, I just want to stress that this will be my notation further on. Actually, what I want to say is that phi mn, that it is here, I will denote it just with phi, the shift of this function phi on the m direction, that it will be this phi m plus 1 comma n, I will denote it as phi 1, the shift of the phi, let's say, variable on the n direction by 1, I will denote it phi 2, and clearly this phi m plus 1 n plus 1, I will denote it as phi 1, 2. And the prototypical example of a vertex equation, actually of an integrable vertex equation, is what is called lattice potential KDV equation that is written over here. well, the large potential KdV equation serves as the discretization of the potential KdV equation. And well, it's an example that it's very well studied, it's very well behaving, and with many applications in mathematical physics. And so at the end, I'm going to end actually this talk, well, not now, of course, but I'm going to end this talk by proposing a non-abelian model for this version of this large potential KdV that I think that, well, maybe is not so known in the literature. Okay, so this is about the vertex equations. So now let me move to edge equations. Again, on a cell of a Z2 graph, if I have a pair of, let's say, relations which somehow connect the two vertices of the elementary code with two edges of the elementary code with a common vertex to their opposite ones, this could be called the edge equation. And okay, for instance, again, I have, for instance, if you want x and y, and I have one equation that actually relates x2 with x and y, and the other relation that relates y1, this one here, if you want, with x and y. And a prototypical example, again, if you want, of this edge equation is what is called the companion of the Adler map. And I give it here. So actually it tells me that y1, that is the value of the field y on this edge here, is given by this formula in terms of x and y. And x2 is given implicitly in terms of x and y again. Well, of course, one can substitute y1 into here and have an explicit formula, but for a reason that you will become, well, in the next slide clear, I just want to denote it like that implicitly. Actually, why, maybe I'll say it now, why I denote it implicitly, because actually you see already that the first equation of the CH5 is already a conservation relation. And, well, it's written as a conservation relation. Okay, so this is, let's say, an example of an edge equation. And what is interesting is that from the examples that we do have of integrable, if you like, vertex and edge equation, is that the point is that usually the integrable vertex and the edge equations are related. The way to go from a vertex equation, from an edge equation to a vertex equation is called potentialization. Whether the other way, we will call it vectorization, if you like. Okay, so actually for the potentialization, so it means that we start from the companion of the Adler map that I had the previous slide. The first term of the companion of the Adler map actually guarantees, because it's written as a conservation relation, guarantees the existence of potential function phi that is defined in this way. And actually, in terms of phi, the first relation of the companion of the Adler map is automatically satisfied, identically satisfied, where the second one will be reached exactly as the lattice potential KdV equation. Okay, so in that way, introducing a potential, we can go from an edge equation to a vertex equation. The other way, actually, that this was given by Papageorgiou and Veselov, we can go from a vertex equation to an edge equation by using the invariance, if you like, of the underlying symmetries that the vertex equation has. So actually, the lattice potential KdV is translation invariant with respect, is translation invariant. So if one rewrites lattice potential KdV in terms of the invariance of, let's say, of this symmetry, of the symmetry generator of this, let's say, group action, we'll get exactly the CH5 that is started with. Okay, so this is, if you like, the story. And now, how this edge and vertex equation relations related. And now let me give what is known in the literature, and let me speak about a list of other Bourbon series that actually incorporates what is known, well, not everything, but what is known under some, let's say, requirements of integrable vertex equations on the Z2 graph. And actually, these are the equations that constitute the Andrei-Bobekov-Souris list. The Andrei-Bobekov-Souris list of integrable equations is a classification up to some, of course, conditions we want to put in the classification that I'll probably speak later on, but it's not so important for this presentation. But what I want to stress here is that, okay, we have all these equations which are integrable vertex equations. The top equation is the Adler equation or the Q4 equation, where all the others come by various degenerations or by a limited procedure. And all of these vertex equations can be related to edge equations. Nevertheless, for this presentation, I will consider the vertex equations that are below this red line that I have here. Okay, and these vertex equations which are below this red line that I have here are related, to, I will skip that, I don't want to speak about classifications. About the ABS classification is well known, and actually one can see it in the original paper. But what I want to say is that all the equations below, of the ABS list below the red line, are related to these lists of vertex, of edge equations. Okay, this list of vertex of edge equations were derived by Andrei-Bobekov-Souris in 2004. Actually, the first column of vertex equations and the second column of vertex equations was given a bit later by Papagiorgiou, Tonkas, Souris, and Veselov in 2010. Okay, here I have to just to stress something is that although for the vertex equations we have classification by classifications given by Andrei-Bobekov-Souris, and maybe also this classification by relaxing some requirements of classification was extended by, let's say, Ball and Souris a bit later. In the edge equations, we do not have classification yet. So actually, it's an interesting open problem to define a classification for the edge equations. Another thing that I want to stress here before proceeding is that the edge equations are usually simpler than the vertex equations, and that's why when we want to go to the non-abelian domain, we will use the edge equations. Moreover, because to go to the non-abelian domain, and of course to go there and preserve integrability, it's a quite allow me to say, delicate procedure. Okay, we will go to the non-abelian domain by extending the lax representation of these systems. This will be our strategy, and actually by using the lax of the abelian systems, we will extend it to the non-abelian domain in a nice systematic way that I'm going to explain, and we will obtain the non-abelian analysis of these systems. But maybe a bit late. But anyway, so actually what I want to say here, so as I said, I described is that the edge and vertex equations could be seen are related, and moreover, they can be seen as a map. This is the map, the underlying map. And now let me speak very, very quickly about what is this property somehow that manifests integrability in terms of edge equations when the edge equations are seen as a map. This property is what is called 3D compatibility of maps, and this is related to the 3D consistency of the, okay, it's in a sense equivalent to the consistency of the underlying vertex equation. And so let's start. So if we have any set, and if we have a map F from the Cartesian product of this set to itself, we can consider the maps Fij, which are the maps that act as F on the ith or the jth factor of the triple product of the set X. And if we will denote this map with components as I have done it here, then the map F will be called a 3D compatible map if it holds this compatibility relation, or if it holds, well, or in an expanded form, that means we have this kind of 3 in total compatibility relations to be valid. Okay, so this is the integrability of the 3D compatibility of maps. And the 3D compatibility of maps under an assumption of quadirationality that or partial inversion that I'm going to describe in a while, actually are the 3D compatibility is equivalent to the Yang-Baxter property. So actually, a 3D compatible maps with this quadirational, its companion is a Yang-Baxter map. So a map R will be called Yang-Baxter when this quantum Yang-Baxter equation is satisfied when we consider composition of maps. All right, so this is the Yang-Baxter property. Then I'm going to speak very quickly about equivalency of maps and symmetry of maps. So two maps R and R hat will be called Yang-Baxter or WB equivalent if it exists a bijection K such that this relation holds. Also, a map also bijection phi will be called the symmetry of the map R if this relation holds, as I've written it here, or in other words, if we use the bijection phi to rewrite, to change coordinates, so to express the map in a new system of coordinates, then the form of the map will be the same in the new coordinates. This is actually what this means. And what I want to say is that this Yang-Baxter equivalency relation that I introduced above actually respects the Yang-Baxter property as well as 3D compatibility. And if one wants to classify actually Yang-Baxter maps or 3D compatible maps, he has to use actually this equivalency relation. But anyway, this is, we don't do classification here, but just to stress it. And then just to introduce a very important notion of quadirational maps or partial inversion of a map. So a birational map R will be called quadirational if this companion map is also, as it is stated here, is also birational. Okay, so you see it's a partial inversion of the map, and this is the quadirational. And the statement here is that actually the companion map of a quadirational map is a 3D the companion map of a quadirational Yang-Baxter map is a 3D compatible map and vice versa. And finally, I will put a very important, let's say, proposition given by Papageorgiou, Dongas, Veselov, and Souris in 2010 that actually states that if we have a Yang-Baxter map R, then we can build a new map out of it by using the symmetry of the map R, and this new map R will be also be a Yang-Baxter map. And moreover, the maps R and R hat will not be Yang-Baxter equivalent. Okay, finally, we can have the Lax matrices for 3D compatible maps and Yang-Baxter maps, or actually we can have a matrix refactorization problem, and we can have, let's say, the Yang-Baxter map or the compatible map out of it. So actually your map is equivalent to matrix factorization problem. And okay, having all this and reciting again the list of Yang-Baxter maps given in the past by Adler, Bobek, and Souris. This is actually the list of quadirational Yang-Baxter maps. And what is called the H list of quadirational Yang-Baxter maps given by Adler, by Papageorgiou, Dongas, Veselov, and Souris. These are the Yang-Baxter maps that we would like to extend in the non-abelian domain. And how we will do it? Actually, we did it with Theodoros Kouloukas recently, a few months ago. And what I mean non-abelian domain, I mean that I consider that the map acts on elements of an associative algebra over a field phi, F, with multiplicative identity. Okay, not to lose time, I will consider this so the algebra actually, well, we have in mind, for instance, a skew field, for instance, quaternions, as an example. And so let me go straight into the result that we had with Thodoros. The result we had with Thodoros is that this, what we call CK family of maps, given here as it is, where ABC belong to the center of my algebra, so actually it can be considered as scalars if we want. Okay, this family of maps for generic ABC, this has the property that it has asymmetries, these bijections, has a strong lax matrix, these metrics that I have written here, where lambda is a spectral parameter that is commutes with 30, that belongs to the center of this algebra, and this map is a 3D compatible map. Okay, this is where we have to stop. Okay, this is a non-abelian map. What we have to observe here is that if this map was abelian, so if the symbols here were commuting, what will have happened? Will have happened that the product U2 with U1, if you see here, will have become x2 x1. So, and moreover, the product y2 times y1 will be v2 v1. So in a way, in the commutative case, x1 x2 v1 v2 is are invariants of this map. And if we want to mimic the commutative case, but still remain in the non-commutative domain, we can demand or assume that x2 times x1 and y2 y1 are invariants also in the non-abelian domain. This was called centrality assumption by D'Oliva. And by doing so, we can partially invert this decompatible map and obtain the associated Yang-Baxter map. This is the associated Yang-Baxter map, and in the new variables where actually I used this invariants P and Q, which are the U2, U1, Y2, Y1, I have this map that is in a non-abelian domain now, and this is a Yang-Baxter map. Okay, so what is the story? That was the main result of us with Thodoras. We had also the the symmetries and the lax matrix. And what is the story here? The story here is that in the commutative setting we have these two lists, H and F list, but in the non-commutative setting we have the K list of maps, this general map K that I wrote before, the H, the F, and the lambda. So we have more richness, more rich. The situation in the non-commutative case, as expected, is richer. Okay, so this is what we get. Just for instance, to give you some example what we obtained, I will give you here the F list of quadrilateral Yang-Baxter maps extending the non-abelian domain. Here, the maps below the red line were known in the literature, the non-abelian analogs. Okay, actually they were known, but here the F2 and F1 are new, so they were not known in this format. Actually, you can see why. Maybe you explained why they were not known. I mean, you can see the symmetry in the formulas from F3 and 4 and F5, but even from F2, you see that the symmetry breaks, and actually you have this y minus v here, and times 1 minus v to the minus 1 over here. That clearly these things will cancel in the non-abelian domain, but this is not the case in the they will cancel in the abelian domain, but not in the non-abelian domain. And of course, these things are important, these factors, in order to have the Yang-Baxter property, if you like. Okay, so maybe I do not have much time, but let me proceed very fast on what I did a bit later, or what we can do more. Actually, what we can do more is actually we can extend the lax matrix that I introduced earlier to the order n case. So I can have n times n lax matrices. And how this extended lax matrix of the CK of the CK map will look will be one part will be, let's say, this form. So okay, I give it here explicitly this map, this lax matrix, and so sorry, I'll go a bit fast. I'll go a bit fast, but okay. Sorry. So let me say about the slide. Okay. So if we start with this lax matrix here, and this lax matrix will give us a vertex, an edge system that looks like that, and this 3D compatible edge system was given by D'Oliva in 2014 in the non-commutative setting. Of course, it was known before, and it was known by Newman Yamada in 2002 in the abelian setting. And okay, and here what I want to say is that if we consider n to be infinite, tends to infinite, actually this system serves as the non-abelian Hirota-Miwa equation, as it is said, and it was given by Nemo in 2006. Okay, so this is the one lax matrix, and this lax matrix for n equals 2 give rise to the H3B Yang-Baxter map. Okay, we can have another matrix. Actually, we can have n times n minus 1 matrices like that. Will give some systems. But what I would like to state here is that actually we can deform this lax matrix actually to obtain a new lax matrix by multiplying this Ln0, we multiply from the left with this diagonal matrix, as I state. And if we do so, so we have a new lax matrix, and this new lax matrix will give us a new integrable difference system in edge variables, this one. And this one clearly is the one that I can extend it. This is 3D compatible. It's a 3D compatible map, defines a 3D compatible map. And let me say some properties before finishing this talk with this system, is that this admits a strong lax matrix. It's a birational one, actually, because I have this kappa j, the two systems. These are multidimensional compatible, admit two non-equivalent families of multiplicative potentials. And in terms of the potentials, we obtain two Backlund-related integrable hierarchies in vertex variables with rhombic symmetry. The first hierarchy is the hierarchy of the non-abelian lattice potential modified KDV, and the other one is the non-abelian Neifeld-Queisel-Capel hierarchy, NQC hierarchy, or the Q3 node hierarchy. Furthermore, with the rhombic symmetry. Furthermore, if we impose the centrality assumptions as it states here, we have quadrirrationality, so we can obtain hierarchies of Yang-Baxter maps, non-abelian domain. And we have the lattice modified Gelfandiki hierarchy, or the NQC Gelfandiki hierarchy, but here with the D4 symmetry. All right, maybe I do not have much time, but here we can have the Yang-Baxter maps. We can have the hierarchies of different systems in edge and vertex variables. For instance, well, this is the NQC hierarchy, as I have it here. Well, this is the rhombic Q3 node, as I said it, and if we add centrality, we obtain the D4 non-abelian version of the lattice NQC, or the Q3 node, that looks like that. And okay, because I don't want to have time, I just want to, instead of writing the hierarchy, I just want to end this presentation by ending of how I started, I will just present the non-abelian, if you like, rhobic lattice potential KdV equation that is now this system of equations of phi and psi. This has the rhobic symmetry. That means that if we reflect these equations in terms of the diagonals of the chord, this system will be, the equation will be invariant. And moreover, if we impose the centrality conditions, that looks like that, we will obtain the D4 symmetric version of lattice potential KdV that was given in the past by Frank Nyhoff and Chris Field. And okay, so this is what I wanted to state. And finally, is that I just want to mention that our next call is to provide the same, to do the same things for the, well, Q4, for instance. This is what we would like to do, and maybe, well, we can speak about discrete Penlevé as well, non-abelian discrete Penlevé equations. Okay, so that's it what I wanted to say, and thank you very much for the, for the attendance.
Okay, thank you very much, Pavlos. Are there any questions or remarks? Okay, there's one question by Valery Bartakov.
Thank you for interesting talk. I would like to know about your your description of non-abelian Young-Baxter maps, but you consider on under what ring or under what algebra you consider it?
I consider it under an associative algebra with unital associative algebra. So.
But in your formula, you can see that u minus v in inverse, but division. But it means that it's defined on not all pairs.
I think I understand what he's trying to say, but you were talking about two things. Okay, correct me if I'm wrong. When you have Young-Baxter, you have inverse elements, so yes, there you have a division ring. However, when you are in the case of the discrete integrable systems, like in the last slides, you don't need any inverse, so you are in a free algebra. Is that correct?
Well, yes, but of course, well, you might want to have an initial value problem, so you need to solve for a specific field in order to propagate your well, your initial data. But okay, you can always be on a division ring, but actually in some cases we can be. You don't need to be so.
Yeah, so these Young-Baxter and discrete integrable systems, they are very much related. If you want to derive a map, yes, you need to solve for these new variables, so you need to inverse some elements, so you need to restrict yourself to a division ring. However, if you are in the case of discrete systems, you don't necessarily need to solve for all these variables to get a discrete system, so you can be in an associated variable. But as Pablo says, if you have initial conditions and you want to find solutions, then you need again to restrict yourself to a division ring. Is that right, Pavlos?
Yeah, it's right. So let's say to be safe for all these things and invertibility, to be on the division ring or a skew field. Yeah. But of course, with some, I still think we should not be so restrictive. Maybe we can find some other cases. I mean, for instance, when we have a totally positive Young-Baxter map, we can have totally positive Young-Baxter maps. For instance, if you see this map here, ABC, let's say, belong to the center. So for C equals -1, you have a totally positive Young-Baxter map. So there you can take the algebra, your algebra to be the upper triangular matrices, where in the diagonal, your diagonal belongs to R+, for instance. So there always you have elements that, well, you will have no problem with inversions, whatever you do with your map.
Okay, so I understand. It's defined not all for all pairs. For some of them, it's defined. Yes.
Yes.
Thank you. And next question.
In this example I was telling. Yeah.
Is it possible to define twisimilar map for tetrahedron map? If we consider in Stott-Young-Baxter relation, you can consider tetrahedron relation. Is it possible to construct the maps of this type? For
yes, possibly.
rational, for example.
I think Sotiris has also some examples, but also prior to them, I mean, even the original work from, well, also Kashaev.
Kashaev, yes. Because the same relation that have... Yes. So Pavlos now was saying about the relation between Young-Baxter maps and lattice equations, but there's a similar relation, okay, a little bit more complicated, between tetrahedron maps and 3D lattice systems. And the very most popular example is the Hirota, discrete Hirota, the non-commutative, is related to the star triangle transformation. Yeah. Yes.
Yes, indeed. This is the case, and they have done it. I mean, many.
So they actually, in another paper, they have a theory of how you can go from tetrahedron to 3D lattices via symmetries.
Yes. I think the first person did it, but correct me if I'm wrong, is 96 Kashaev in his paper, but yeah, maybe even before. But I think Kashaev was the one. No, Kashaev was one in his 96 paper. Where he, anyway, yeah, that's it.
Okay, any more questions? Okay, in which case, thanks again very much, Pavlos. Thanks for us.
Thank you very much, and thanks for the questions as well.
So we now, I guess, move to Varna. Is
yes,
Georgi.
Exactly.
Hi, Georgi.
Hi, Steve.
Okay, we can see you. Oh, is it Tesexen?
No, this is
it's Varna. Yeah. Because you have a lot of books everywhere, so it's difficult to, right? Can you try to share your screen then?
Yes, I will.
Okay, great. We can see your slides. So can you do it full screen?
Yes.
Perfect. So the next speaker for today is Georgi Grachovsky from the University of Essex in the UK, and he will be talking about real Hamiltonian forms of affine Toda field theories. So Georgi, you can start whenever you're ready.
Thanks, Sotiris. So first, I would like to thank the organizers about the possibility to participate virtually. And I promise that once all the obstacles are over, I'll try to make it face to face. We can only hope that this can happen soon. So the results I report today are based on joint work with Vladimir Krejcikov from Sofia and Alexander Stefano from Sofia as well. Here are the exact references. So I'll be talking about affine total field theories related to Lie algebras. And first, we'll just present a few slides of preliminaries to set up the stage, notations, and all that. Then I'll describe briefly what real Hamiltonian forms are. And then, with the main part, we'll discuss the spectral properties of the associated Lax operators, and we'll provide a couple of examples here. So for say, if we want to save time, probably I can skip the second exam. All of them are available, or the preprint that we have. This is the third item in the list here. So we might need to save time, I have a feeling. So it's well known that to each simple algebra one can evaluate both conformal and affine versions of total field theories in 1+1 dimensions. By 1+1 dimensions, I mean that I have one space and one time variable. And since 70s, due to Flaschke, it's known that these models allow Lax representations. And in this case, you need to choose the Lax operators of this form. So here lambda is a spectral parameter. The coefficients in front of the spectral parameter are actually contain the fields in the second Lax operator, and here the field is outside. So here Q usually belongs to the Cartan subalgebra of early algebra, and it has a dual vector in the r-dimensional Euclidean space, which gives us the components of our total field. And then if the summation here goes over the simple roots of early algebra, we say that the equation of motion gives a conformal total field theory. If the summation goes over the set of admissible roots, that is the same as the minimal root was added, then the total field theory is known as affine. And the Lax representations for most of total field theories are normal, related to the normal real forms of the corresponding clear algebra. And our aim here is to describe the so-called real Hamiltonian forms of affine versions of total field theories related to complex, untwisted, or with height 1 exceptional affine algebras, and to provide some examples and to outline the spectral theory of the associated Lax operator. And here we'll start with some background material that we might need. So if we have a simple algebra, if small h are the generators of the corresponding Cartan subalgebra, and capital E's are the generators of the complement part, or the so-called vowel generators, then we'll assume standard commutation relations of this form, and here the integers actually capital N gives the structure of the commutation relations. To each root system, one can associate a vowel group generated by reflections with respect to a hyperplane of this given root alpha. So if you take the entire root system, actually this will generate your vowel group. The important feature of this vowel group is that each element of this group has a finite order, and also that there is a vowel group reflection with a maximal order. So this maximal order is known as the Coxeter number of the algebra, while the automorphism of the algebra that corresponds to this reflection is known as the Coxeter automorphism. And again, the important properties of these Coxeter numbers and automorphisms are that they don't depend on the choice of the basis. This means the choice of these ends in the normalization conditions, and the choice of ordering, and of course the choice of the representation. Then each element of the vowel group can be written as a composition of basic reflections with respect to the simple roots of the algebra. So here the integers n sub 1 to n sub k actually they're also invariants of the algebra. And the Coxeter automorphism can be written just if you take all these integers to be equal to 1. Then finally, another important property of this Coxeter automorphism is that it always allows the dihedral realization. This means that if you have two sets of orthogonal roots to each other, you can always write the Coxeter automorphism as a product of the composition of reflections of these two sets. The important thing is that each alpha here is orthogonal to each beta here. And in this case, of course, the two automorphisms C1 and C2 will generate the dihedral group. Then, if we have a semi-simple Lie algebra, you can generate the real forms by imposing an invariance condition with respect to an involution sigma, which is called a Cartan involution. So every involution that commutes with minus Hermitian conjugate is called a Cartan involution, and actually the classification of non-equivalent Cartan involutions gives the classification of real forms of the algebra, and this is done by Cartan. So the compact real form corresponds to sigma equals 1, and then for orthogonal and symplectic algebras you have normal real forms that corresponds to sigma equals minus transposal. Then we should also note here that the Cartan involutions are determined up to an automorphism from the Cartan subgroup of the algebra. And if we have non-compact real forms, usually Cartan involutions split the root system into two types of roots: compact roots, which are orthogonal to the involution, and non-compact roots, which are not. And usually for non-compact roots, you can have two types of orbits. A one-element orbit if the involution just changed the sign of the corresponding root vector, and two-element orbits, where actually the involution acts non-trivially. And for our purpose, we'll make use also of the so-called reduction group. I'm sure that this morning at least a couple of people mentioned about this. So this is, roughly speaking, an invariance condition on the Lax pair combined with conformal mapping on the complex plane of the spectral parameter. This was introduced by Sasha Mikhailov in late 70s or early 80s, and what I'll just say here is that all these algebraic constraints that are induced by these invariance conditions will be automatically compatible with the evolution of our system. And for in the case of extracting real forms, the Z2 automorphism that extracts the real form of the Cartan evolution acts in addition on the complex lambda plane via just a complex conjugate. And if we go back to our total field theories, it's also well known that they can be written as infinite-dimensional Hamiltonian systems with Hamiltonian functional written here and a canonical Poisson bracket. And our aim here will be to start with a given finite order field theory. This means to start with a given Hamiltonian or a Poisson bracket, and to complexify it, and to try to extract real Hamiltonians and Poisson brackets, or real forms of real Hamiltonian forms that are automatically integrable if we start with an integrable one. So for this purpose, we introduce an involution calligraphic C that acts on the phase space and preserving first any function of your dynamical variables, then preserving the Poisson bracket and the Hamiltonian. So if we can find such an involution, and if we assume also that the Hamiltonian is an analytic function of the dynamical variables, then by complexifying our dynamical variables and actually admitting the results that the Poisson bracket will also become complexified, and these are the non-zero components, then we'll try to extract real forms. So this means that our complexified total field theory will have actually a real and imaginary part, and the symplectic form have this part. And if we impose an invariance condition with respect to the composed involution C and the complex conjugate, which means the reality condition, of course, this will split the initial phase space into +1 and -1 parts, and then the composed involution will split the complexified phase space, and now actually the +1 part will contain a complex dynamical variables exactly in the same way as the Valery unitary trick works for real forms. And then if you restrict yourself the +1 space, it means that this is the subspace which is invariant with respect to the composed involution C twiddled. You automatically get a real valued Hamiltonian, which will correspond to an integrable system, since the reduction group and the involutions, all the automorphisms, they will preserve the evolution and the dynamics. And this automorphism C actually plays the role of the Cartan involution that extracts real Hamiltonian form. And then if the evolution satisfies the three conditions we mentioned, one can always get an integrable real Hamiltonian form starting with a given affine total field theory. Since the evolution must preserve the Hamiltonian, this means that we need to bear in mind a kind of additional restriction that which tells us that the evolution must preserve the system of admissible roots if you have a affine total theory, or the system of simple roots if you have a conformal total field theory. And such evolutions can be constructed from or even from the Z2 symmetries of the extended Dinkin diagrams. And here there are some references that we have the examples about this. Then we should mention here that since here we'll be considering systems with Z H symmetries, that the Coxter automorphism can be realized either as an element of the Cartan subgroup of the algebra, and then this can be done using the fundamental weights of the algebra, and then it can be alternatively realized also as an element of the Weil group of the Lie algebra, using the dihedral realization. We just need to pick two systems of orthogonal roots, and then this will work. Then if we consider for the spectral properties of the Lax operator, if we consider class of potentials that go to zero faster than any degree of x when x goes to plus or minus infinity, then the complex lambda plane will get split into twice h regions of analyticity, and the rays that split these regions will give us the continuous spectrum of the Lax operator. So the rays are determined by the angles that they close with the horizontal axis, and then in each sector one can construct a fundamental analytic solution. Since if you start with the real solutions or the fundamental solutions for the Lax operator, there will not be analytic at all. So there will be elements that are analytic, there will be elements that are not. And the construction of fundamentals analytic solutions are actually formally reordering the rows and the columns in such a way that the reordered fundamental solutions are analytic in the region. And usually this is done by the factors of the Gauss decomposition of the corresponding scattering matrix. Now in the case of the ZH symmetry, so if we have twice H regions, actually it tells us that the involution connects regions with step 2, and that you just need 2 regions as fundamental domains. So this means that for the minimal set of scattering data that we'll need, we just need the scattering data formulated on 2 rays. Then the symmetry will relate all the others. Then using this symmetry, actually the inverse scattering problem for the Lax operator itself can be reduced to a local Riemann-Hilbert problem in more multiplicative form. So if we just define the sawing function on the borders of between 2 regions, actually, if we impose also that canonical normalization of the solutions, then we'll always have a solution, since the Riemann-Hilbert problem will be local and with canonical normalization, which will serve as initial condition for the Riemann-Hilbert problem. And then one can show that one can recover the potential automatically from the solutions of the Riemann-Hilbert problem. And now, as I mentioned, the minimal set of scattering data are formulated just on 2 rays, so there are 2 options, either in terms of transmission or in terms of reflection coefficients. All these can be expressed in terms of the Gauss factors, so I will not spend time for this, and I'll try to go for an example. So if we consider the height 1 E6 affine Lie algebra, so the exception is from the exceptional Lie algebras. The extended Dynkin diagram is given like this, so this is the minimal root, alpha naught is the minimal root. And so now for the dihedral realization, if we just consider the black roots, so obviously they are orthogonal since they are not connected by any line in the Dynkin diagram. So this means that we can realize the Coxeter automorphism using the black and white roots. So here are the set of admissible roots, and the total field is given explicitly. So we will have only 6 independent coordinates, since this is a special projection actually. All the exceptional algebras can be constructed as special projections on the dual Euclidean space, and here the fundamental weights. So the Coxeter automorphism can be written as this decomposition. And now if we pick one of these automorphisms like S2 to extract a real Hamiltonian form, we'll get Hamiltonian system of the affine total field type with a Hamiltonian which is given with this formula. I should say that alternatively one can pick this involution to extract the real Hamiltonian form. You get another Hamiltonian form which is in a sense dual to the one presented here. And here we have written explicitly also the Coxeter automorphism as a linear operator in the dual space and the characteristic polynomial of it. Of course, we can try to do this. Probably this is an interesting case. The G2 affine algebra, so there is only untwisted affine algebra of G2 type. The set of admissible roots are just 3, since this is rank 2 classical. G2 is early algebra of rank 2, and these are the fundamental weights. So if we impose invariance with respect to the first, which is the product of the reflection with respect to alpha 1 and the minimal root, you will get a Hamiltonian like this, and a fine total field theory related to this Hamiltonian. And of course, the root space will be split with respect to the involution. And I should note here that it appeared to be both the most simplest and the most peculiar case. The peculiarity comes from the fact that G2 is rank 2 algebra, which means that the dual Euclidean space should be the Euclidean plane. But traditionally, this algebra is written as a subalgebra of B3 or SO7, which is a rank 3 algebra. And this is done via a projection that with respect to the hyperplane, to the plane given by E1 plus E2 plus E3. That's why for the Coxeter automorphism here, we can have a standard realization by 3x3 matrices using this projection from SO7. If we do this, this is the result. And if we decide to go directly, then one can also proceed it like this. Then the dual space will be the Euclidean plane, and the roots and all the roots must be written in terms of this projection explicitly. Then everything will become 2x2 plus one-dimensional invariant subspace of this projection. So if we project onto the non-parallel part, we will get the 2x2 realization of this. In all cases, the Coxeter number of the algebra is G2 is 6, and the exponents are 1 and 5. So this doesn't depend on any choice of representation, basis, and everything. So this is in both cases, it remains. And there are other examples in the main text. So as a brief conclusion, since now I'm on my 28 minutes since I started, we can just say that we presented some real Hamiltonian forms of affine total models related to exceptional and untwisted Kac-Moody algebras. We outlined the spectral properties of the associated Lax operators, which have ZH symmetries. H is the Coxeter number. And as open problems, I should mention the complete classification of all non-equivalent real Hamiltonian forms. Since I should mention here that you can generate actually new integrable systems like this. Then the description of the entire hierarchy of Hamiltonian structures. in order to find Soliton solutions, one needs to extend either the dressing method or any of the alternative methods, direct methods for obtaining Soliton solutions. The difficulty is that due to the higher order symmetries, actually you need to start with dressing factors with too many singularities. Then I should mention that an open problem is to study types of boundary conditions and boundary effects for these models and the real Hamiltonian forms. And the complete picture is, of course, to provide a complete solution of the inverse scattering problem for these operators. So thank you very much for your attention, and I think I overran with about a minute. I apologize for this.
Questions?
It seems that everybody is waiting for the coffee break.
Thank you for interesting talk. I have maybe stupid questions. You consider the Coxeter automorphism for some Lie algebra special type E6 and G2. Is it possible to define this automorphism for Lie algebra of type A, B, C, and so on?
They're well defined and they're known for a very long time. For example,
it's well known.
So in the books of Bourbaki,
yes,
I think in the second part there are very detailed appendices about this.
They defined and studied, but
Yes,
why they did
well.
not study this?
Sorry?
You told that Coxeter automorphism are defined for Lie algebras of type A, B, C.
Yeah, for the classical series and for all classical simple Lie algebras, they're well defined, well studied, extensively studied, and in almost every book. Actually, you can find them. So, for example, in the books by Bourbaki, in the second part of these books about Lie group, the volume about Lie groups and Lie algebras, you can find a very detailed appendix about all the classical series and the exceptional series. So for a fine Lie algebras, there is a book by Roger Carter, published probably 15 years ago, which also has a very detailed study. And very recently, accidentally, I find a book by a Chinese author. It's cited somewhere in the paper, which is also very good and very detailed, And there are lots of constructive results there for all this.
Thank you, thank you.
You're welcome.
Okay, I think there are no more questions, so thanks again.
So now it's coffee time.
Yes, coffee time. Coffee is upstairs. Sorry, guys, we need some coffee.
Okay then, so we are ready to start the final session of this conference. So the next speaker is Valery Bardakov from the Sobolet Institute of Mathematics in Novosibirsk, and he will be talking about braid groups and the Young-Baxter equation. So Valery, please, you can start.
Thank you, thank you. At first, I would like to thank the organizers of this nice conference for invitation, for the possibility to be here in your beautiful, beautiful city. I am first time here. And also, I thank all participants for interesting talks, for interesting conversation. And today, I will speak about some results which we have found with Dmitry Telalayev, and now these results are available in archive, and today I say only about some of these results. During my talks, I recall the definition of Young-Baxter equation and braid equation and say about connection between them. Also, I explain what is virtual braid group, what is generalization of the classical braid group, and say about a couple of our results. The first result is dedicated to connection of Young-Baxter equation and representation of a virtual braid group. And the second result is dedicated to the following question. Suppose that we have solution of the Young-Baxter equation over some vector space B and some vector space C, and we consider their product. How is it possible to construct solution for the Young-Baxter equation on this vector space? Of course, there are different approaches, and we also suggest some approach for construction of this solution. We consider quantum Young-Baxter equation, but study two types of solution, linear solution and set theoretical solutions. Some results it's possible to use in both directions. Young-Baxter equation and solution of the quantum Young-Baxter equation is a linear map from the tensor product of V by V, where V is a vector space over a field K, such that the following relations is true, where the product A12, R23, R13, R23 is equal to the product of these operators, its opposite direction. Here, what is RIG? RIG is operator which acts from the V cube tensor cube to V cube, such that it acts as R on the ith and jth factors and as identical on the third factor. Buchstaber called such map A Young-Baxter map, and we will call the pair VR is said to be a solution of the Young-Baxter equation. And Greenfield suggesting to study solution for which instead of vector space V, we consider some arbitrary set X. We consider the set X, take its square, and define a some map. And define some map A. A is only map from x squared to x squared, such that it's if we consider the vector space with the basis x, then it must to satisfy the Young-Baxter equation. It's analog in this case. We say that the pair XR is a set theoretical solution to the Young-Baxter equation. For example, if we take X is an arbitrary set, when the map P of XY, which permute these elements, give a set theoretical solution for the Young-Baxter equation for arbitrary set X. It's not difficult to check that if we have A is a solution for the Young-Baxter equation, then the following map S, what is a composition of P, P's permutation, and A is solution for the Young-Baxter equation, give the solution for the so-called Braid equation. Braid equation is equation of this type. It acts on the V cube to V cube, and this operator acts as S on the second component, as identity on the third component. Next operation acts as identity on the first component, as X as on the second and third, and so on. You can see that in fact these equations it's similar to the relation in the braid group Bn. And now I recall the definition of the braid group, and the definition it's generalization virtual braid group. Braid group Bn on n strengths is generated by element sigma 1, sigma 2, sigma n minus 1, and is defined by two types of relations. First relations is the so-called braid relations. It's look like as braid equation, and this relation is so-called commutativity relations. You can consider the braid group as object of combinatorial group theory, because we defined this group as the set of generators and defining relations. On the other side, it's possible to give a geometric interpretation for elements of this group. If we define sigma I as the braid of this type, suppose that we have two planes and endpoints on upper plane and endpoints on the bottom plane. You construct a string between them, and you can define the product of these elementary braids. After the product of some elementary braids, you will construct a braid. Braid is topological object in free space, and you can define the operation of closure, and if you consider the closure, then you construct some link or node in three-dimensional space. And in fact, this group Bn is very important in the low dimension topology, because the main problem in the node theory, it's possible to formulate on the language of this group. And some properties of this group, it's not difficult to see that there is a homomorphism from the braid group Bn onto symmetric group Sn, and which homomorphism is defined by the following rule. Generator sigma I goes to the transposition I and I plus 1. And the kernel of this homomorphism is called the pure braid group and is denoted by Pn. It's important that P2 is infinite cyclic group, and Markov proved that Pn is a semi-direct product of three groups. We have Un, it's free group of rank n minus 1. Here Un minus 1 is free group of rank n minus 2, and so on. Hence, it's the so-called normal form in the pure braid group. And it's a well-known fact that if we have Vs is a solution of a braid equation, then we can construct a representation of the braid group Bn into the group of automorphism V and tensor power n, vector space n. This representation is defined by the formula. Sigma I, generator of Bn, goes to elements Si, I plus 1. But see, it's interesting to formulate the next question. Here we use only operator Si and I plus 1. But in fact, we can define the operator Si and Sj for arbitrary I and J. And the first question, what is pre-image of automorphism Sij, where I minus J is not equal to 1? This is the first question. And the second question, is there a group Gn such that any solution of the Young-Baxter equation, here we consider the solution of Braid equations, define a non-trivial representation of this group into the group of automorphism. Of course, if you have some concrete solution for the Young-Baxter equation, you can construct the group what is generated by the elements Rij, but I ask about the group which in some sense is free for all these solutions. This is our questions, and now I explain the virtual braid group VBN. It was introduced by Kaufman for studying of so-called virtual not fairy. Virtual nodes or virtual links is a generalization of classical not fairy, and the VBN is generated by the classical braid group BN and the permutation group SN. Sn is a group with generators ρ1, ρn minus 1. This is the set of generators, and now the set of relations. Here you can see that ρi satisfies this set of relations. It's relations in the braid group, and here the relations that ρi in square is equal to 1, and this is the so-called the mixed relations. This is the mixed relations, it's for commutativity, and these relations, it's analog of so-called third mixed de Master move. And also it's possible to give interpretation, also geometric interpretation for the generator ρi, but now ρi is not topological objects. It's only some picture on the plane which has the following crossing. And as in the classical case, we can define a homomorphism from VBN into symmetry group Sn by the formula C. Sigma I and ρi goes to one element ρi. And the kernel of this map is the so-called virtual pure braid group. And this group is defined by the following elements. Lambda I plus 1, it's the product ρi sigma I inverse. Lambda I plus 1i, it's a conjugation of this element, and it's equal to a sigma I inverse ρi. And now we can define the other element lambda ij and lambda ji. You can check that's only the conjugation of elements lambda I plus 1, lambda I plus 1i, because its conjugation since ρi plus 1 have the order 2. And it's possible to prove the following result, that this group VBN is generated by elements lambda ij and defined by the following relations, where all indices are different. And you can see that this is a relation of Fock commutativity, but this relation look like as a Young-Baxter equation. And here it's possible to give a geometric interpretation. Here you can see that group VP2, and this is a group what is generated by two elements lambda 1, 2, lambda 2, 1, and it's free group of rank 2. And here it's geometric interpretation, and have a look. Here we have a permutation P, and here we have a braid as we describe solution of Young-Baxter equation by solution of braid equation. And now we can prove the following result, that group VBN, it contains as the kernel of VBN, and also it contains the symmetry group Sn, what is generated by ρ1, ρn minus 1. Hence we have the semi-direct product, and Sn acts on the generator of this group but conjugation. And conjugation is defined by the following formula. ρ1, ρn minus 1 with symmetry group, and if A is some element from this group, when A with
with bar is its image and symmetry group Sn, which group acts on the symbol 1, 2, so on, n minus 1. When, if we want to conjugate this element lambda ij by elements A, it's enough considered to action of this permutation onto the indices. This is the formulas of actions. And the group Vpn contains a subgroup Vpn plus what is generated by elements lambda I, j, where I less than j. We can take only part of these generators. And for example, if we have the group Vp3 plus, when this group is generated by 3 elements and defined one relation, you can see that is exactly the Young-Baxter relation. In some sense, it's smaller group what defined the representation for Young-Baxter equation. And in the general case, there is a homomorphism from Vpn to Vpn plus, which defined on these formulas. And now we want to define another epimorphism from Vpn to symmetry group Sn. See, in this case, generator sigma I goes to the 1, and the rho I goes to rho I. And let us denote this group Hn is the kernel of mu, and defined the following elements: xi plus 1, it's sigma I, xi plus 1 I, it's the element of this type. You can see that this element lives in Hn, and now we consider the conjugation by these elements. All these elements live in the subgroup Hn. And in fact, Rabenda proved that the group Hn is generated by element x chi L and defined by the following relations. But have a look on this long relation. It's not Young-Baxter relations. It's a relation of Braid relations, because the first generators is equal to the third generator. And Rabenda found the presentation of this type, Vpn is the semi-direct product, and the group Sn acts on the subgroup Hn by the same manner. It acts on the indices generators. And now we want to give an answer on the questions which we formulated. At first, if we take the permutation P, which acts on the pairs as permutation, and we can define the action P, in fact, on the tensor power n. We define Pij, it's the map which acts on the V in tensor power A to V in tensor power A by the following manner. It acts as P on the I and J factors and as identity on all other factors. And the group Pi plus 1 generated by this element, it's isomorphic to symmetry group Sn, and there is an isomorphism of this subgroup, what is defined by the following. Now let us define the elements. Suppose that we have a solution for the Young-Baxter equation. Now we consider the linear solution, but it's possible to take instead linear as a theoretical solution. Suppose the pair VR is a solution of the Young-Baxter equation, and this map is invertible map. Then for any natural n, we can define the map Rij, which acts by the following formula. As Ri plus 1, it's the map of this type. Now it's conjugation on this map, and now we defined the elements Rij and Rji, where I less than j. It's conjugation of these elements that we defined before. And our results with Dmitry Telalayev, that suppose that the pair VR is a solution of the Young-Baxter equation with invertible R when there is a representation of VPN into the group of automorphism of V in the tensor power n. This is the answer on the second question which we formulated. And if we want to give an answer on the first question, we can see that the maps Sij that defined on the V in power n to V in power n is equal to the following map. Si I plus 1 acts as S on the component I and I plus 1. Here conjugation on these elements. And now we can see that S, I, and J can be defined by the following formulas. And the same as J and I. And the answer on the first question, suppose that we have Xs is a solution of the braid equation with invertible map S, then the map Xij goes to Sij, define a representation of the group Hn into the group of automorphism of this vector space. This is the answer on the first question. And as corollary, we have the following result. Suppose that Vs is a solution of the braid equation with invertible S, or Vr is solution of the Young-Baxter equation with invertible R, when there is a representation of VBN, braid group VBN, into the group of automorphism of Vn, such that what this map is an extension of the representation phi ns and phi n rho, which we defined before. And now I discuss the following, the second question. The question is the following. The question is the following. Suppose that we have two vector space, B and C, and we defined the solution for the Young-Baxter equation on any of these spaces. And we want to construct solution on the tensor product of these spaces. To do it's interesting to define something more general things. I recall the construction of quasi-triangular Hopf algebra. I think that it's introduced by Deinfeld. Deinfeld called the quasi-triangular Hopf algebra. It's a Hopf algebra A such that there is an invertible element A, what is defined on the A tensor A, and this element is called the quantum A matrix, which satisfies the so-called exchange condition, where delta is co-product, delta opposite when we permute component must be equal to the following conjugation. This is the first condition, and also the compatibility condition. Compatibility condition is condition of these two types. Here, R23 its action on the second and the third component as R and as identity on the first component, and here it's defined by the similar manner. And in particular, if we have quasi-triangular Hopf algebra, when this map R defined a solution for the Young-Baxter equation. And now suppose that we have two quasi-triangular Hopf algebra, one Hopf algebra B with co-multiplication, co-unit, antipod, and R. It's R matrices, and the same for algebra C. At first I told about vector space, and we can consider B and C as vector space with some new structures, product, co-product, and so on. And suppose that we have an invertible map R, which is defined on the tensor product C and B, such that the following four conditions. In this case, in this case, we can define on the tensor product Hope algebra. If we define the co-multiplication by the following formula, here co-multiplication on B, here co-multiplication on C, and we consider the conjugation by operator A23. And we can define an antipode by this formula. It's also conjugation, and the co-units, it's only the product of co-units. When our theorem that suppose that the Hope algebras B and C are quasi-triangular and are be an invertible element such that the following conditions hold. When the Hope algebra B tensor C is also a quasi-triangular with the quantum A matrix, what's defined by the following formula. Have a look. If we consider only the product A13B B and A24C, then it's evident solution. But now we consider the product of this form. We take the product A41 and here A23 minus 1. And in some particular case, this theorem was proved in the paper of Reshetikhin and Semyon Tyanshensky. And now I want to formulate the problem which is interesting for me, and I hope maybe it will be interesting for some other people. Suppose that we have a linear solution of the braid equation or the Young-Baxter equation for finite dimension vector space V. When is it possible? The problem is the following. Is there a linear solution of the braid equation or Young-Baxter equation for finite dimension vector space V such that the representation of the braid group Bn is faithful for all n more than 3. Faithful means that the kernel is trivial. And the same question for the representation of Vbn into the group of automorphism. This is the third problem which I want to formulate. And now the second problem. Instead of Young-Baxter equation, it's possible to consider tetrahedron equation. It's equation of this type. It's look like similar. And also it's possible to consider tetrahedron equation of vector space and take tensor product. And also it's possible to consider set theoretical solutions. And the question is the following. What is more general group Gn, such that any solution of the tetrahedron equation gives a representation of this group. For Young-Baxter equation, we understand that it's need to consider virtual braid group. But what is this group in this? This is my second question, and thank you for your attention.
Okay, thank you very much. Any questions or remarks? Okay, I see no questions from the. Maybe any questions from the online participants? In which case you need to switch on your microphone. Okay, you have some nice examples of tetrahedral maps in your last archive paper on groups, but they were not here.
Yes, we have some. Because not only me, a lot of people study solution of tetrahedron equation. Also, we construct some solutions possible to find in our last paper in archive.
Okay. No more, any questions? Okay, in which case, thanks again very much for
okay,
this talk.
Thank you.
So the next talk is online. Is by Azamat Shavlukov. Are you here with us?
Yes, I'm here. I'm ready.
Okay, yeah, I can hear you. I can see you as well. Great. So, okay, just give me a second to move you to the big screen.
Okay.
Right. So, okay, the next speaker for today is Shavlukov from the Institute of Mathematics with Computing Center in Ufa. And he will be talking about catastrophes of solutions to the equations of an isentropic gas flow and catastrophes of solutions to the linear wave equation. So you can start whenever you are ready.
Okay, I'm ready. Can you see my presentation? I'm sorry, can you hear me? Can you see my presentation? Well, I guess
I can
start.
hear you, just the microphone, the other microphone stopped working, so we
Okay,
can hear you and see your slides perfectly.
Okay, it's great. So I'm gonna start. Well, hello everyone. My name is Shavlukov. I'm from Ufa, from the Institute of Mathematics. So we're gonna say about the catastrophes of solutions to the equations of an isentropic gas flow and the catastrophes of solutions to the linear wave equation. The main result is the following statement. Solutions of the one-dimensional hyperbolic quasi-linear gas dynamics system have the same typical singularities germs as the general solution of the one-dimensional linear wave equation. And we have obtained the canonical form of the section of the hyperbolic umbilical catastrophe. It is here. We state that a similar inheritance should take place for the non-one-dimensional cases as well. It should be noted that our main result is only about inheritance, and the classification of catastrophes for even more general systems in forms like that with the following restriction was made by the Moscow mathematician Alexander Akhimov back in 1993. He had described the fault catastrophe, Kasper catastrophe, and the so-called C22 catastrophe. Basically, knowing the catastrophe equations allows us to understand the asymptotics of solutions to these equations in the neighborhood of the gradient catastrophe point. It is the finite point where all first derivatives of the solution approach infinity. This study was made with my scientific advisor Valery Suleimanov, and the result was formulated in the paper that will be published in the mathematical notes during this year. Okay, let's go next. Here we have in the formula number 1 the one-dimensional gas dynamic system. Here U is the speed of flow, rho is the density, alpha is the smooth function with such expansion with this restriction on its coefficients. I'm gonna say about it a little bit later. The function alpha includes P, which is the equation of the gas state. By using Riemann invariants, here they are, we can diagonalize system number 1 to the system number 3. So now we have a diagonal system. Okay, let's go next. By using the Godograph transformation that basically switch roles between independent and dependent variables, we have the following linear system. And we have the following Godograph transformations in Jacobian. C is the sonic speed. Let us suppose that Jacobian equals to 0 in some point. What does it mean? It means that all derivatives tend to infinity. So if the small g equals to 0, then the big G equals to infinity, and all the derivatives tend to infinity. Okay. Also, it means that the gradient catastrophe occurs. Also, it means that the mapping from the Tx plane to RL plane is no longer bijective and smooth. We're going to discuss the asymptotic behavior of the solution in this case. Next slide. By using the Godograph transformation and the formula on T and X, formula number 5, we can reduce the original gas dynamic system to the second order hyperbolic equation without a number, Or if we are going to use the Riemann invariance, we're going to have the equation number 6. Here B is the formal power series that defines the solution. Due to the fact that the equation 6 is hyperbolic equation, we can say that any formal solution to this equation corresponds to true solution. I can say you where to read about it a little bit later if it is the case. Okay, the Jacobian equals to 0 in some point, at this point. What does it mean for the solution, for the coefficients of the formal power series that define the solution? It means the following, or this one. According to catastrophe theory basics, we can impose no more than 2 restrictions in the form of equalities on coefficients of this series. Why 2? Because so-called governing parameters of the catastrophe perturbation can depend only on t and x. So we use both of these restrictions and demand that the following equality to the coefficients of the series B that defines the solution, that defines the formal solution of the equation number 6. Also from this equation and these relations, we have the following relations to the coefficients. Okay, let's go next. And the Jacobian equals to 0 in this point corresponds to critical points in the same point of the following function f. The relations on t and x, this one, are absolutely equivalent to the critical points of this function f. This is the function of arguments u, ρ, and parameters t and x. The description of typical degenerate critical points of functions like this is the typical problem of the catastrophe theory. Should be noted that there is no such potential function in the case of a more general quasi-linear system studied by Rahim. Okay, let us use the obtained relations on coefficients and write the Taylor series expansion of this function f. Here we go. It is formula number 8. And let us take this expansion in the point t star x star. And what happens? These terms, the whole second line and the first term of the last line are gonna vanish. So if we're gonna take this expansion in the point t star x star, this expansion is gonna start by this constant term and 2 cubic terms. Well, I should say that a plus, a minus are constants, h2, h3, and f are all constants, and delta t and z are this one. So what does it mean? It means that the function f is the so-called two-deformation of the function f taken in the point r star l star, and it can be induced from the versal deformation defined by 3-parameter function family like this. What does it mean? It means that the function f can be defined in the following form in the formula number 9. Here k and gamma are smooth functions, and y is the locally smooth change of coordinates from RL to x to y1, y2, tx, which is the local diffeomorphism if t and x are fixed. So we can define the canonical form of the umbilical catastrophe using not just formal transformations, but smooth and bijective transformations. And we are going to do it. After that, we can say that the critical points of the function f, this one, define the solutions of the gas dynamic system by the formula number 10. Here you can see that K3 depends on K1 and K2. in the next slide, we're going to show that K3 depends on K1 and K2 indeed. So by that fact that the F is a two deformation doesn't mean that K3 depends on K1 and K2. It just happened, we just discovered it during our calculations. So this is our transformations. Well, I'm not gonna say a lot about these calculations. It's pure technique. It's not very interesting. Just want to highlight that K3 is the expansion as well. Is the expansion indeed. So K3 can be defined by the following expansion with the following coefficients. So this transformation can be constructed, and mentioned canonical catastrophe form like this can be obtained, and it means that its critical points really can define the solutions to the gas dynamic system by formula number 10. Okay, let's go now to the wave equation. Here we go. The one-dimensional homogeneous linear wave equation with constant coefficient can be written as the system number 12. It can also be reduced from the linearization of the original gas dynamic system as well. Once again, we use the Godograph transformation, and we have the following system, and we have the following Jacobian of the Godograph transformation. Once again, we use the similar substitutions on T and X, and again we have the second order equation, which is now the wave equation, and its solution known very well. Once again, we're gonna introduce the similar potential function. Now we're just gonna call it psi. It has the similar properties, so its critical points are equivalent to the T and X, to these relations. It is the same situation as we just mentioned earlier on the gas dynamics, and its T and X. Once again, we have some relations from the Jacobian, from its equal to 0, from the relations on T and X. Once again, we wrote the expansion, okay, and by using very well-known techniques from the general catastrophe theory, we can describe the fault, cusp, and umbilic catastrophe singularities germs, and all of them can be stretched to the germs or the solutions to the gas dynamic systems. So that's why we're saying about how they coincide. That's why we are saying about the inheritance of catastrophes, because the solutions of the general solution of the one-dimensional wave equation has basically the same catastrophe germs as the solutions to the one-dimensional gas dynamic system. Now, some notes and our current goals. In the very well-known Becker-Stanislavski case that corresponds to this gas equation state, there will be no K3 term in the canonical catastrophe form. In this exceptional case, I have mentioned it earlier at one of the first slides. I have mentioned here, it is the relation on the coefficients of the expansion of the function alpha, which is included in the first equation of the system. So if this one doesn't hold, it's a very special situation. It means that the quadratic terms of the formal power series B from this B, from this B, there will be no quadratic terms. So this will be 0, this will be 0, and this will be 0. It is pretty much different situation. It is not the general case, so we're not going to talk about it. It should be noted that inheritance occurs in the elliptic case as well, but we only described it on the formal level. We cannot prove the conformity between the formal and true solution as it was done in the hyperbolic case. The inheritance was noted in one of the works that we have a reference to, but it was stated that K3 equals to 0, which is not so. There are also so-called dropping singularities. It means that this point equals to 0. It means that the density of the gas tends to 0. We already described them for both elliptic and hyperbolic cases, but they are not inherited. But we think that similar dropping catastrophes should be typical for non-one-dimensional gas dynamics systems as well. Right now we study two-dimensional linear wave equation. After that we are going to study the three-dimensional Laplace equation. Some references. The books number 2 and 7 basically are the main handbooks for catastrophe theory. The works number 3 and 8 are about the dropping singularities. The work number 9 was mentioned here when we talked about the inheritance in the elliptic case. Here it is. The work number 5, this paper number 5, was mentioned in one of the first slides. It is the Moscow mathematician Rahimov that described the classification of the catastrophes to the more general quasi-linear system. The same was done in the paper number 1, but with another restrictions on this system, and works number 4 and 6 are pretty much important works in catastrophe theory as well. Well, this is it. Thank you for your attention. Thank you for the organization of this satellite.
Okay, thank you very much.
Answer your questions.
Thank you very much, Azamat. So, are there any questions or remarks? Okay, no questions from our side. Any questions by the online participants? In which case you need to switch on your microphone. Okay, no questions, in which case let's thank the speaker again. So thanks very much.
Thank you again.
And the last talk will be in person, so it's going to be streamed on the YouTube. Okay, and the last speaker of the whole conference is Sergey Gonin from the Yaroslavl State University, and he will be talking about some algebraic and differential geometric methods in integrable systems with applications to Backlund transformations and homologic of tetrahedron maps. Sergey, please, you can start.
I would like to thank the organizers, especially Satiris, for the opportunity to give this talk. So you see, I will give a review of some recent results on algebraic and geometric methods in the theory of integrable systems with applications to the theory of Backlund transformations for partial differential equations, as well as Backlund transformations for differential difference equations, and to so-called homologic of tetrahedron maps, which are set theoretical solutions of the homologic of tetrahedron equation. And you see a list of works where you can find some results of this talk. Now, first we need to recall some standard notions of differential geometry. We consider a manifold E, which can be in principle infinite dimensional, and
Excuse me, I don't see demonstration.
Да, то есть если вы хотите, надо подключиться на YouTube, потому что тут в Zoom только онлайн доклады.
Нет, а я в YouTube не вижу, у меня параллельно YouTube включен.
На YouTube не видно?
Презентация, да, и все.
То есть на YouTube не видно, что ли?
На YouTube шавлуковская демонстрация стоит.
Давайте я сейчас пришлю вам ссылку. Может быть, вы неправильную ссылку используете. Я пришлю вам ссылку прямо сейчас.
Okay. Excuse me.
Okay, so we consider a manifold E and an integer, non-negative integer n, and we define the notion of n-dimensional distribution C on E. It is such a distribution is an n-dimensional subbundle of the tangent bundle of the manifold. So to define an n-dimensional distribution C on a manifold E, we need to choose an n-dimensional subspace CA at the tangent space of every point of the manifold E. So A is a point. This is at the tangent space at the point A, and we choose an n-dimensional subspace CA, such that this family of spaces depends smoothly on the point A. And moreover, they form a subbundle of the tangent bundle. Next notion, we consider a submanifold S. It is called an integral submanifold of the distribution C if S is tangent to the subspace CA for every point A from S. So the tangent space of the submanifold is a subspace of CA. All right, okay. Now this language of manifolds, distributions, and integral submanifolds allows to formulate a geometric approach to partial differential equations. It is a well-known approach, but known not to everyone. So I would like to say a few details. I think this approach goes back to the mathematicians Élie Cartan and Sophus Lee. And the main idea is the following. For any PDE satisfying some non-degeneracy conditions, we will define a manifold E and an n-dimensional distribution such that solutions of the PDE correspond to n-dimensional integral submanifolds. And the number n is the number of independent variables in the PDE. The manifold E and the distribution C are constructed by means of the theory of so-called infinite jet bundles. I will present this construction. And in this framework, PDEs and many structures related to PDEs, such as symmetries, conservation laws, backward transformations, lax representations, all these structures can be studied geometrically in a coordinate-independent way. And this, as we will see, this has applications in particular to the theory of integrable PDEs. Now, a summary of the main ideas of my talk of the part related to PDEs, which is the main part of the talk. Okay, so using the geometric approach which I outlined, a PDE can be regarded as a manifold E with a distribution C such that solutions correspond to integral submanifolds. So we can in principle forget about the PDE and study the corresponding manifold E and the distribution C, because they contain all the information about the original PDE. The geometry of E and C contains all the information about the PDE. In particular, solutions can be reconstructed as integral submanifolds. And the idea is to study geometric and algebraic invariants of E and C. They will be invariants of the PDE. And recall an important invariant in algebraic topology. For each topological space X and each point A of X, one has the fundamental group. And we will do something similar for PDEs. For any analytic PDE and each point of the corresponding manifold, I will define a so-called fundamental Lie algebra. So the fundamental Lie algebra is, its role for PDEs will be somewhat similar to the role of fundamental group for topological spaces, but for some reasons, for some important reasons which I will explain, in the case of PDEs, we get a Lie algebra, not a group, but a Lie algebra. So what? The main properties, the importance of them comes from the following: fundamental Lie algebras are new geometric invariants for PDEs. Computing these Lie algebras, we get interesting infinite dimensional Lie algebras. And the computations have been done in collaboration with Gianni Manna from Torino. And using fundamental algebras, one obtains new results on backlog transformations and zero curvature representations, in other words, Lex representations, which play important roles in the theory of integrable systems. And now, the main idea of the definition is the following. The classical fundamental group can be defined by means of topological coverings of the space X. And the fundamental Lie algebra of a given PDE at a given point A can be defined by means of so-called differential coverings of the PDE. So it turns out that one can introduce an analog of coverings for PDEs, and they are called differential coverings, and one can use them in order to define some analog of the fundamental group. However, this analog will be a Lie algebra, not a group. Okay, now summary of applications. Using fundamental algebras, we obtain necessary conditions for existence of a backlog transformation between two given PDEs. Is it possible to remove this thing? Thanks a lot. Yeah. Okay. Next application, necessary conditions for existence. So using fundamental Lie algebras, we obtain also necessary conditions for existence of a non-trivial zero curvature representation for a given PDE. And these necessary conditions really work, and in some cases they allow us to prove non-existence of backlog transformations for some pairs of PDEs and non-existence of non-trivial zero curvature representations for some classes of PDEs. And I would like to emphasize that here we consider the widest class of backlog transformations, not necessarily of Miura type. Well, there is an important class, there is an important particular class of backlog transformations, so-called Miura type transformations. I will discuss them separately, but they are important, but they form a relatively small class of all backlog transformations, and in this theory we consider the widest class of Bechdel transformations, which is much wider than the class of Miura-type transformations. In particular, our Bechdel transformations can depend on derivatives of arbitrary order. And next application, we find a normal form for zero curvature representations of a given 1+1 dimensional evolution PDE with respect to the action of the group of local gauge transformations. And another interesting result, in my opinion, is the following. We get invariant meaning for infinite dimensional algebras and algebraic curves related to some PDEs. So it is well known that studying integrable PDEs, one constructs Lex pairs and where one can see infinite dimensional algebras and sometimes some algebraic curves, but the construction depends on the choice of coordinates. So one gets just coordinate formulas, and from them one can see algebraic objects. And here we have a geometric construction. We have a geometric object, a manifold with a distribution, and a very general geometric construction, which gives Lie algebras in a coordinate independent way. And for 1+1 dimensional soliton equations, those Lie algebras often turn out to be infinite dimensional and quite interesting. And also one can extract, by means of some algebraic and geometric procedures, in an invariant coordinate independent way, one can extract algebraic curves from those Lie algebras. Now, as I said, we use so-called differential coverings of PDEs. This notion was introduced by Vinogradov and studied by Vinogradov and Krasilchik. Let me show you first a classical example, the Miura transformation from MKDV equation to KDV equation. We consider we have here the MKDV equation, which is an equation for a function the function v of two variables x and t. Here the classical KDV equation for the function u of x and t, and this formula is the famous Miura transformation. It's the statement is the following: for any solution v of this equation, the function u given by this formula is a solution of KDV, and moreover, for any given solution of KDV, for any given solution u of KDV, if u is given and satisfies the KDV equation, one can consider the system of these two equations, and this system always has a one-parameter family of solutions. So this means that for every solution, its pre-image under this map is a one-parameter family of solutions of MKDV. I will explain why it is, why we call it, why Vinogradov and Krasilchik call it a covering. There is some natural geometry behind it, which I will explain. For the moment, I give an informal definition in coordinates, and in a few slides you will see geometry. Okay, so, but let's give first an informal description in coordinates. We consider a PDE for a function, for a vector function v of variables y, a PDE for a function vector function u of variables xi, and a map from solutions of this PDE to solutions of this PDE, a map of this form where the right-hand side you see can depend on y, v, and arbitrary partial derivatives of arbitrary finite order. And the requirements are the following. For every solution v of E2, these formulas give a solution of E1, and moreover, for any fixed given solution u of E1, its pre-image under this map is a family of solutions of E2 depending on a finite number d of parameters. And in the geometric definition, which I will explain in a few slides, this number d of parameters will be the dimension of fibers of the covering. So in the case of PDEs, differential coverings, they have fibers, but the fibers are not discrete sets. Now the fibers are finite dimensional manifolds. So the PDE itself is an infinite dimensional manifold, and we consider some maps of it, some coverings of it, and the fibers of coverings are finite dimensional manifolds. And there are also some requirements on the distributions. You see that, you remember that we have a distribution on our manifold E, and the geometry of the covering uses the distribution. I will explain this. Okay. Now, a geometric definition of coverings, differential coverings, will be given in a couple of slides, but for the moment I would like to recall what is a background transformation in this language. Well, using the language of coverings, one can say the following: PDEs E1 and E2 are connected by background transformation. If there is another PDE E3 with a pair of coverings, a covering from E3 to E1 and a covering from E3 to E2, such a diagram, and we consider only coverings with finite dimensional fibers. The theory of such coverings is rich enough. Well, at least it is rich enough for the case of 1 + 1 dimensional PDEs. And such a pair of coverings allows one to obtain solutions of E2 from solutions of E1. We take a solution of E1, we find its preimage in E3, and we project to E2 by the second map. So take a solution here, find its preimage, and project. And let's consider another classical example. We have the KdV equation here, and here E2 is the same KdV equation. The E3 is this equation, which is mKdV with parameter lambda. Lambda is a fixed constant, and we have two coverings, this one and this one. You see they are very similar, but they are different because we have minus sign here. And this allows one to do the following: we take a solution of KdV, we find its preimage, and then the preimage will be a one-parameter family of solutions of mKdV, and then we project, and we get a family of new solutions of KdV. So starting from one solution, using this procedure, we get a family of solutions which can be more interesting than the original solution. For instance, if we start with the trivial constant solution, find its preimage and project, we get a family of solutions containing one soliton. Now we take one soliton, find its preimage and project, we get a wider family containing two soliton, and so on. All multi-soliton solutions can be obtained by this procedure, and this is a well-known result. Now, a geometric approach. Now I would like to explain how to construct a manifold E and a distribution C for a given PDE. It's instructive to consider an example to get the idea. We take the KdV equation. The infinite jet space in this case will be this infinite dimensional space. Here we have x, t, u, and all partial derivatives of u. But now these partial derivatives, they are regarded as abstract symbols which are coordinates of the infinite dimensional manifold J infinity. So J infinity is an infinite dimensional manifold with these coordinates. And we have two special vector fields on this manifold, the so-called total derivative operators. So the structure of this dx and dt is clear, and they can be regarded as vector fields on this infinite dimensional manifold. Moreover, they commute. Now we consider the KdV equation. We differentiate it with respect to t and get this consequence. Differentiate KDV with respect to x, we get this consequence, and so on. We differentiate KDV with respect to x and t any finite number of times. We get a collection of algebraic equations in those coordinates. So you see, each of these equations is an algebraic equation in these coordinates. We get an infinite collection of algebraic equations on this manifold, and we consider the algebraic variety determined by this infinite collection of algebraic equations. It's easy to see that this algebraic variety will be non-singular, so it will be a manifold, an infinite dimensional manifold, and it is possible to give rigorous definitions what are infinite dimensional manifolds in this case. Moreover, the vector fields dx and dt are tangent, so this manifold we denote by E. It's easy to check that the vector fields dx and dt are tangent to it and span a two-dimensional distribution on it, so a two-dimensional subbundle of the tangent bundle, which is the distribution C which we wanted to construct. And then solutions of KDV correspond to two-dimensional integral submanifolds of this distribution. So here we have the case of two independent variables x and t, and we get a two-dimensional distribution. Now consider the general case of n independent variables. Then we get a manifold with an n-dimensional distribution called the Cartan distribution. And as I said, solutions correspond to integral submanifolds. Now, a geometric definition of differential coverings. So for us, from now on, PDEs are replaced by manifolds with distributions. So let's consider a PDE E1 with distribution, a manifold E1 with distribution C1, distribution E2 with distribution C2. And what is a differential covering in the geometric language? We consider a bundle tau with finite dimensional fibers such that the differential of the bundle tau preserves the distribution. Namely, moreover, for each point, the differential tau star, the differential of tau determines an isomorphism of the subspaces of the distributions. So on the level of distributions, tau, the differential of tau is an isomorphism at each point. This is a natural requirement. So why such maps are called coverings? Because let us consider a special degenerate case when the distribution is the whole tangent bundle. Then what we get? Suppose that our distribution is the whole tangent bundle. Then we have a bundle tau such that it determines, such that its differential is an isomorphism of the tangent spaces. This means that tau is a local diffeomorphism, and a local. So we have a bundle which is a local diffeomorphism. Therefore, it is a covering. It is a topological covering. So in the case when the distribution is the whole tangent bundle, differential coverings are just topological coverings. But in general, our distribution is a sub-bundle, and then the class of differential coverings is much wider than the class of topological coverings. So recall that topological coverings of a manifold M are determined by actions of the fundamental group. We want to introduce an analog of the fundamental group for differential coverings, and we will do this. I will explain the main idea. The definition will be given later. I would like to describe first some properties of the fundamental Lie algebra, but here I say why we consider Lie algebras instead of groups. So for topological coverings, fibers are discrete, and a discrete, in the case of topological coverings, a discrete group acts on the fiber. For differential coverings, we consider differential coverings with whose fibers are finite dimensional manifolds, and one can expect that some Lie group acts on the fiber, and the groups, but the construction, well, as a result, one gets infinite dimensional objects. And it is not convenient to work with infinite dimensional Lie groups. So it's more convenient to replace infinite Lie groups by Lie algebras and study things locally. Because the local geometry of differential coverings is rich enough. So for topological coverings, local geometry is trivial, but for differential coverings, even local geometry is non-trivial, and we study local geometry, and because of this, one can replace Lie groups by Lie algebras. That's why we get a Lie algebra instead of a group. So for every differential covering, I will skip the word differential. From now on, I just say every covering is a differential covering. The fundamental Lie algebra acts on the fiber of the covering. The fiber is a manifold, and an action of Lie algebra on a manifold is just a homomorphism from this Lie algebra to the Lie algebra of vector fields on the manifold. Okay, I have to be very quick now. Recall that if we have a topological covering, then the fundamental group of the covering manifold is embedded in the fundamental group of the base. One has a similar property for differential coverings, and this allows one to obtain a necessary condition for existence of a Backlund transformation between two given PDEs. We take here, suppose that E1 and E2 are connected by Backlund transformation, then the fundamental Lie algebra of E3 is embedded into the fundamental Lie algebra of E1 and to the fundamental Lie algebra of E2, and these embeddings are of finite codimension, because the codimension of the embedding is equal to the dimension of the fibers of the covering. However, the algebras themselves are, in many cases, are infinite dimensional. So if we have such a Backlund transformation, then the fundamental Lie algebra of E1 and the fundamental Lie algebra of E2 have a common subalgebra of finite codimension, and this is a necessary condition for existence of a Backlund transformation between E1 and E2, because the algebras themselves are infinite dimensional, but they must have a common subalgebra of finite codimension. Okay, and this necessary condition allows us to obtain non-existence results for Backlund transformation. So it allows quite well. There are already a number of examples where we have a pair of PDEs, and this necessary addition allows us to prove that there is no Backlund transformation between these two given PDEs, and to my knowledge, this is the only available method to prove that there is no Backlund transformation of general type between two given PDEs. All right, and well, here I have the description of the results. No time to read. Well, you can read, and I can send you the slides if you are interested. And so a list of examples is here. Now, what the main idea of the definition of the fundamental Lie algebra for a PDE? First we recall some version of the definition of the classical fundamental group. The classical fundamental group can be defined without using loops, using only transformations of fibers of the covering. Well, for every covering we have, if G is a fixed element of the fundamental group, then for every covering we have a transformation of the fiber. And if we have such a diagram where tau 1 and tau 2 are coverings, then this relation holds. And it is well known, but not to everyone, that a given element G of the fundamental group is uniquely determined by the collection of transformations of fibers of the covering. So the element G determines a transformation G2 of the fiber for every covering tau. So for every covering tau, we have a transformation of the fiber coming from G, and this infinite collection of transformations uniquely determines the element G. And they are in agreement with respect to each commutative diagram of this form, where phi is just any continuous map and tau 1, tau 2 are coverings. So this relation always holds. And then one can define an element of the fundamental group as a collection of such transformations satisfying this requirement. So no need to use loops, just an element of the fundamental group is defined as a collection of transformations of fibers of the coverings. Okay, now one can use a similar idea to define fundamental Lie algebras for PDEs. Here now transformations are replaced by infinitesimal transformations. So infinitesimal transformations are vector fields. So transformations are replaced by vector fields. But transformations of fibers are replaced by vector fields on fibers. And here is the main idea of the definition. An element of the fundamental Lie algebra is a collection of vector fields. For every covering, we have a vector field on the fiber such that for every commutative diagram of this form, where tau 1 and tau 2 are coverings and phi is an analytic map, we have this requirement, which is the analog of this requirement.
Okay, Sergey, you have 3 minutes.
Okay, so right, and but here I use the word formal. This is the main idea, but not the precise definition. To give the precise definition, one needs to use so-called formal vector fields instead of analytic vector fields. So, one needs to consider formal power series, and Lie algebras of vector fields on fibers are replaced by arbitrary Lie algebras. Well, if you are interested, I can give you details after the talk. I have to skip a lot of things. You can find details in the works which I mentioned. Okay. Well, Miura-type transformations is a particular class of Bechdel transformations, and one get results on them. No time to describe them, unfortunately. And some results can be translated to the case of differential difference equations. For instance, construction of new Miura-type transformations for differential difference equations. Here is an example of a new Miura-type transformation for this Narita-Ito-Bogayevlensky lattice, which is a differential difference equation. And finally, a few words about tetrahedron maps, which are theoretical solutions of the homological tetrahedron equation. This result is not related to the previous content of the talk, but I like it, so I would like to advertise it. For every associative ring and every element M of the ring A, these maps are tetrahedron maps. And if we take the ring of n times n matrices and consider this particular matrix, then these maps are Liouville integrable. That's all. Thank you for your attention.
Okay, thank you very much. Any questions or remarks? Okay, this is one question.
Да, есть вопрос, но может другие зададут.
Do you have some? You said about Backlund transformation. Yes. If you are given two equations, you can prove that they are not connected by Backlund transformation. If so, but if not, you have two equations and they have Backlund transformation. Can you give an algorithm to find this Backlund between these two equations?
I can tell you what I can do.
No, only answer yes or not.
Well, some particular class. Let me explain.
No. Yes or no. Can I use, for instance, if I will need, can I рассчитывать на это или нет?
Look.
Yes or no only.
Partial yes.
Partial. Thank you.
Partial yes. Okay.
Okay. There is one online question, I understand.
Я не понял, вот вы приводили пример Бэклундов, да, что вот как строить n-солитонное решение для КДВ из постоянного решения. Это не фокус, но вы посредством отражения от Миур, да, и вы полагаете, что это новый пример или вы
This is a classical example. I said this example is well known, of course. This example is well known.
Известно, нет, именно как посредством отражения с Бэклунда. У нас, просто я помню, приятель мой, уже покойный, Равиль Емилов, в начале 90-х годов очень сильно, у него статья, и даже, по-моему, в физике опубликована, но как-то она не получила широкого отклика. Он очень гордился, что вот берем КДВ решение, раз его туда, в этот самый, например, в МКДВ, потом обратно вот новое решение и так далее. То есть вот этот трюк у него был. Точно он даже им гордился, хотя общественность не оценила.
I said several times that this example is well known. It's just motivation.
Excuse me.
Yes.
Sure.
Okay, any more questions or remarks? Okay, in which case, let's thank the speaker again. So was the final talk actually. So on behalf of all the organizers, I would like to thank you once again for finding the time to come here, especially to all of you who remained until the very end and suffered the 5 conference days on so many different topics of science. So we will be happy to have you again next year. So thanks again.